Analyzing big data is hard and slow. I personally hate wasting minutes or even hours for my computations to finish. If you took the first course of our specialization, you have probably understood it yourself. Nevertheless, big data is everywhere now, so professionals are getting pretty tired of all this waiting. And more, you have to really master the time management to plan your work effectively and not to waste the money of your employer. You might say, that sounds awful. I should ask for a refund and go learn some fun and fast stuff like web programming. Sure thing. We're all free to do whatever we like. Free will, you know? But if you could spare me a minute right now, it might save you much more of your own time in the future. I will tell you a secret. All the best minds are working on speeding up frameworks for big data analysis. There is Apache Test, which can speed up your Hive queries. Another example is Apache Spark. Spark can be blazingly fast, but being a general-purpose framework, it gives you all the knobs to shoot yourself in the foot and write code that is really slow. But don't worry, I will help you save both legs. In the final week of the course, we will dig deeply into the Spark execution model. You will get a solid understanding of Spark internals. You will learn about partitioning and serialization. We will squeeze another second from the nearly optimal implementation of PageRank provided by Natalia. You will master Spark SQL and know how to optimize your computations with Catalyst. And finally, you will learn how to manage resources of your Spark app. To be honest, the skill that is so rare that is worth another couple hundreds in your paycheck. Still want to learn web development? Guess not. Jump in and let's do fun stuff on petabytes of data fast.
To the best of my knowledge, the ancient Greek philosopher Aristotle was one of the first who popularized analytics. Of course, nowadays it has a different flavor, but anyway it is useful. Analytics is art to find patterns in data, the ability to divide a vast amount of data into logical groups, and the ability to find hidden components. With the help of data analysis methods and technologies, you can easily count the number of website users from service logs. You can analyze your target audience and build users' profiles, which can help you make decisions based on data. For example, by analyzing communications with your customers, you can extract the most common service problems. Locating and solving these problems is beneficial for your customers and you as a service provider correspondingly. You either know by yourself or you have learned from the first course of this specialization how to work with Hadoop MapReduce and Apache Spark. However, as you can understand, it is not the end of the journey. So many years passed since MapReduce article was published in 2004. MapReduce, which was previously considered a high-level programming language for big data, is not a high-level tool anymore. You can even use structured query language, or SQL for short, on top of big data. Moreover, it will be much more efficient than writing your own MapReduce applications. My co-authors, Pavel, Natasha and again Pavel, will tell you more about high-level tools which you are going to learn. They will also explain the structure of the course and make an overview of the assignments. Stay tuned!
To make a fast and high-quality analysis, you should use special instruments suitable for data analysis. A code for such instruments look more simple and understandable than a code on MapReduce and even on Spark. Could you imagine my first impression when I realized that I could write a code not on MapReduce for my task, but solve them by simple and elegant SQL query? Thank you, developers from Facebook! You made my life easier. A tool that allows you to do this is called Hive. And this is one of two general analytical instruments that we will deal with in our course. The second, very important engine we will use in analytics is called Spark SQL. It also works on big data by SQL queries, and it has the same simple syntax like Hive. The same performance as Spark or even better. and also it well integrated with any possible data sources that you will deal with. It allows you to place together data from text files, pandas data frames, SQL table, and many other sources. In our time, processing the data without Hive and Spark SQL is the same as using pigeon mail in the age of the internet. So, join the course and become big data professionals.
Having reached my part of the course, you already know how to work with huge data volumes using MapReduce Spark, as well as such high-level tools as Hive and Spark SQL. But, as Leonardo da Vinci said, he who loves practice without theory is like the sailor who boards ship without a rudder and compass and never knows where he may cast. So, to analyze big data, you should not only master the usage of practical instruments, but also let a bit of street magic, but also let a bit of maths into your life. But smart is the new sexy, isn't it? My students will be lucky to know that the public transport scheme, bank transactions, your friends in your favorite social network, and a lot of other data can be represented in shape of such mathematical abstraction as graph. That will let us employ the graph theory developed since 1736. But as far as our course is a hands-on one, we shouldn't forget about the practical side, and you will review how to store graph data in RAM, how to aggregate graph data using Spark and Spark SQL, as well as a high-level tool as GraphFrame package. Moreover, we will discuss how social networks are trying to make every person an extrovert, expanding his social graph. Sounds pretty evil and sinister, doesn't it? Have no fear. I'm always here to take all your fears away and lead you through the cobwebs of how to detect spammers. Further, we will examine what concept Google uses during processing your search query and how graphs are connected to it. And you will discover how to find the most influential users in your favorite social network and become one of them. Finally, a cherry on top, you will write your own code to find the most rocking music meeting your specific taste, using graph algorithms, of course. So, see you during the weeks 3 and 4. I'm going to do my best to make your educational process smooth and exciting.
Hello! Remember the previous course where we learned how to store data in HDFS and process it with Hadoop MapReduce and Spark RDD? We even broke down several real-world applications into a chain of MapReduce jobs. Think back of all the complexities of this process. So this course will teach you how to use more high-level programming languages for big data applications, which hide these complexities for you. Understanding of low-level implementation details is essential to become a good big data engineer. What you get from upcoming lessons? By the end of this week, you will be able to use high-level language to write a few lines of code that will spawn several MapReduce jobs. You'll know how it works under the hood. Finally, you will be able to tune up your applications according to existing cluster configuration. Sounds cool, doesn't it? So let's get going. There are two most popular high-level programming languages for batch processing MapReduce pipelines. They are Hive and Pig. Pig is a procedural language used to explain in script how you would like to process your data. Hive, on the other hand, is a declarative language focused on the semantic of what you would like to achieve. Hive is quite similar to a structured query language, also known as SQL. Surely there are a lot of people who believe that knowing SQL can assure all their needs. They are right, definitely. It also doesn't require additional time and effort of learning another procedural language. Nobody wants to rack his brains, but nobody will give you a silver bullet. There are problems that could be easily solved with Hive and with Pig, correspondingly. According to Google Trends, Hive is almost twice more popular than Pig. That is why I have chosen HiveQL language for this course. I will show you how SQL can help us to solve several typical business problems. Imagine your company owns a website portal, and users all over the world access different pages of a website. Naturally, you would like to create positive user experience and optimize or personalize page content for website customers. By doing a simple market research and collecting data about our customers, you get the most popular regions users query our website from, quantity of real and fake users, male-female distribution of customers in different regions, and the average age of our customers. What do we use? Web service logs, a geobase of IP addresses, user personal data such as gender, age, or occupation, and bot database. Here are a few examples of web service access logs in case you are unaware of this format yet. Experienced users already? Feel free to skip through the video and test yourself with the help of in-video quizzes. For those who have stayed, here is a slide with log examples of default Apache HTTP server configuration. By no means you know it's one of the most popular web servers. The first item in a log is IP address, which is used to identify user's location. There are several types of IP addresses, IP version 4 and IP version 6. IPv4 has a limitation of the number of computers connected to each other. IPv4 consists of 4 numbers from 0 to 255 or 32 bits overall. Therefore, we could have at most 4 to 5 billion IP addresses. Do you know how many people are here on the Earth? I think you get the point. IPv6 has 128 bits, which is, in short, way more bigger. So service providers can stop worrying about running out of addresses. Being mostly obsolete, the second field is usually a hyphen, whereas the third field is the user ID of the person requesting a web page as determined by HTTP authentication. Happen to know what HTTP stands for? HTTP stands for Hypertext Transfer Protocol. Want to know the time when a request was received by a web server? Check the next field. There are different types of requests. Two most common are GET and POST. GET reads data from a web server, while POST sends data to a web server. This field helps you to understand what exactly has been requested, like cooking web page or Python 3 features overview. Time to see the next field, which is a status code of user's request. 200 means everything is okay. Numbers starting with 3 tells browser to redirect user's request. If you see 4, oops, user could have requested a non-existent page. Number 5 shows a server-side problem, like a database where you store website critical information is down, and your users are desperately trying to reach it. Want to see the number of bytes per user's request? Check the next field. No data? You will see a hyphen in this field. All previous fields were related to a common log format. Another default Apache log format is combined log format, containing 2 more additional fields. Referrer is a previously visited web page, which can be located on another website. New user browsing session? Then this field will be marked by hyphen. Interested in users' browsing patterns? Check this field. For example, you can find out pages that are usually referred from news websites, whereas some pages are more visible from search engines, and some are only accessible via internal links. See this field? It is a user agent. The information in this field is provided by client's browser. What do you get from it? First, browser's type and version. Examples are Firefox, Opera, Internet Explorer, Google Chrome. Second, an operating system. Examples are macOS, Linux, or Windows. Using this info, we can assume user's profile. Surely, being a brownie website administrator, you would like to adjust log format for your needs. Examples on the slide show you a configuration where fields are separated by tab characters and date is encoded in more machine-parsable format. One of the most important fields for logging is cookies. No. Put the box of cookies back to the shelf. It is a small piece of data sent from a website and stored on a user's computer by a user's browser. This piece can be small, but it will help you to identify user and store recent users' activity to personalize content. Provider of a music streaming service can personalize the next song by users' like-dislike history. Now, as we know log file structure, it's time to turn back to our business use cases. The first case: what are the most popular regions users query our website from? We have Apache access logs with user HTTP request meta information such as IP address, requested page, refer, status code, and so on. We also have a geobase. The geobase is hierarchical structure where you can get region by IP and a nesting level. For example, the following IP belongs to Russia on one of the highest levels. Then it belongs to Moscow on the city level. Then it belongs to central part of Moscow one level deep further. For simplicity, we can assume a flattened storage format for geobase as you see on the screen. To answer our question, we have to first join by IP address, second solve MapReduce problem similar to word count to aggregate hits by region, and finally we need to sort regions by a number of occurrences in the logs and choose top 100 regions. Therefore, we see chain of 3 MapReduce jobs: join, word count, and limit. Next example is very essential. What is the amount of queries made by real and fake users? For real users and bots differentiation, we need another dataset. It contains all info such as bot's name, list of user agents, IP address or IP network used by this bot. We will answer the question if we join our dataset by a complex key consisting of IP address and user agent, and by solving word count problem. Bear in mind that in a word count problem, here we have to use complex value aggregation as we have several fields, not one. Overall, we have here a chain of 2 MapReduce jobs, join plus word count. More complex example. Male-female relations questions have never been easy. What is a distribution of male and female customers in different regions? To answer this question, nothing can help us 3 datasets: access logs, geobase, and personal data. Personal data can be in a form of tabular data similar to what you see on the slide. The solution to this problem could have a chain of 3 stages: join of access logs and the geobase by a simple key, IP address, the following join with personal data by a complex key, and finally, complex word count problem. Overall, join, join, word count. Still with us? Let us dig in a bit further. What if we are going to find out the average age of our customers in different regions? We still have the same 3 datasets. The only change will be the last MapReduce stage, where instead of word count, we will find out average value for each key. Do you remember how to speed up these kind of calculations with combiner? You don't? Feel free to revisit or skim through the slide of the first course of this big data specialization. Now imagine how much of boilerplate MapReduce code you will write to solve these problems during your homeworks. Please take a deep breath and release. I'm kidding. I'm not going to force you into writing it on MapReduce. Though it might be a good practical exercise. We are going to use SQL-like language, whereas SQL queries will be translated automatically into a chain of MapReduce jobs. It is the beauty of Hive framework and programming language called HiveQL. Ladies and gentlemen, get ready. Now I present you solutions for all 4 previously presented problems on Hive. In the first use case, we do join of 2 tables by a simple key, then aggregate data by region, order by hit count, and limit the output by most popular ones. Don't feel comfortable with SQL? Be my guest and see a short introduction for you in optional videos. Thus, you will be able to revisit this video as soon as you gain the necessary theoretical knowledge. Now you see how to solve the second problem with Hive query language. We have complex join and complex aggregation function. I highlighted left outer join. If you don't understand what it is used for, then please revisit SQL optional videos. Look at the next use case. What a handy API to do several joins in a few lines of code we have here. The last example looks even simpler. Function avg is doing combiner optimizations for you. If you are not scared of reading Java code, then you can take a look at an implementation in the source code. Summing up, in these and previous videos, you have become familiar with web service logs and service log configuration options. Mark my words, access logs are one of the most popular data types data engineer and data scientists deal with. You now know that there are several high-level programming languages for big data. For example, one of them is Hive, which is a declarative language, and another is Pig, which is a procedural language focused on semantic how. You have seen 4 business use cases solved with the help of Hive, so you should be able to solve similar problems by changing several lines of code. In the next videos, you will learn how it works from implementation point of view, so you will know what optimizations options are. Hello! Ready to walk through basic concepts of a structured query language? Jump in, cause by the end of this video you will be able to extract data from a database table, filter and order data, aggregate data according to some rules, join data from different tables, and use subqueries for more complex data analysis. First things first, let me introduce a few concepts. Relational algebra provides a theoretical foundation for relational databases, in particular query languages for such databases and their practical optimizations. In relational databases, we have relations, also known as tables. Each relation has an arbitrary number of tuples and a fixed number of attributes. Tuples are related to table rows, and attributes are related to table columns. Relational algebra provides a common set of operations, such as projection, selection, rename, and joins. Wanna get a simple example? See the slide for a slice of SQL table. If you need to extract particular columns from a table, use a projection operation. It has the following syntax: select, comma-separated list of columns, then from statement and the table name you are working on. Usually, there are several tables in one database. That is why it is necessary to specify a relation name or a table. Cott introduced the relational model in his paper in 1970. Well-known nowadays selection operations were originally called restriction operations, which makes a lot of sense. With the help of selection operations, you can limit the output only to requested rows. For example, you can extract only the rows from our customers table where column country is set to Mexico. See how natural our SQL query looks like. You have select asterisk, meaning get all columns, then from and a table name, then where statement and our condition. Country equals Mexico. That is why SQL is sometimes pronounced as SQL, which stands for Structured English Query Language. Need to combine several conditions? Combine them with logical AND statement, as in the example that you see on the screen. Do you want to mix projection and selection operations? Use a comma-separated list of target attributes instead of asterisk. Another selection operation used to sort out or order the output is order by clause. If you order our relation by country, then you should see rows related to customers from Argentina before customers from Austria, customers from Belgium before customers from Brazil, and so on, in alphabetical order. This order is ascending by default, but you can easily reverse the order by adding DESC acronym, meaning descending order. Remember that having several columns to sort on, we use a comma-separated list and choose type of ordering for each of them. See the following example to get the idea. You have a customer from the USA, and this could be a problem due to the great number of states there. A nice way out of the situation is doing ordering first by country and second by state. And feel free to combine order by with other projection and selection operation. Now it's time to reveal the full power of SQL. Having a relational database means having a lot of relations. On the slide, you see example of Chinook database consisting of 11 tables and connected to each other by different fields. Consider simple example. 2 tables, customers and orders. Customers table gives you information about your customers. Order tables naturally tells you about customers' transactions. Keeping a unique customer ID instead of full information is not a mistake. Intellectually curious are welcome to get a theoretical foundation in Wikipedia article about normal forms and database normalization. In a nutshell, who wants to update all your tables when your customer changes a name after a wedding? That is why there is a single copy of all the information about a customer and it is stored in one table, where it can be requested or related when needed. The power of SQL are joins. You can join customers and orders tables by customer ID. The syntax of a join is the following: from table 1, join table 2 statement on and join condition. In our case, orders.customers.id should be equal to customers.customer.id. Bear in mind the syntax to access attributes when you have several tables in a query. To access an attribute, type table name dot and the attribute name. There are different types of joins. They are inner join, left and right joins, and full outer join. Check the images on the slide to understand the purpose of these joins. If you use default join statement, which is inner join, then you see in the output only the rows that match in both tables. For example, if you have an order with customer ID -2 and there is no customer with this ID in customers table, then you will not see this row in the output. If you would like to see all the rows from orders table despite missing rows in customers table, then you should take a look at the left or the right join. The difference between left and right is only in order of tables around join statement. For the aforementioned use case, you have to place orders table on the left before join and use left join, or you can place orders table on the right after the join and use right join. All missing values from another table will be substituted by null values. Do you want to know the quantity of customers' orders per day? Don't forget to mention customers absent from the customers table and customers without transactions. Quite a task, yeah? Nope. You need to perform full outer join of orders and customer tables. Just to make sure you understand the concepts and difference between joins, take a look at the 2 tables, A and B. A has values from 1 to 4 and B has values from 3 to 6. Make sure that you understand joins presented on the screen. In one of the previous examples, I touched upon the point of data aggregation. There is a special clause for this case called group by. For example, you would like to count the number of customers in each region. You can aggregate data by column country or by 2 columns, country and state, for more granular report. For each aggregation key set, you can count different statistics. The most common one is count, to calculate the number of occurrences. For orders table, you can aggregate transactions by date and count minimum, sum, average, or maximum value of transactions. Semantics of these types of queries is here for you on the screen. Every time students learn SQL, they happen to mix where and having clauses. A simple rule of thumb might be of great help. Where is way more cheaper and efficient. It is applied when we read data from a table, and there are a lot of optimization techniques, such as indexes to skip a bunch of rows. Having, on the other hand, can consume huge amount of resources. It is used to filter data after aggregation. For example, you cannot select regions from customers table where you have more than 10 customers with where clause, but you can do it with having clause, the way you see on the screen. The last functionality we are working with is subqueries. Subqueries are used to combine several SQL queries. For example, here I have selected all customers from previously chosen countries. Summing up, you know how to extract, filter, and order data from a database table with the help of projection and selection operations. You know how to aggregate data and combine several queries into one SQL query for more complex data analysis. You know how to relate data from several tables and the difference between join types. By the way, don't miss a really good resource to learn basics of SQL. Check out the W3 School portal for interactive SQL tutorial. There are several more useful SQL operations that I haven't covered during this intro. They are data insertion and removal. Nope, I haven't forgotten about them, as they have some differences for Hive query language. Oh, I nearly forgot. Wanna prove yourself? There is a really good way to do it on that website. Personally, I set the test for less than 5 minutes. Okay. I had a call in between. What is your score? Hello. Having seen a few examples of Hive queries, you are up and ready for a big dive into Hive architecture and peculiarities of its work. Hive was originally developed as a data warehouse solution at Facebook. It has been designed to work on top of HDFS and MapReduce framework. Nowadays, it has integrations into such storage layers as Amazon S3 and distributed NoSQL database HBase, which is also a part of Hadoop ecosystem. Hive can work on top of different execution layers, such as Apache Test and Spark. Details of these integrations will become clear after this course. Imagine you have been requested to build a data warehouse solution on top of HDFS. You have tons of unstructured data in a distributed storage, and for analytical purposes, you need to relate data of one dataset with another. To accomplish this task with SQL-like language, you have to somehow transform, at least metaphorically, our datasets into a tabular view. So it is becoming natural to have meta-information about our datasets. That is why Hive defines a concept of a metastore. Metastore provides information about data layout in HDFS. It is different from HDFS name node because it helps to answer the question what exactly is stored in a particular folder. For example, if you have Apache logs stored in HDFS, then name node answers the questions where blocks of files are located, and metastore explains that the first field in a log line is IP address, the fourth field is date, and so on. As I have already said, metadata is not stored on a name node. It is not stored in HDFS either, and there is a reason for this. HDFS is designed for sequential scans, while metastore is designed for random reads and updates. Hive metastore can be configured to work locally on a client's machine or as a remote service backed up by a relational database, such as MySQL or PostgreSQL. As a result, Hive provides the low latency access for the metastore objects. Moreover, Hive metastore can be used independently from Hive framework itself, and it is used by other tools in Hadoop ecosystem. Hive provides command line interface where you can use Hive Data Definition Language, or DDL for short, to explain how data is stored in HDFS. Feel free to define your own tables. Similar to other relational database management systems, you can define namespaces called databases. Created for your convenience it does not limit to query tables from different databases, unless you don't have access to them. Let us create our first table. Syntax is the following. Create table, table name, then comma-separated list of columns with types within braces. If you don't provide database name, then a default database will be used. I didn't say anything about relation to data in HDFS. Describe statement is our friend to find out these details. First query. Describe database and database name. Second query. Describe table extended or formatted and a table name. HDFS location in the output is the place where actual table data is stored by default. You can provide HDFS location during database or table creation in the following way. Use clause is used to specify database name you are working on. Have you ever built a table schema against the existing dataset? Let me show you how simple it is. Here is a tabular data where the first column is a string, the second column is a string, and the last column is a numeric field. All fields are separated by tab character. If you create a table with the following DDL query and try to select data with HiveQL query, then you will see null in the second and the third columns. Think about it. What are we missing? Hadoop MapReduce uses a tab character as a key value separator, but it is not the case for Hive. There are a lot of textual data in HDFS datasets, and when you try to split arbitrary tabular dataset into columns, there is a high probability of a collision. That is why Hive developers chose Ctrl-A character from a set of ASCII control codes as a default field delimiter. Of course, there is a way to specify your own delimiters. You can do it with the following syntax. You need to drop the existing table if it already exists, which is true in our case. Then you create a new table with the same location and specify a tab character as a field separator. When you call select again, you see, strange, isn't it? Let us take a look what you have in HDFS folder. It's empty. I hope you will not repeat the same mistake on a production Hadoop cluster. Let me detour from our task to give you a brief overview of table types in Hive. Hive tables can be managed or external. Managed is a default option. If you create a managed table, then Hive is responsible to manage data in HDFS. So if you drop a table, then Hive will remove table metadata and will remove data in HDFS. But if you use an external table, then data in HDFS will be left unchanged. Drop statement will only remove table metadata. In addition to managed or external tables, there are temporary ones. So it will be automatically removed after Hive session is closed. Good things. I backed up this data, so I can restore it in HDFS. To prevent our mistake from happening in future, I am now creating this table as an external one. When you spawn select query, you see all three columns separated as expected. Row format is used to explain how to serialize Hive row objects into bytes to store in HDFS and deserialize from bytes back into Hive row objects. There are several extra options you can control. Collection item delimiter, Ctrl-B, map key value delimiter, Ctrl-C, line delimiter, and special characters for escaping and null value. Lines are delimited by /n by default, which is natural. For collection and map items, you can raise a question, where and how are they used? You could have mentioned that I used string type for the first two columns in our dataset and int type for the last column. But there are way more types. They are primitive and complex types. There are numeric primitive types ranging from 1 to 8 bytes in size, fixed and variable length string types, auxiliary boolean, decimal, and date types. Complex types are containers that permit arbitrary numbers of nesting. They are arrays, maps, and structs. And this is exactly where row format collection and map items delimiters are used. On the slide, you can see table definition and a few rows. Reading from left to right, you can understand how Hive deserializes bytes into objects. For instance, first field before the field delimiter Ctrl-A is a name of a person, and it is a string. The second field is float, and it is a person's salary. The next field is an array, and you see how array items, or more precisely collection items, are separated by Ctrl-B. One field further, there is a map. Key value pairs are separated by Ctrl-B, and Ctrl-C separates keys from values. Struct is essentially a named fixed size array, so it is stored in binary format the same way as array, but can be accessed in a more convenient way by the attribute name. In addition to a row format clause, you can also define a container type for rows or file storage format. File storage format can be row and column oriented. They can be in plain and in binary forms. Column-oriented formats usually have better compression. You will learn more about it in upcoming lessons. From syntax point of view, you should have stored as clause. Default storage format is text file, which is a plain text. After you have dealt with simple DDL queries, let us take a bigger picture back. From users' interfaces point of view, we have covered CLI API. But it is not the only way to work with Hive. Hive provides a number of services or APIs. There are common JDBC connectors to work from Java applications, ODBC connectors to work from BI applications, and Thrift API that is supported by almost any programming language. There is not much change in Hive functionality provided. That is why we will focus on CLI API in our lessons. Still guessing what this video was about? Let me show what you can do now. You can create databases and tables on top of existing datasets in HDFS, that is, configure Hive metastore. You can list different options to access Hive service. You can explain where Hive stores data and metadata. You can list primitive and complex Hive data types and explain how complex types are stored. Therefore, you should be able to translate manually binary stream of records into objects according to table definition or schema. More on Hive DDL you can find on official website. Missed me? I'm going to close the loop on Hive basic skills. This video is about DML, or Data Manipulation Language. Now you have experience of creating tables on top of existing data in HDFS with Hive DDL. You have also seen how to execute simple HiveQL queries without investigating how it works under the hood. In this video, you will be moving data in and out and inspect HiveQL queries a little bit further. First, if you have data in HDFS folder, then you can move it into Hive warehouse location with the following DML query. I intentionally call it data moving. Hive, unlike traditional relational databases, supports schema on read strategy. If you have a schema on write database, then all the data that you try to load into the database will be automatically validated to fit the table schema. On the other hand, this statement holds true when you write into a Hive table with the help of SQL query. On the other hand, Hive in its turn does not validate the data during the loading procedure, which you see in the slide. Consequently, it will throw exception during the data reading if your data is not aligned with a table schema. That is why it is called schema on read. If you move the data into Hive table, then it is your responsibility to align the data. In addition to moving data from one HDFS folder to another, you can load data into Hive table from a local file system. You only need to add a statement local and provide a path in a local file system. By default, data that you move into Hive warehouse location is added into existing files in HDFS folder. If there are files with the same names, then they will be overwritten. If you want to truncate HDFS folder content during this tape to make sure there are no any obsolete pieces of data, then you can add a statement overwrite. The other way around, you can export the data into a local or HDFS folder with the help of HiveQL queries. Handy Hive functionality that differentiates it from traditional relational databases is a multiple insert statement. By querying one table, Hive can optimize the execution plan in a way where it reads HDFS data once and do in-memory calculations for different select statements in parallel. You can create and populate one Hive tables with the help of the others. And from my personal experience, it is the most common workflow. You are familiar with insert or write table statement. The only change is that you don't move the data. You generate it from other Hive tables with HiveQL query. To make a new table, you can use a special construction, create table as select. Due to its popularity, it has got a special acronym, CTAS. You can have an arbitrary complex HiveQL query and save the outcome in a Hive table for future processing or analysis. So, you know all the basic components of Hive warehouse solution. They are Hive metastore, data definition language, data manipulation language, and query language. I bet you wonder how it works on top of MapReduce execution layer. In the first videos, you saw the following SQL-like HiveQL statements. I can't make you wait any longer. Let us go through them one by one. In select from statement, you only choose a subset of existing columns. So you will be able to do it within a map phase. Where statement, again, is applicable during data reading. So it is a map phase. Group by is implemented by Hadoop MapReduce framework within shuffle and sort phase. You can control it with the help of partitioner. Consequently, having is used on a reduce phase. We had intensive discussion about joins in the first course, and we have touched upon this question during this lesson. There are map side and reduce side joins. Therefore, it can be calculated during map or reduce phases. Order by statement is tricky. You rarely need to order the whole distributed dataset. That is why Hive developers provide you with a statement sort by. Sort by guarantees sorting within each file in HDFS folder, which is related to a particular reduce worker. Therefore, you can have an arbitrary number of reducers and a high level of parallelism. Order by guarantees total ordering and therefore is much more expensive. So please use it with care. Want to get detailed execution plan for your query? Prefix it with the explain statement. In the output, you will see how your query is parsed into abstract syntax tree, how many stages you have and what is the connection between them, and most importantly, you will see detailed information about each stage. So you should be able to figure out what will exactly happen during execution and where you will have map or reduce phases. Let me finalize our present outcomes. You know what DML stands for and how to move data from and into Hive warehouse. You can populate existing tables and you can create a new Hive table on the fly with the help of CTAS approach. You can explain where map or reduce phase is used for an arbitrary HiveQL query. Moreover, you can get a detailed execution plan for any HiveQL query. Feel free to use official documentation when you are doing your homeworks. Hello, I have good news for you. You haven't completed the course yet, meaning there is still a lot to learn. Learn how regular expressions can be used to read data and extract useful information from fields, how to extend Hive functionality with streaming scripts, and finally, how to use window functions, which are also known as analytic functions. Let me start with regular expressions. Unfamiliar with it? Feel free to watch the optional video. In this video, I will be using only basics of regular expressions. More elaborative examples you will be able to construct by yourself later on. I'm sure you still remember examples with Apache server log from the previous lesson. As you can see, it is not a simple tab-separated format. There are square brackets and double quotes to escape the whole columns. How can you create Hive table schema for it? If you use any whitespace character for a field separator, then you will parse correctly neither a date nor other multi-word attributes, such as HTTP request or user agent. As you could have already guessed, regular expressions come into play. Our row format is not a collection of delimited items. Therefore, I have specified row format as SERD, S-E-R-D-E, and provided Java class name to process it. SERD is a shortcut for serialization and deserialization library. If SERD has configuration options, then they can be defined with the help of SERD properties in the way you see on the screen. For regex SERD, you have to provide regular expression groups that correspond to table columns. I am not going to dive deep into details as there is a special video about regular expressions, but skimming through this to make sure that we are on the same wavelengths might be a good idea. We start regular expression with caret symbol, which means start of a string. The first field is IP, and it is a string without any space characters. There are two backslash symbols. One extra backslash is used to escape the other. Parentheses specify a group. Each group is related to one table column. Backslash capital S means that you extract known whitespace character. Asterisk means that there can be arbitrary number of characters, even 0. There are 3 similar columns, and then you see a regular expression group for a date. Date is written in square brackets, so I specify square brackets around this group. As a square bracket is a special character in regular expression language, I have to escape it by using backslash characters. Finally, a regular expression for a date would be a collection of characters except closing square bracket. Similar story with the next field. You are interested in a string within double quotes. Good thing you don't need to escape them with backslashes, as you do with square brackets. In the group, you expect arbitrary length sequence of characters till the closing double quote. Please bear in mind that regular expressions in regex SERD should match the whole input string. That is why you see dot asterisk, which means arbitrary number of arbitrary symbols, and a $sign, which is used to specify the end of a string. Another point, please use regex SERD class from a Java package that you see on the slide. At the time of shooting this video, it is the latest implementation of regular expression SERD, which supports different data types. For example, in previous version of regex SERD, it was only possible to have string columns. So you have to cast them to appropriate data types during requests. Here you see that I could specify numeric type for status code. By the way, how did people solve this problem with casts previously? To be honest, it is not really convenient to cast a column data type each time you need to work with it. And it is not really space cost effective to create another table from existing one just to curse types. For this purpose, you can use views. View is a read-only table that is only stored as meta-information and generated on the fly when necessary. Let us create a view on top of just created Apache log table and parse a year from a request datetime. Syntax is the following: create view, view name. Then a list of columns without data types. Data types will be extracted automatically from select query and as select statement to populate this view. You can add all the necessary casts to this select statement, so Hive will automatically detect the corresponding column data types for the view. It is easy enough. That is why I have added handy regexp extract functionality to expand your analytical horizon. Regexp extract Hive function can be used to extract the necessary information from other fields. You need to provide input data, regular expression pattern, and group index identifying parentheses in the regular expression. If you need to learn more on this, please take a look at regular expression optional video. After you have created this view, it should be visible in the list of database tables. To get a detailed information about this view, you can use the same semantics as with tables. For example, take a look at the output of show create table. When you have a HiveQL query to process data with views, Hive automatically will optimize the execution plan for us. For example, consider a pipeline where you read data from HDFS file split, parse it into columns, cast into appropriate types or extract the necessary piece of information, then filter records according to thumb rule in where clause. And all of it happens within a map phase. Amazing, isn't it? Though there are several limitations. There is no opportunity to write into a view. You will likely spend extra CPU cycles to construct a view instead of reading it from a storage, but some optimization exists. For instance, regexp extract can be evaluated at the time of reading data from HDFS without running MapReduce job. View schema reflects connection to tables or other views at the time of writing. If corresponding tables or views are updated, then this view could become invalid, and you will see errors only at the time of running HiveQL query. Summing up, after watching this video, you should be able to create Hive table schema on top of Apache logs in HDFS with the help of regexp crd Java library. You should be able to list benefits and limitations of Hive views, so you will know where to use and not to use them. Hello! This video is supposed to be a short introduction into regular expressions. Of course, you will not be a professional regular expression writer after watching it, but you will get all the necessary knowledge to complete this course. There are quite a number of websites that you can use to play with regular expressions online. They usually provide the following interface: a field where you put your regular expression, a field where you insert some text to look for matches, and an output field where you see information about found regular expressions matches in the text. If you don't have access to the internet, no worries. You can always use Python on your laptop. Let me show you how to do it. First, you need to import standard Python library, RE, which is a shortcut for regular expression. Then you can use search or match. Match functionality is used to find matches from the start of a string, whereas search is used to scan through the provided string to find the first match, not mandatory at the beginning of the string. Surely, you would like a real-world application to see the difference, just like e-commerce website. So you've decided to provide functionality to find good products automatically and show them to users on a special page. Each product on your website has a description and users' comments or any other type of feedback. You got an idea. If you find a word good in a product textual data, then you label it as a good product. So let us take a closer look into the behavior of re.match and re.search. The first text is classified as good as expected by both re.match and re.search. The second text is not classified as good by re.match as it looks for matches at the beginning of the string, but is classified as good by re.search. The third example is not classified as good by any of them. If you need to ignore case for substring matches, then you should provide an extra flag. In Python, this flag is called re.ignoreCase. Here you can see green output with this flag in place. Substring matches for alphanumeric characters sound long and complicated, but I bet they will be easy enough for you. I'm going to add complexities little by little. You implemented good products page and later on decided to improve this functionality. If you have a word nice in a document, then this document should be also classified as good. Regular expressions provide an opportunity to define this type of rules too. Open bracket, good, pipe, nice, closing bracket, matches good or nice. By the way, parentheses have a special meaning in a regular expression language. Everything inside brackets is called capture group. It can be used to retrieve the content of match later on. So you will know if a provided text has a match with a word good or nice. In Python, you should use the following syntax. If you remove parentheses around good and nice, then you still will be able to extract matches substring, but you will not be able to get it with groups. Sounds counterintuitive. Why do you need to have parentheses at all? Imagine that some users have found out that by adding good or nice word to a description, their products will be classified better or rank higher on our website during searches, or at least show up on a good product special web page. To prevent that, we have decided to add robustness to our algorithm and mark products as good only if they have in description really good or really nice. You can do it with the help of the following regular expression. Really good, pipe, really nice. But it would be better to use groups to reduce repetitions and a room for errors such as mistype. In this case, groups will match the whole substring, really nice, when groups will locate only capturing groups, word nice in this case. If you only need to use parentheses to reduce verbosity of matches, then you can use non-capturing groups. You should prefix matching group with question mark and colon. See example on the slide. At some point of server's evolution, we got an idea. If you have a positive adjective such as good or nice, what will be the next word in a description or user's comment? Maybe a customer is writing about good weather, or maybe he or she is writing about selling item. Let us extract the next word in the document for further analysis. Square brackets in regular expressions are used to specify a set of characters. For example, you can enumerate letters from A to G, or enumerate digits from 1 to 5, or you can even provide an arbitrary set of letters and digits. More handy way to do the same is to use ranges. See the syntax on the screen. Of course, it will only match one character, but you most likely want to match a sequence of characters. For this case, you can use the so-called quantifiers. You can match an arbitrary number of specified characters if you use asterisk. Asterisk can be used to match empty sequences, which is an edge case. If you want to make sure that you will match at least one character, then you should use plus sign instead. Question mark is used to specify optional group of characters. More granular size control matches are possible with curly braces. Consider the following example. If a person says it is way better or way better, the second option is not a formal language, but provides an insight that a person has more positive opinion about something compared to the first scenario. Unless there are 20 of A characters, which is more likely to be an error or a spam, you can expect from M to N characters with the following syntax. If you don't provide the first boundary, then the minimum size is considered a zero length. If you don't provide the second boundary, then the maximum size is infinite. If you need to match exactly K characters, consider phone number patterns that you see on the screen, then you should simply specify this number within curly brackets, without any extra commas compared to the previous examples. Time passes and regular expressions users and developers get tired of specifying all possible ranges for alphanumeric characters and their different combinations. That is why people have invented meta characters. The most common of them are \d, which matches any digit, \w, which matches any alphanumeric character including digits, and \s, which matches any white-spaced character. Sometimes you need to specify any character except a certain set of characters. You can use it with the following syntax: open square bracket, caret, set of characters to exclude, and closing square bracket. And of course, there are commonly used meta characters such as \D, which excludes all digit characters, \W, which excludes all alphanumeric characters, and \S, which excludes all white-spaced characters. There is way more to learn, but let me close the loop on regex basic skills. I'm going to show you 3 more special symbols. The first one is dot character. You can match with it any symbol. I mean any. So be really careful with it. For instance, in the slide you see an example how we delete unwanted files by mistake. If you need to escape dot character, then you can do it with \, which works for any other special character, including parentheses, different types of brackets, meta characters, and so on. The second special must-know special character is a caret symbol, which is used to specify the beginning of a string. Even with re.search, you are looking for matches at the beginning of the string. The third one is a $, which is normally used along with a caret symbol on the other side of a string. It is used to indicate the end of a string. Now, you can write simple regular expressions and validate matches in Python. You can use capturing and non-capturing groups and can explain difference between them. You can use special meta characters to find matches at the beginning, in the middle, and at the end of a string. You know how to use .meta character and escape it to prevent problems. You can define a set of characters to match a substring and can control the size of this match. More about regular expressions in Python you can read on official website. There are websites where you can learn and practice regular expressions online, and you can easily find them in the internet. I have provided a few links for your convenience. Hello! You have already seen quite a number of examples of HiveQL queries, so you know how to create a table schema on top of data in HDFS. You know how to move data in and out Hive table. You know how and where to use regular expressions. The only left piece: practice, practice, and practice. During this video, I will present you Hive functions that are most commonly used for analytical purposes. Hive official website classifies all functions into built-in operators such as arithmetic and logical operators, built-in and custom user-defined functions or UDFs. Examples are string and date manipulation functions. Built-in and custom user-defined aggregate functions or UDAFs. Examples are sum, average, minimum, and maximum. It is only possible to use on a reducer. Built-in and custom user-defined table generating functions or UDTFs, the functionality that people are usually unaware of. If you have a collection of items in one column, then with the help of UDTF, you can expand it into a collection of rows with one item per row. Real-world scenario is the following. You have staff Hive table. One column is a name of a manager and the second is a list of direct reports. You have another table with information about employees. When you need to join these two tables to find emails of all subordinates for all the managers, you have to use table generating functions to expand the list of direct reports. As usual, you will go from simple to complex functions, from operators and UDFs into UDAFs and UDTFs. There are around 200 built-in functions. you can list them with show function request. You can get description for each function using describe function statement. If you wish to get usage examples, then you can easily do it with describe function extended statement. For instance, see the output for a simple numerical UDF function. UDF functions are meant to be applied per row, and they generate exactly one value. If you have user agent string and you would like to extract client's browser information, then you should use Hive string functions, which are also UDFS. The rule is simple. When you have one-to-one matching from an input row to an output row, then it will be UDF. Of course, you can combine arbitrary number of UDFs in one request, and it will be evaluated during map phase. UDF functions will not cover all our needs. Consider a popular website that requires hardware to work on. Definitely, there will be uneven workload during the day. Therefore, you can plan hardware resources beforehand to optimize our costs. Any ideas how to calculate the workload using UDF functions? Right you are. You can extract an hour from a date from service logs. It is an UDF functionality. But when you need to aggregate all of this data per hour, UDAF functions come into play. The rule of thumb is simple. The input of UDAF is a collection of rows. The output is only one row. So far, you have seen one-to-one matching UDF functions. You have also seen many-to-one UDAF functions. What is left? Of course, many-to-many and one-to-many functions. Many-to-many analytics functions you will consider in upcoming videos. One-to-many functions are called UDTF functions. Despite the name, there are not so many of them. But you can easily extend Hive functionality by writing your own functions on Java language, or by downloading them in jar format from available resources. Each company has its own services and data processing pipelines. That is why it is common for companies to support their own collections of user-defined functions. It is quite likely that you will support your company library. Therefore, you need to know how to work with them. If you define your own function, then you should compile it into a Java jar and make it accessible on workers during runtime. How to reach that? You can easily achieve this with the help of a distributed cache. Don't remember the details? Feel free to jog your memory by revisiting the first course of this specialization. As soon as you have this library available on workers, you can define a temporary function by Java resource identifier and use it as any other built-in functions. In addition to temporary functions, you can define permanent functions. They are attached to Hive metastore. If these functions become obsolete, you can easily remove them with the help of drop function statement. Just one more comment. While UDFs are used on a map phase and UDAFs are used on a reduce phase, UDTFs can be used in both scenarios. We detour a little bit from a discussion of UDTFs. Take a look at this example. How can you join array items from the first table with description attributes from another? First, you can use UDTF explode to flatten our array into a column. Then you can write a simple join HiveQL query to match items with their attributes. I intentionally used only one column in the first table. UDTF functions limit the usage of select statements. You cannot combine arbitrary projection operations with UDTF functions. In case you need to do it, then you have to use lateral view statement. From my personal point of view, it has a little bit awkward syntax, but you will get used to it with practice. Take a look at an example of its usage on the screen. As a reminder, you can use explain statement to get detailed execution plan. As you can see from query execution plan, lateral view performs internal join of UDTF output with selected columns. Summing up, after watching this video, you can list 3 types of user-defined functions, explain difference between them and their usage patterns from MapReduce perspective. You also know how to get function documentation and usage examples directly in Hive session. You know how to combine UDTF function with projection operation. Finally, if you have your own user-defined functions, you can configure a Hive session to support these operations during write time. As usual, see official website for detailed documentation on these topics. Hello! In the previous videos, I told that you can easily extend Hive functionality by writing your own user-defined functions in Java. Courses of this specialization do not require Java skills. So let me walk you through the topic of extending of Hive functionality with the help of Python programming language. We are going to talk about Hive streaming. Hive works on top of Hadoop MapReduce framework. That is why it has all the benefits of MapReduce. If you write MapReduce streaming scripts in Bash or Python, then you can reuse them in Hive. Take a look at how to transform data by streaming scripts in Hive. Select transform statement is used for such purpose. The syntax of transform is the following: transform and a list of columns to process, using and a streaming script, optional as clause with a list of output fields. Output of streaming script would always be a string. That is why there are several options to specify output fields and their types. For instance, you can specify data types within parentheses along with field names. More examples you can find on the official website. Another handy functionality is that the quantity of output columns defined in Hive should not necessarily match the quantity of output fields from a streaming script. If you specified 2 columns in HiveQL query and you have only one field emitted by a streaming script, then the second column will be empty. To be precise, the value of this column will be null. On the other hand, if you specify 2 fields in HiveQL query, but you have 3 or more fields from a streaming script, then all columns after the second one will be truncated. As in Hadoop MapReduce, streaming scripts are not evaluated per row basis. It will be too slow to spawn a subprocess for each line. Therefore, a streaming script consumes the whole stream of records. How do you differentiate between map and reduce streaming scripts in this case? Honestly, there is no difference from transform syntax point of view. But there is a way to persuade Hive to execute some scripts during a map phase and others during a reduce phase. I bet you remember how to solve word count problem with streaming scripts. During the map phase, you take a line of input and emit pairs, word and the amount of times you have seen this word within the line. During the reduce phase, you take pairs sorted by word, accumulate word counts and emit the final statistics. For simplicity, I call scripts mapper.py and reducer.py. The magic clause to execute reducer.py in a proper way is a distribute by clause. Distribute by is essentially an implementation of a partitioner. You can partition or distribute by any set of columns and even use their simple operators and UDF functions. In addition to partitioning, you can request some sorting. All the complexities to perform a secondary sort will disappear. If you distribute and sort by the same fields, then I advise you to take a look at the cluster by statement. It is a shortcut for distribute and sort by. One more tip. I once spent the whole day debugging my applications. Believe me, you don't want to repeat my mistakes. Please don't use map and reduce HiveQL statements, or at least use them with care. They are essentially synonyms to transform statement, but they will not guarantee you that your streaming scripts will be executed during map or reduce phase. It is only controlled by distribute or cluster by clauses. Hive users who are starting to use streaming scripts to extend Hive functionality happen to forget adding scripts to a distributed cache. So scripts become available during execution. The semantics of this functionality is the following: add file and a file name. See working example of Hive streaming word count solution on the slide. There are add file statements, transform clauses, distribute and sort by to control execution on a reduced height. And everything is in one simple HiveQL query. The power of Hive is unleashed. Summing up, in this video, you have learned how to extend Hive functionality with the help of streaming scripts that you can write in Python. You have also learned how to control execution of mappers and reducers, which is important for streaming scripts. Hello! Have you ever worked in finance industry? I personally not, but I'm familiar with the concept of overdraft. Are you? It is a special loan your bank provides you with if your balance goes below zero. Large bank has millions of customers and a huge network of ATMs to withdraw cash. These ATMs are not always connected to the bank network to validate each transaction, but they still allow to withdraw some amount of money to support positive customer relationships. All transaction logs are aggregated later on in one central repository, which can be a distributed storage. How can you simply evaluate who and when goes below his or her limits? Naturally, you can do it in an old-fashioned way, by grouping data by customer ID and then executing your handcrafted streaming scripts. But there is a better way to do the same job with a built-in Hive functionality. There are partition table functions, or PTF for short. Due to their popularity in SQL languages, they have a number of other names, such as window or analytics functions. From the raw processing point of view, you have seen UDFs as one-to-one transformation functions. You have seen UDAFs as many-to-one functions. You have seen one-to-many UDTF functions. PTF functions are many-to-many functions that can spawn a chain of MapReduce jobs. First, you partition our dataset with the help of partitioner. On each partition, you apply a function for a rolling window. Size of a window can change dynamically during execution. For example, you can evaluate current balance since bank account open date. Therefore, you will be able to find all the episodes of overdraft. Take a look at the following examples to become familiar with window functions syntax. You have select statement, then you can have arbitrary number of attributes from our table, and here you can mix them with window functions. For instance, row number over a partition by statement. For a partitioner, you can use all available table columns. Row number window function is as simple as it sounds. It just enumerates each row within a partition. Not to be confused with rank and dense rank, I provided an output for both of them against the same dataset to highlight the difference between them. Both rank functions enumerate rows starting with rank 1. Dense rank enumerates rows without any gaps, such a way that equivalent rows will get the same rank. Simple rank function is somewhere between row number and dense rank. It enumerates rows in such a way that equivalent rows will get the same rank, but you will see gaps in the output to account a sequential number of a row within a partition. If you develop a leaderboard application, then you will be using rank window function. I intentionally showed examples with the same partition by clause. Hive can execute all of them within one MapReduce job. You can either write it the following way, or you can use more precise syntax by defining a window. For each window function, you will have a special object on a worker node to store results. Hive framework will iterate over the input rows and push them down to all window operators. Each operator will emit an output field. Then Hive framework gathers items from different operators into a row. But if you have different windows, then Hive framework will process a query in multiple MapReduce steps. One MapReduce stage will correspond to evaluation of functions over one of the window partitions. These window partitions will be evaluated sequentially, one by one, to unfold a list of attributes in a row during each iteration. Turn back to our original overdraft example. On the slide, you see a cumulative aggregation window function usage to track current balance for each customer. Please mention that I have added order by clause to HiveQL query to account for transaction ordering. Summing up, after watching this video, you can take a test on finance and get positive score. You know what overdraft stands for, and you know how to process account transaction logs with the help of window functions to look for overdrafts. You can explain the difference between row number, rank, and dense rank analytical functions, and how to process them simultaneously over the same window. You can provide at least 2 HiveQL queries to do the same job. You can explain how Hive executes PTF functions. in what condition there would be exactly one MapReduce stage and when there would be multiple of them. Occasionally, there are not so many resources to read on HiveQL PTF usage and implementation. There is an official website where there are a few useful examples, but if you would like to dive deep into this subject, then I suggest you to look first into window functions in relational databases. Welcome to the last lesson of this week. I hope you have been waiting for it, because during this lesson we will talk about Hive optimization techniques, which can be of great help to you as a big data engineer. Mostly they are about data organization. We are working with the same website as in the previous lessons, so no wonder it's still popular. We are constantly carrying out market research to provide users with the most relevant content. Recent data is more valuable to see current user needs. That is why we are most likely to use the following where statement in our HiveQL queries. What will Hive do to execute your query? What will it not do, you may ask? It will read all the data from HDFS, deserialize it into Java objects in memory, and after that, filter out unnecessary rows. Quite a waste of resources. In the first course, we had a discussion about the speed of hard drives, RAM, and network. And I bet you remember that if you can skip data reading from a disk, then you would better do it. Hive developers have invented a concept called data partitioning in HDFS. It is natural to store access logs in folders named by the date logs were generated. You can easily create a Hive table on top of this data and specify a special partition column. Voila! You are executing HiveQL query with the previously seen where statement, and Hive will not read unnecessary data into memory at all. You will save a lot of time and resources for tables with hundreds of partitions. Want to have more than one level of partitioning? You can have a nested folder structure. For instance, you can group your data in HDFS by year, by month, and then by day. Hive DDL query used for creating a table against it will look the way you see on the screen. And when you spawn HiveQL query, the framework will automatically determine folders to be read or skipped. Other way around, you can overwrite only a partition with insert overwrite statement, leaving the other part of the table intact. Generalization of the previous example is a dynamic partitioning. The value of a partition column can be undefined, or better to say dynamic. To populate a Hive table using the dynamic partitioning, you have to follow the you have to follow the following rules. The dynamic partition columns have to be specified after all other columns in the select statement. The order of dynamic partitions is important. They have to be specified in the same order in the select clause as in the partition clause. If you expect a huge amount of files and partitions to be generated, you would better increase Hive configuration parameters values for max dynamic partitions per node, overall max dynamic partitions, and max created files. To prevent users from mistakenly populating the Hive table by empty partitions, you can also set the flag year on empty partition to true. By the way, you can easily mix static and dynamic partitions. If you do this, all the previous rules have to be satisfied. One more rule. Dynamic partitions have to be specified after all static partitions in the partition clause. Thanks to the most patient viewers, we have to come to the more granular level of HDFS folder structure, which is a bucket. If you take a look inside any HDFS folder, you usually see not one file, but a number of them. Hive framework calls them buckets, and you can define how many buckets should be in each partitioned folder, how data is distributed over these files. Moreover, you will be able to specify how data is sorted. Reasonable question: how can all this metadata help us to optimize execution of HiveQL queries? Think about it. Why is it so important to know that your data, for example, is distributed over 200 files by a hash of a user ID? You definitely remember the business use case example from our first lesson, where you extracted the most popular regions users query our website from. Does it make sense to process all our logs to answer the question? Can you process 50% of our logs, or maybe even 25% of the data and get the correct answer? The answer to this question will be, in most cases, you can. This technique is called sampling. This term comes from statistics, and if you are unfamiliar with it, Wikipedia might be of great help. Together with it, there are a lot of freely available statistical books and online courses. So if you are interested, you can learn it at your own time and pace. But relax, this knowledge is not mandatory to complete this course. From practical point of view, when you need to read 25% of the data, then you need to read 50 files out of 200. Did you get the point? In this case, you don't even read 75% of the data from HDFS to execute HiveQL query to answer the question. The syntax of sampling operation you see on the screen. What will happen if you have a table with 3 buckets and you need to sample only half of the bucket? In this case, you read only one file and filter necessary rows by corresponding hash value. As you can see, the quantity of buckets in a table is a trade-off between name node RAM usage and possible optimizations during Hive query executions. What is most appropriate for your organization is defined by your data usage patterns and hardware limitations. Hive follows schema on read paradigm, so it is your responsibility to align data when you write into a Hive table with buckets configured. You have to set corresponding quantity of reducers, distribute data by bucket columns, and sort data if necessary. Watch out for making a stupid mistake here. If any of these parameters are wrong or outdated, they would be difficult to spot. Having a gut feeling that there is something seriously wrong? Relax. I'm here to take all your troubles away. Be at ease to use a special flag, Hive enforce bucketing. If this flag is set to true, then Hive framework adds the necessary MapReduce stages to distribute and sort data automatically. Do you have any ideas how we can use the information about data being sorted? This information is used to optimize several types of queries. Suppose you have access logs sorted by user ID. Word count problem to calculate the number of occurrences of each user ID can be solved within map phase only, without calling shuffle and sort and reduce phases. So, if you find yourself frequently clustering data by a fixed set of columns, then an intermediate Hive table with configured buckets can save you a lot of resources. A brief summary of this video is the following. By acquiring this knowledge, you will be able to use partitioning to dramatically increase the speed of data processing, use buckets to optimize the execution of sampling queries, read from and write into partitioned, bucketed, and sorted Hive tables. As usual, more on these topics are available on the official website. Welcome back. During this video, we will continue discussing the topic how to utilize meta information. In the previous course, you got a detailed overview of how to do map side and reduce side joins, and how to work with data skew in Hadoop MapReduce. Now, get on board to take a look at the functionality Hive provides you to complete similar tasks. When you have several Hive tables to join, the default MapReduce implementation is a reduce side join, but tables meta information can help Hive framework to transform reduce side join into an optimized version of map side join, such as plain map side join, bucket join, and sort merge bucket join. If you have a small table according to Hive session definition, then Hive automatically tries to convert any found reduced side joins into optimized ones. Small is defined by Hive configuration parameters, such as row numbers and size in bytes. Having solved this problem with Hadoop MapReduce, you manually put a small table into a distributed cache. Hive framework is doing similar work. First, it downloads a small table into a client machine. Second, it builds a hash table in memory for join keys. And last, it uploads the generated hash table into a distributed cache. MapTask in this case loads the hash table into a memory from the local disk and uses it to match join keys while streaming a big table. No reduced tasks are involved in this process. Operating moderate-sized tables, you can't execute simple map side join, but there is a room for improvement. Tables bucketed and joined by the same set of columns can benefit from bucket map side join. Without loss of generality, let us consider join of two tables by one column. The simplest case if two tables have the same amount of buckets. Each mapper processing a file split from a big table retrieves only the corresponding bucket of a small table to complete the join task. If there is a different number of buckets in tables, then you should remember the following rule of thumb. Data in a bucket is defined by a hash of column or a set of columns, and then divided by the number of buckets in a table. So, having 2 buckets in one table and 4 buckets in another one, you can easily find out that the first bucket from a table 1 will correspond to buckets 1 and 3 in the second table. Having 2 buckets in a table 1 and 10 buckets in a table 2, the first bucket in the table 1 will correspond to odd buckets in the table 2. But having 3 buckets in table 1 and 5 buckets in table 2, you have to read all the data from other table to perform a join. That is why I recommend you to always use a power of 2 as a number of buckets in tables. Even if you have a different number of buckets in tables, you will still be able to benefit from bucket map side join. In comparison to other power-based systems, the power of 2 provides the best possible name-node RAM utilization. If a bucket has grown to a size that you are no longer able to use in optimized versions of joins, then you can split buckets. If you use the power of 10, then you will increase name-node RAM usage for this table by a factor of 10. Optimizations recognize no limits. Do you know how you can use information about data sorting? What is the biggest limitation of bucket map side join? You have to read buckets into memory. But is it really vital when you have data sorted by a join key? Exactly. You have already seen this example in the first course, when we were talking about algorithm called external sorting. External sorting is based on a merge sort algorithm, where you read continuous chunks of data only when necessary. Similarly, sort merge bucket join will read into memory only the items for a particular key, perform a join, output generated pairs, free up the memory, and move to the next key. At the time of shooting this video, it is by far the most efficient type of joins in Hive. To make it work automatically, you have to supply just a few flags. Now you know why it is so important to properly configure data layout. With the help of bucket configuration in Hive tables, you can execute bucket and sort merge bucket joins and explain how they work under the hood. Hello! We continue our investigation of Hive DDL peculiarities. In this video, you dive deeper into the subject of data skew. Data skew is a natural property of real-world applications. When you analyze website access logs, you expect to see far more data from more populated regions. To be even more realistic, you can expect 80% of website hits by known authorized users. Consequently, data aggregation by skewed keys will be a real bottleneck. One of the strategies that was shown to you in the first course was to use 2 or more stages pipeline. We call this technique salting. Distribute by clause can be used in Hive to reproduce the same behavior. On the slide, you see the way to enforce Hive to partition data related to a skewed key over a set of reducers. Highlighted parameters can be used to configure the level of parallelism. There are many ways to implement salt in Hive. One of the approaches is to use universally unique identifier, also known as UUID. Good description of it you can find on Wikipedia. Personally, I can tell you that it is a random identifier which you can use to implement the salt algorithm. Here, I provided you with an example based on UUID implementation in Java language. See how easily you can call it from Hive with the help of the reflect UDF. Knowing this problem to be the common daily one for data scientists and data engineers, Hive developers have implemented a tool to overcome it. When creating a Hive table, you can provide your knowledge about skewed values. The syntax of such meta-information specification you see on the screen. Bear in mind that unlike partitioned columns, skewed keys have to be presented in the list of table columns. There are 2 ways of organizing your skewed dataset. The first option is called list bucketing. To enforce list bucketing, you have to specify stored as directory statement in a Hive table definition. If you supply this option, then the data for each skewed key will be stored in a separate folder. From optimization point of view, it is very similar to partitioning and bucketing. Hive will read skewed or non-skewed data only when necessary. When you write into a table with a data skew and subdirectories, you need not to forget set Hive mapret supports subdirectories flag to true. So Hive will be able to create all the necessary subfolders automatically. The second option is called skewed table. In this case, you don't need to create extra folders in HDFS. During execution, Hive automatically scans a skewed table several times. During the first run, it will extract and process all the skewed keys. During the second run, Hive framework will process other keys. Then it will merge the results from both runs. Which option to choose depends on your requirements or limitations. If you have hundreds of partition values and 100 of skewed keys, then list bucketing will generate millions of HDFS folders, which is likely an overkill. If you usually need to process skewed and unskewed keys independently, then list bucketing can be a good way to go. Summing up, if you are tired of solving the same problem in Hadoop MapReduce again and again, then Hive developers most likely have implemented this functionality for you. Skewed dataset problems are not exceptions. After watching this video, you can create and use tables with a data skew. You can list what types of tables with data skew exist and explain their pros and cons. If you need to find more information about available, supporting, and developing Hive features, you also know that the official website and Hive Jira Task Tracker are your friends. You can follow these links from the slide to get more examples. Hello! Having touched the subject of row and file formats, we spoke about row formats only. You likely remember such row formats as delimited or regex CRD. So now I'm going to uncover the power of file formats containers, and row-column-oriented file formats in particular. To the best of my knowledge, Facebook was one of the first companies who experimented with row-column-oriented files. They published an article about record columnar file formats in 2011 named RCFile, a fast and space-efficient data placement structure in MapReduce-based warehouse systems. Later on, it went to public as an open-source project. It was designed for fast data loading. Already in 2011, Facebook generated more than 20 terabytes of data per day. Fast query processing. Data stored in Facebook Warehouse was simultaneously processed by concurrent users. Highly efficient storage space utilization. Quite an obvious requirement, if you ask me. Strong adaptivity to highly dynamic workload patterns. In Facebook, they did not find any regular data processing patterns. There was the majority of unpredictable ad hoc queries. RCFile was widely adopted by Hive and Peek in Facebook and Yahoo. So how did they manage to achieve all of these goals? All genius ideas are really simple, and this one is not an exception. The logical table is divided into row splits. And then, instead of storing row split sequentially reading from left to right and from top to bottom, you store your data by columns, in other words, reading from top to bottom, from left to right. You may ask, what is different? From user's perspective point of view, nothing. But from the framework optimization point of view, you have found the holy grail. Take a look at the following example. You have columns which are numeric, strings, or dates. Let me structure them column by column for you. If you implemented a framework to store this data, how would you decrease disk space requirements taking into consideration the aforementioned data layout? For example, you can use lossless compression techniques. Compression applied to row-oriented file formats does not provide so much benefit compared to compressed column-oriented file formats, because you can use different compression algorithms to different data types. Consider datetimes. They are usually stored in the form of Unix timestamp. Unix timestamp is a number of seconds since the 1st January 1970. This date is an official starting point of Unix epoch. For example, the value of 1.5 billion Unix seconds is 14th of July 2017. If you store these dates in a plain string format, then each date consumes 10 bytes per date. If you store them in integer format, then each date consumes 4 bytes. The upper limit date in 4 bytes format is the beginning of 2038, so be careful with this representation. For storing timestamps, there is a better space-efficient way which is used in an optimized version of RCFile format. Have you heard anything about delta encoding? Instead of storing plain timestamps, you store the first value and all others are stored as delta values to the previous timestamp. How many bytes you need for delta encoding highly depends on your data, but usually 1 byte of data per value is enough. The more you know about your data, the better you can compress it. String data types are dictionary encoded, and other numeric values are run length encoded. I only highlighted the basic concept to give you an intuition. If you are curious to learn more on RCFile implementations details and compression algorithms, please follow the provided links. Turn back to our design goals. Fast query processing, yes. You can easily skip the whole columns if you don't need to read them. Efficient space storage utilization, definitely yes. You have seen how you can reduce storage space usage by almost a factor of magnitude. Fast data loading. According to Facebook experiments, RCFile requires extra 10% to group and compress records. But mostly you live in write-once, read-many paradigm in big data world. Speed up of query execution time dramatically outperforms shortcomings in data loading. Dynamic workload adaptivity. It was achieved by the next generation of RCFile format, which I encourage you to use nowadays. It is called ORC, ORC for short, which stands for Optimized Row Columnar File Format. It was a joint work of Facebook and Hortonworks. At the same time, Cloudera and Twitter developed Parquet file format pursuing similar goals. In Hive, you can use both of them. ORC file format also contains index information about minimum, maximum values in a column stripe. It will give you a power to skip the whole stripes of data during query analysis, so you don't need to read and decode this data. More about predicate pushdown you will learn during the last week of this course. ORC also contains information about count and sum, and therefore a bunch of aggregate queries can be highly optimized for execution. And there are a lot more tiny tricks implemented to make your warehouse fast and efficient. So it's time to see how to use ORC files in practice. Here is the way to define a Hive table with ORC data file layout. You can provide configuration parameters via table properties statement. On the slide, I only provided a few of them. Hive table metadata, such as ORC file configuration, makes sense only for data reading and writing. It is already a significant improvement over the row-oriented file formats. But Hive queries usually consist of number of MapReduce jobs. Therefore, you have to take care of disk I/O usage between MapReduce stages. Compression in between is controlled by the following Hive configuration parameters. The first flag is used to set intermediate compression. Then, if you use MapReduce execution engine, you can configure a compression between map and reduce with provided flags. Other execution engines supported by Hive are Apache Spark and Apache Tez. Most likely you will use them in production environment, so you know where to look for optimization options. In this video, you have learned what are the components to build efficient row-column oriented file format for big data applications without any regular workload patterns. You know how to use ORC and Parquet file formats in Hive tables. And please, don't forget about intermediate compression. Take my word for it. Data layout, including data partitioning, bucketing, and file format configuration, are essential components in Hadoop ecosystem. I remember the time I was working at Rambler and managed to reduce the time to run business-critical pipelines from days to hours, just with the help of proper data layout configuration. And I bet this knowledge will help you to optimize a lot of data processing pipelines in your career. Hi friends, in this video I'm going to show you how to submit your first Hive assignment. At the time of shooting this video, there is no possibility to run the Hive sandbox environment directly on Coursera resources. But I bet our research and development engineers will not make you waiting for a long time to have it available online for you. Meanwhile, let me walk you through how to run the Docker sandbox environment to prepare your first submission. First of all, you need to pull Docker container called Big Data Team Hive Course 2. This image is publicly available on Docker Hub. So you can do it simply by calling docker pull from CLI. As soon as it is available on your computer, you can run Docker container with the help of docker run CLI command. As you can see, I use the following flags: --rm and -it for removing container as soon as you kill application or close terminal. -p for the number of ports forwarding. For example, 8888 is used for Jupyter Notebook, 570 is used for the name node UI, and 8088 is used for Resource Manager. In the output the Jupyter Notebook is running at, you can open your favorite browser and open Jupyter Notebook at localhost 8888. If it works, I'm happy to congratulate you, because half of the complexities is done. If it's not, please follow the videos on Docker installation and request guidance on Coursera forums and on our Slack channel. As a last resort, you can subscribe for infrastructure updates to wait till the moment we announce the Coursera Sandbox environment available online without any local Docker installations. I hope everything is fine and you see the following page. Let's go to the folder called Demos. Here we are interested in the notebook with the suffix submission. I highly encourage you to read all the instructions before your submission. Let's pretend for a moment that I'm a lazy student. Run all the cells and make a submission to the grader. To make a submission you have to, firstly, make sure that you run all the cells in the notebook, because this is exactly what will grader do. Secondly, download this notebook as IPNB. Thirdly, open tool for relevant programming assignment on Coursera Learning page. In this case, it is Hive Demo Assignment Subnets. When you click the button, Coursera generates a unique submission ID and redirects to our web page. This unique ID is necessary to send the score for your submission back to Coursera. And that is why you are not able to make several submissions from graderbigdatateam.org without reopening page with the help of Open Tool button on Coursera. Let us make a submission with the saved notebook. First, we drag and drop our IPNB to this box. Second, we wait for grading feedback. While we wait, this IPNB is evaluated against the real multi-node Hadoop cluster. After some time you can see status done, but your score is 0. Do you know why? I know, because you pretend to be a lazy student, which I bet you are not. If at some point you need to share your submission with course mentors, please click Show Logs. And pay attention to the last line starting with Source Notebook. It is the physical location of your submission on the edge node of our infrastructure, and only mentors have access to it. Take a look at the semantic exception. Database doesn't exist. Let's move back to notebook and read instructions carefully. When you read this passage, you will understand what is going on during the execution on the Hadoop cluster and why do you need to comment this line for submission. We provided this example for you so you can create any database inside the Docker container. Let's comment this line, execute it, and make a new submission. You will see the following error if you try to submit this notebook directly on graderbigdatateam.org. If you don't understand why, please revisit the first part of this video. We have to go to Coursera page first and click Open Tool only after we refresh the page. So Coursera will be able to generate new unique submission ID. If you don't refresh the page, then you can see the following error. Wait for submission to be evaluated and finally see that score is 1. My warmest congratulations! Don't forget to kill the Docker container to free up resources on your computer. Overall, in this video, you have learned how to launch and kill the Docker sandbox environment, how to make Hive submission to the grader, why it is important to read instructions. Enjoy the course, practice your skills with programming assignments, have a good time, help others, and make friends in Slack. See you there!
Hello! In this video, you will get acquainted with a key element of Spark SQL, which is called a data frame. What is it? Why does it need a scheme? How is it related to RDD? How to create them and how to work with them? The answers of these questions you will find out in this video. Well, as I have said, the core element that you will work with in Spark SQL is called a data frame. But what is it? Well, when you are working with structured data, it can be represented as a set of tables, where each row is an individual record, for example, bank transaction, or a logged internet event, and each column is a property of that record: who visited the web page, when it was visited, what URL it has, etc. Tables in Spark SQL are represented by data frame objects, which allow you to access their data and process it. This solution was inspired by Pandas library. I hope you are familiar with it. Spark data frame is a distributed collection, reconciling distributed data sets. Actually, data frame is built on top of RDD. Each table's row is stored as a separate element of RDD. But what about columns? In which way does data frame works with them? Well, data frame also keeps additional property called schema that describes columns of its data. Let's see how it works. That's how you create a Spark session object just the way you had done it before. We were starting pure RDD API. Now we are reading textual data set from HDFS. Let's see how it actually works. You have a mapping table in this data set where each IP is associated with country and its country code. Fields are separated by commas and spaces. You can use such a table to determine user's country by its IP. You are able to split its rows by commas and get list of fields: IP, country code, and country name from each record. Now you will convert RDD into data frame explicitly. To do this, you should define a schema of data frame that which column it has. All IP, code, and country fields are textual, and our schema will look like this. You create the object of structure type for the schema and add fields with the names and types for it. All columns store textual data, so the type of each column will be string type. Now you can create data frame from RDD and schema. Here we go. Let's check if you have exactly the data frame you need. Printed representation of the new object shows us data frame with fields IP, code, and country. If you call show method, it will show you our first 3 rows and with their structures. RDD property gives us access to internal RDD, where actual data is stored. Let's take a look at what there is. As you see, data in data frame is stored as a set of row objects. Each of them contains the name of the column and its value. Also, you can check the schema of our data frame by print schema method. It will show us the list of columns with their types. Nullable property means that field could contain null if the value is missed. Here you can see 3 columns as planned. As I have said before, Spark data frame was inspired by Pandas data frame. And it's wonderful that you can transform Spark data frame to Pandas data frame and back again. Just call to pandas method of Spark DataFrame and you will receive pandas DataFrame object. But be careful. The whole data that is stored in your data frame will be collected into your driver. And if you try to convert 1 terabyte data set from Spark data frame to pandas data frame, your program will run out of memory and crash. If you need to convert pandas data frame into Spark one, you can call create data frame method or Spark session and pass your pandas object as an input param. Your local data frame will be distributed over Spark executors, and you will be able to process it by Spark. In this video, you have learned what is Spark RDD and how its schema looks like. And now you can create it from a simple RDD object and from pandas data frame. Hello! In this section, you will know why DataFrame API is called Spark SQL and how to process its data by SQL queries. Well, what can you do with Spark DataFrame object containing your data? Among the variety of operations that DataFrame allows us to do, I will show you a few basic examples. The first operation that you saw in the previous video was show. It's a quite useful method which allows you to look inside any data frame and check its content. I use it a lot in my daily work. Also, you can decide which columns you want to see by the select method, like omitting the country code column and as it's not interesting for you, and select only country and IP. Here is the result. Want to see any Russian IP addresses in the table? Well, filter this table by country name column using where statement. Let's add this condition to our pipeline. You will investigate API of the data frame in details during the next lesson. Now I want to focus your attention on the couple of things. Knowing that every method returns some new value, what values are returned by select and where method. To check it, let's rewrite our last occupation in this way and check the types of intermediate objects. The select method returns Spark data frame object with a new quantity of columns. Where also returns data frame object as well, whereas show method returns empty value. The data frame, like RDD, has transformations and actions. Transformations return new data frames, and actions return something else, and nothing. Select and where method are typical transformations, and show is a typical action that can be performed to your data frame. Using the time command of Jupyter Notebook to measure the execution type of each step, the result will be about 30 milliseconds. The second step, which is also a transformation, takes 15 milliseconds. And the third step takes about 200 milliseconds, which is 10 times longer than previous steps. Do you know why it's happened? As you remember from the Spark RDD lesson, all transformations of RDD are lazy. They are calculated on request, only when your code needs to make some final action with your data. For example, print it out. Until this moment, the data frame as well as RDD has been storing its lineage, where to get the data from and how to proceed it. So, when I told you that the data frame was the analog of SQL table, I was quite incorrect. More precise analog of data frame in SQL is a view, because both data frames and views don't keep data in fact, but calculate it on request. As you can process these data frames by SQL queries, let's see how you can do it. Firstly, you should create an SQL view associated with data frame. You can do it by the createTempView function. This view is called temporary because it exists only during the Spark session and will disappear right after it's finished. And now you can use the new view in our SQL queries. It can be done by Spark session SQL method. Just type your query and execute it. Oops, this query hasn't returned the final result to us. It just created a new data frame. Let's assign this data frame to a new variable and look what is on inside. Let's call it country HDF, for example. Let's check the result. Each result of the SQL query in Spark SQL is a data frame object, and you can deal with it as with any typical data frame. And every data frame can be converted into SQL view. I hope you understand the difference. And it can be used in the following queries. Now you know how to make simple operations with Spark data frame, convert them to SQL views, and execute SQL queries on them. Hi guys, my name is Pavel, and today we will talk about how to work with Hive in Spark SQL. If you are able to connect Spark SQL to Hive and use its tables in our data processing, then our capabilities will grow significantly. To connect to Hive, you should use Enable Hive Support option when you build your Spark session. Here you can see how it's done. There are two ways to check that Hive tables are available in our Spark session. First of them is the following. You can ask Spark to show databases by SQL query. Actually, this query is show database. Let's execute it. As you see, you have two databases in your Hive metastore. The default database exists by default, and all tables store there if nobody specifies a particular database. But somebody created the database web. It's also possible to check what is inside of it. You can list all the tables in any database by show tables in query. The database web contains the access log table. You worked a lot with it during the previous week. Another way to do this, to use a special catalog field of Spark session. The catalog contains methods that work with tables and databases. These databases will return us information about all the registered databases in Hive, and the list table could show you all the tables in 1 DB. The output of these functions is not so pretty as by SQL queries, but it contains the more information. For example, you can get the database name and description from its output. One more important difference is that the syntax error in SQL queries will be found on query execution, and in the list database function it will be found when you execute your script. The sooner you will find your error, the cheaper it will be to fix it. Now you are connected to Hive and check that the connection is successful. You can run queries on it. As you remember, the result of each query is data frame. Let's check that you have access to content of access log table. Yes, you have it. And what is more important, you can execute Spark SQL queries on Hive data. The Spark SQL implementation is almost fully compatible with Hive SQL, except some tricky cases. It means that you can take any Hive query, execute it on Spark SQL, and get exactly the same answer. I have one more question to you. What do you think about Spark SQL query execution? Is it a transformation or an action? Actually, it depends on query that you wrote. For example, the query like create table as select stores the result of your query into a new table and return an empty data frame. Such query will be executed as an action, and most of other query types are transformations. The Spark SQL optimizer makes a decision about what it will be. Now you can download any dataset from Hive into Spark SQL. Our next step is starting the process of exporting data frame into the Hive. Now let's return to the GeoIP data frame. It will be very useful if you keep it together with access log. Then you will be able to join them and determine the country of the event. Geographical information is essential in the web log analysis. To do this, you should create a temporary view as you did it before. If you check the web database again, you will find a new GeoIP view. The table will have a temporary flag that shows that this table is not permanent. Now you can create a permanent GeoIP table in web database by create table as select clause. If you verify tables of web database again, you will find a new GeoIP table that is permanent. It has no temporary flag. Finally, you can select a few rows from this table and ensure that it contains our geographical data. In this lesson, you have learned how to get connected to Hive, how to load and save data frames into the Hive. Hello! In previous video, you will learn how to write queries on Hive tables. You can use SQL queries to read data from a table and save it into a new one. Now you will extend your knowledge by learning more ways to read and write data from different sources. At this point, you can save the GeoIP data frame into the Hive by SQL query. To do this, you should create a view from our data frame and execute the create table as select query on it. After that, you will have a new temporary view with a new table in the web database. But this table creation is verified only when this query is executed, and it will be set if your program fails at the end of the data processing. You also can save data into Hive by the Spark API method. And in case of a syntax error, your program will fail at the very beginning, and this will save you a lot of time and nerves. Data frames have a special property, write, to save data into any place. You can save data into Hive table by saveTable as table method. Let's try this. Unfortunately, the save as table method fails. Let's check why. The table GeoIP already exists. You created it by the SQL query earlier. Let's save our data frame into a new table. Now it works, but what should you do if, for example, you have a new results that are more precise than the previous and you want to reread them? The result of the method save as table, in case data already exists, depends on the mode parameter. The default mode is error, and Spark throws an exception each time the data already exists in the source. If you want to clean up the previous results and rewrite new one, you can use the overwrite mode. And the append mode will add the data frame as a new rows into the existing data. Let's check the behavior of save as table in different modes. Firstly, you rewrite the existing table in the overwrite mode, and you check the number of rows in the table. Now you should append GeoIP data to the existing table. And check the number of rows again. As you can see, the number of rows in the table has doubled. The data frame write property allows us to store data frames not only to Hive, but in files as well. For example, we can save our tabular data into a file by save command. Spark creates GeoIP out folder in our homes directory and writes the data there. I suggest you to look what is on the inside. The first 3 rows taken from the files return us some kind of mess. But you can find elements of data there. Here is an IP address, for example. It means that data is stored in a binary format. By default, Spark works with binary Parquet files, which are designed to high performance reading and writing. If you want to store the data in a more human-readable form, you can save it in CSV format, for example. The data will be organized as a text. The columns in each row will be separated by commas. Another popular textual data format is JSON. You can store our data as JSON strings, and each row will contain columns, names, and values. This overhead helps us parsing the data in the table in advance. If you try to save a data frame in the folder that already exists, you will get an exception. Any ideas what should you do if you want to rewrite this table or append new data at the end? As with save as table, you can overwrite the output folder by setting mode equals overwrite, and the append mode will add the data to the existing one. Also, each data format has an explicit function to save into it. Parquet saves into Parquet files, CSV saves into CSV, JSON saves into JSON. You can choose which one is more convenient for you. Spark SQL allows to read data from folders and tables by Spark Session Read property. The Spark Session Read table will create a data frame from the whole table that was stored in a disk. And now you check its first rows. To read the folder with JSON objects, you can use the readJSON method. The columns read from JSON file will be permuted because the columns in JSON don't have any order. When you read the data from the CSV file by the readCSV command, it returns the right order of columns, but without the names of columns. you should provide a schema of the data frame as you did it when we creating the data frame manually. Now the columns are correct. And you can read data from the Parquet file as well. There are no issues with the names of the columns and order in them, because each of the saved Parquet file stores in its own schema. As you remember, each table in the Hive is saved in HDFS as a separate directory. So, save data in table and save data in file are pretty similar. But now I will show you something totally different, saving data into any external database. It's really awesome because it allows you to import and export data from anywhere in your company. Each relational database allows to read and write the data into it by a special JDBC protocol. JDBC means Java Database Connectivity. You should just download the jar file with a client library for this database and set a proper connection string. The connection string contains a type of database, its web address, the database name, the username, and the password. Now you can write your data frame into the external database by JDBC and read its data from a JDBC as a new data frame. It is very useful at the end of data processing, when you have created a report or machine learning prediction and should make it available from other business systems in your company. Now you can read and write data into the Hive by Spark API method. Can read and write data into directories as well as export and import data frames into external relational tables. Hello! By this moment, you have already got familiar with three ways of processing data on the Spark. Take our usual geographic data set. You can select columns and rows in it using the RDD API, DataFrame API, and SQL. So which one should you choose? Let's figure it out. As you already know, DataFrame and SQL are converted by the optimizer into the sequence of RDD transformation. At first sight, RDD and DataFrame should be executed in the same way. However, you write the RDD transformation on the Python. It will be executed on workers in a separate process that runs more slowly and has an overhead to receive and return data. And the DataFrame optimizer generates the code in the Scala language, which runs inside the Java virtual machine without any overhead. As a result, calculations are 2-3 times faster. Another advantage is that the optimizer can choose the optimal way to execute the code, to do filtering before or after the aggregation, to make a join using RDD join or via broadcast of a smaller table to nodes. In some cases, the processing speed can increase at times. Some skeptics will object to me. Pavel, what if we want to process data in some tricky way? After all, in RDD transformation, we can substitute any function, and in Spark SQL we can't. I will answer to them. Don't look for tricky ways to make your life more interesting. But actually you can. To do this, there is a special command, Spark session UDF register, which makes any of your functions available in your SQL code. We will talk about it later. Good. I think I have convinced you to prefer DataFrame to RDD. At this point, let's switch on the comparing DataFrame API to SQL. Here are two pieces of the code that do the same thing. One is written on the DataFrame API, the second in the SQL query. The code will be converted by optimizer SQL equally, and the performance will be the same. However, if you look closely, there are errors in the code. Can you see them? Here they are. And if you run this code, the example on the left will not start at all due to a compilation error. And the example on the right will be dropped at the time of the query call. The principle of good code development says, the sooner you will find an error, the easier and cheaper it will be to fix it. In the case of the DataFrame API, you will find it immediately and run the corrected code again. And in the case of SQL command, you will see the error only when the query is called. Imagine that is create table as select query. And program works for 2 hours and saves the results on a disk with this help of this query. Your results will be lost, and the mistake in it will cost you much more. I can give you an advice. If you already have the working code on the Hive, you can just use copy-paste and work with it. If you need to write processing from scratch, use the DataFrame API. Checking the code compilation will save you a lot of time and nerves. Hello, my name is Pavel. At this lesson, I will teach you to use projection and filtering. Imagine you have the structured data. I mean some kind of a table. For example, let's take the access log table. I hope you already fallen in love with it. In our case, it's not so big, but it could be much bigger. In my company, the access log table has 200 columns and 40 billion entries per day. To work it somehow, you need to select only the useful information from it. From the columns, you can select user's IP and URL and make data frame out of them. Also, you want to choose only the specific records that occurred before lunch, when the user was not very sleepy yet and where he served the pages with kittens. The selections of columns is called projection. The selection of rows is called filtering. You have already played with them at the last lesson, and I promise to tell you about it later. And now I will show you that I can keep my word. Let's create the data frame from table to be able to experiment with it. Firstly, the projection. Projection is what you did in SQL queries using the select and enumerate the columns. It was the first action that you did when studied SQL. To do this on data frame, you need to apply the special select method. Inside this function, you can point the columns that you need in the order you need. Please pay your attention to the fact that you have 2 ways to write this list of columns. The first way is to write their names in a text. The second is to list them as properties of your data frame, like this. Which one do you think is better? In fact, in the case of Python, the compiler will not fail if one of the field names contains an error. But if you develop your code in the IDE, like PyCharm, it could help you to find this error. I will be very thankful if you follow my advice. Please write a good code! When selecting the columns, you can also change their names. This makes the alias method at the column. Here I am changing the URL column name because in fact it is not a full URL but only a part of it. If you specify the name of the column with a text, you should convert the name into a special column object and then apply the alias method to it. There is a special function called that will help you to do this. I also advise you to give the column reasonable and understandable names. Imagine a table containing fields. Field 1, Field 2, unknown, and B1A2 ref CPM. This is the real column name from the table at my work, and I still don't know what is supposed to mean. It will be very difficult to work with such a table, and I am sure that you will forget the meaning of this name in half a year. Now let's move on to filtering. The fact is that you can select lines by the names from the table. They are not there. But you can choose them according to the conditions. For example, pick all the failed requests to your domain from the access log. In SQL, you specify your condition in the where clause, and it filters the rows that you need. For Spark data frame, the filtering can be applied by special method where and filter. They both do the same thing. So, filtering applied to the data frame will look like this. The condition can be written as a string or an expression. You can just copy the string expression from SQL query and it will work. But then you will not be immune to mistakes. The expression in the API is constructed the same way as a pandas data frame. And how can you filter data frame using complex conditions that contains several parts joined by and or, like this. Here you are filtering all the errors that happened with Android users. You can do this using an ampersand and a vertical bar instead. And in order for it to work correctly, the parts of expression must be bracketed. This is the old priority problem in Python. You will face the same problem when you use pandas. By the way, I have got something for fans of pandas. You can select columns and rows in the same way as in pandas data frame by specifying columns names or conditions in a square brackets. When you choose the filtering or projection, the data frame will understand by type of parameters received. Here is an example of filtering with square brackets. At this lesson, you have analyzed the ways of projection and filtration. Use them, and do not forget my advice how to write clean working code. Hello, my name is Pavel, and today we will talk about the functions that can be applied to data using the data frame. As you remember that working with SQL, you can apply functions to columns to get new results. Unlike the function which you use on a Python, SQL functions are applied not to a single value, but to all the values in the selected columns at once. It happens distributedly on all nodes of the cluster. There are three types of SQL functions. The first type, mapping functions. They are the functions that map one value from the source column into one value at the destination. Such functions are the majority. The second one is the so-called generating functions that transform each element into several ones. Actually, there is only one function of that type, but what a function that is. It's called explode and allows you to expand arrays into new rows. For sure, we will talk about it, but we will do it in all good time. And the third type of functions is aggregating functions. They are used when you need to create a new record from a group of existing ones. We will talk about them on the next video. All the functions you worked with in SQL are also available in the data frame. There are more than 100 of them, and I will not enumerate them. Otherwise, you might get bored and fall asleep. I will just show you a few examples of using them and give you a link to the documentation. Let's take the access log and apply some interesting functions to it. In the log, there is an interesting field, user agent. This is a line of information that a browser sent to a web browser about itself. The line itself has had a hard time. Long time ago, web service tried to send different web pages to different browsers and didn't support all of them. So, browsers had to pretend to be other browsers. I believe it will be interesting for you to analyze it. Let's create a data frame that points to the access log. You start from a simple one. For example, you measure the length of the text in the user agent field. All Spark functions are stored in the PySpark SQL functions package. So let's import it. You can apply function to the columns with the select method. You specify the columns and the functions that interest you and execute the query. The result turned out to be correct, but something went wrong with the name of the column. Set the new column name through the alias method and execute again. That's much better. Let's look at the URLs now. Clearly, something is missing in them. They miss the domain, since the web service often doesn't know in which domain it works. To be honest, that is an artificial log that doesn't belong to any real domain. So let's add the URLs to vk.com. That is a very popular social network in Russia. That can be done by concat. Heck! You failed. If you scroll the error message down to the end, you can see the reason. Spark is trying to find vk.com in the column table, and it fails. But you know that vk.com is just a line and not a column name. How to make this clear to Spark? The function lead will help us. It explicitly tells the analyzer that this is a string. Here is the syntax. As a result, you get pages of users which you can try to look through. Most of VK pages are restricted with privacy settings. Can you find any page with open content? Now let's analyze the user agent. To begin with, just choose the field to look closer. Now divide each line of the user agent into words using the split function. To make the columns name less scary, let's assign the name list to it. You can extract the words from the resulting list, referring to them by the indices, or separate words per line using the explode function. It could help us to find the users of Androids from the list. Wow, it turns out that Androids is a kind of a Linux. Did you know it? Also, explode is the first step of word count. You will do it when you disassemble the aggregation. As you know, the user agent, you can determine the type of operating system a person using for visiting the site. Let's write such a determinant. It can be implemented using the when function. All the user agents that contain Android substring belong to Android OS. Let's add this as our first condition. The default value can be set using the otherwise function. Let's check what it has happened. It is possible to add additional conditions into the when function. Let's filter all visits from Windows in access log. They all contain Windows in the user agent. You can do this by changing the when function. In your homework, you can explore this function and learn how to define other operating systems. In this video, you learn the types of SQL functions and how to apply them. Hello, my name is Pavel, and at this lesson you will learn how to analyze the data in tables using aggregation functions. Imagine that you have raw data, and I've already said there are billions and billions rows of access log at my work. And then a marketer comes to you and asks, which pages are the most visited? He or she wants to see a report like this. A technical director comes to you and asks, how does the load on our servers change over time? Should we buy more servers when he or she is receiving the chart, or like that? He or she can schedule the purchase of new servers or their selling. The development director comes to you and asks, what countries do visitors came from? Is it time to translate our site into a new language? To answer these questions, you need to analyze the data and build reports on it. To do this, you should learn how to aggregate the data sets. At this lesson, you will recall how aggregation looks in SQL. Learn how to aggregate in the data frame. You will get acquainted with aggregation functions. Also, you will learn to solve practical problems. Well, let's take the access log, make sure that it looks like you expect, and learn how to extract useful facts. All of you have already tried to write aggregational requests in SQL. Such SQL queries always contain group by with columns for grouping. In select, you can specify the columns by which the grouping is done and the aggregates from the other columns. If you try to add any other columns and will do not apply aggregation to it, the optimizer will throw you an error. You need to be careful here. In the same way, aggregation can be done using the DataFrame API. For this, you need to use two functions, groupBy and AGG. You can get the aggregation functions from the same package, PySpark SQL functions. You apply the grouping to the data frame, then you process the columns by the aggregate function you have chosen and select the first three values from them. Also, there is another approach in Panda style. You make the grouping and aggregation of it as before, but you pass a map with the instructions about what should you do with each column as an aggregation parameter. In my opinion, the method is inconvenient. After all, in the way you can count no more than 1 unit per column. For example, if you need to find the time of the first and the last visit for each visitor, you can do this with such query. AGG will apply only minimum or maximum to timestamp value. In general, it's inconvenient. So use the first method. Of course, you can aggregate not only one, but several columns as well. List the columns, get the result. Let's find HTTP error codes that appear at different pages in this way. In the SQL query, you need to add HTTP code to group by and select in the data frame transformation. Just add HTTP code to group by. As a result, the Spark for each pair URL HTTP code returns number of impressions they were. You can perform the aggregation not only to the columns, but also on the derived values obtained using the mapping functions. For example, you can construct statistics of the length of the URLs. How many different lengths of URLs were there in the log? It will look like this. You can even aggregate the values grouped by 0 columns. What result do you think will be done there? This is an aggregation of the whole table. In this example, you count the number of records that you have encountered in our log. You can remove the group by altogether. You will calculate the aggregate the entire table. It's just another form of the same query. What can you do with the aggregation of the columns? Actions can be derived into 3 groups. The aggregation function is applied to the certain list of values, which correspond to the special grouping condition. What can you do with it? Well, firstly, you can turn it into a real list and put it into a separate field. Count the length of the list or sum its elements up. You can select the unique elements and convert them to list using collect set. Count the numbers of unique elements or find their sum. And if you have a list and a good understanding of math, you can find the minimum value, the maximum value, mean, variance, and other mathematical things in it. That's the whole story. So, for example, let's research the response length field for each URL. Let's find the numbers of answers, the shortest answer, the longest answer, the average answer. It's really easy, isn't it? And as a special treat, I have prepared for you an example with a word count on the data frames. Let's find the most frequent words in the user agent. To start, user agents should be divided into words. This task can be perfectly handled by the split function. At the output, you get the list of the words from each user agent. The next step is to divide the words into separate lines. Well, you already know that this is done through the explode function. Now you can group the lines by the resulting words and count the number of lines for each word. Here you go. And the last step is to sort the words by the number of occurrences and get our statistics. Hooray! For today, you have revised how the aggregation in SQL is done. Learn how to aggregate in a data frame. Have fun and practice with aggregation. So I am waiting for you in the next video, where we will discuss the join. Hello, my name is Pavel. Imagine that you have your favorite access log and some external tables, which, for example, store geographic data for each of the IP addresses. Other sources of data can be loyalty cards that link users' ID with their offline purchases. To access the information and use it to analyze our log, we need to learn how to join tables. The ability to merge multiple tables together allows you to store data as a set of tables with complex relations. We can build stars and snowflakes from the tables. Each of these tables can be updated independently with the appearance of the new data. And you will be able to choose the fields necessary to solve the particular problem for this complex structure. Well, I ask you not to get addicted to complex data structures. The fact is that in order to join two data sets, you need to send the data of each of them over the network. And this is quite costly. Data model is too complicated, thus it will be processed too slowly. Therefore, you should always look for the golden mean. In this video, you will learn how to join data frames. I will show you how you can do different types of join. Moreover, I will show you one trick that you can do with the cross join. Recall that in the past video, the director of product development asked you to build the distribution of users by country. Last time you did it, not build this distribution because there was no information from each country's people were. Let's try to do it now. To do this, let's read the table access log and merge it with the table of geography by join. This can be simply done in a SQL query. To do this, you use the join clause to specify the second table in it and then set the condition. Well, you already know this. If you look at the result, you will see the data from the access log and the from GeoIP table. To do the same with the data frame, you need to use the method join. In this parameter, you specify the second table and the join key. And here is the result. Instead of specifying the join field, you can specify the condition. Then the join will be exactly the same as in SQL query. But let's come back in our distribution of visitors by country. To build it, you join the access log and GeoIP as you have done before. You group them by country and count the number of different IP addresses from each country. And sort the result by descending the number of IP. Based on the statistics, you need to make a French, German versions of your site. During the join, you make one problem that can cost a bundle to you if you ignore it. Let's count how many lines there are in GeoIP. Almost 10,000. How many entries are in the access log? 819. And how many records were obtained in the join table? There were 40 entries less. Where did they go? The fact is that not all the IP addresses from access log are in GeoIP. Spark returns results only for the IP addresses that are both in the left and in the right tables by default. This strategy is specified by how parameters, and by default it is inner join. If you didn't notice it, then you would have 40 visitors less in the daily attendance report. In real life, such errors can distort data, and they are very difficult to find. In our case, to avoid the error, you just need to make the left join. That guarantees that any value from the left table will be definitely be in the result. For visitors who come from the unknown country, the country name will be null. Let's check that now. You don't miss any events from the log. There are other modes like right join, full join, but I suggest you read about them by yourself. Otherwise, my story might be too boring. There are two interesting types of join that I want to show you. The first type is semi-join. If you join the access log and GeoIP in this way, the result will look like the same way was the original access log, without new fields. Why does it happen? Let's count the number of answers. There are 88,000, just as many as when you merge the access log and GeoIP with the help of the inner join. Semi-join is a convenient reception which allows you to select from the tables 1 all the entries that are in table 2. And there is a supplement trick called anti-join. It has a keyword left anti. Applying it, you get 4,100 values, all that was not in GeoIP table. The last type of join I want to tell you about is the cross join, when each entry from the left table is linked to the each record from the right table. If there are 10 rows in each table, then you, in the end, you get a table of 100 values. And if you do a cross join in the access log and the GeoIP, you get 80 million records. Spark developers took a special care about it. They made a particular function to protect you from an accidental data explosion. Why do you need such a join but for writing the multiplication table? I know one problem in log analysis which is solved with the help of cross join. As I have already said, I have too big access log at my work, and to reduce it somehow, my colleagues squeeze events in it. If several identical events appear at once, you store all of them in one record, and you add the events count field at the end. It shows how many events there actually were. Here I have simulated a compressed log using a random number generator, adding values from 1 to 10 as a new column. Let's try to restore the original log from the squashed one. Let the first line appear in it 8 times, the second 2 times, the fourth 3. How to do this? To do this, create a new data frame with the line numbers. You should have enough numbers to restore back any pack of events. In our case, the compressed log requires 10 numbers. Firstly, create a pandas data frame. Then you turn it into a Spark data frame and make a cross join with our compressed data. Each line is now repeated 10 times, and 80,000 lines of the log have turned into 800,000. Specifying the condition ID less than events count, you guarantee that for each compressed row of the log as an input, you get exactly the required number of the expanded logs lines at the output. For 6 events, you got 6 lines of the log. For 3 events, 3 lines, and so on. So you have restored the compressed log, and 80,000 records increased to 500,000. Let's sum what you have learned in this video. How to join on a data frame, the difference of join types, got acquainted with the trick of data processing using cross-join. This is the end of second lesson. At the third lesson, you will learn advanced data processing techniques in data frames. Stay with us. Hello, my name is Pavel, and now we will talk about user-defined functions. Let's return to the task called word count. You solved it when you were talking about aggregation. Some time ago, I worked as a manager. When someone from the staff came to me and bought me something like this, I would tell him, what are these capital letters doing here? And these quotation marks, those break-ins and those commas. Do you think that you have done this task? Do you find it right? Are you kidding me? Go and do it again. This is not a result that our customers want. Since you can do everything with those predefined functions that are available in Spark SQL, you need to write some functions by yourself. Of course, in this case, you can use complex combination of the existing functions, but then you will find your code awful. It's good enough to scare children at night. Let's see how it can be done in a nice way using Python functions. I believe you remember the wonderful times when you had only RDD API and nothing more. We could write everything on SQL, every transformation. We took some function, ran it on RDD, and it worked. Where are they now? In fact, we can still bring them back. You just have to create a user-defined function, abbreviated UDF, and use it on both the DataFrame API and SQL queries. Of course, it will work more slowly than functions written on Java. This user-defined function should be used at a pinch. Let's assume that you have some case now. In this video, you will learn how to create a user-defined function for DataFrame API, how to use UDAF in SQL queries. Also, you will solve our problem by building a clean and accurate word count and parsing user agent. First, you create the simplest UDF function. You take a function len for this purpose, which measures the length of a string or array. You can create UDF using the Spark function UDF. You pass len as a param and get a function that can be applied to the data frame. Let's call it len UDF. Now you take access log and measure the length of user agent by len UDF. And here is the result. Everyone excited and happy. But if you look at the scheme of the resulting data frame, you will see that the resulting lengths are stored as a text. What a nonsense that is! And how can I filter string by length? How I calculate its squares? How to find the longest line? I don't need strings, I need numbers. What should I do? The fact is that all the fields in the DataFrame API are typed, and each function must output data of a certain type. All the function returns string by default. If you want the function to return something else than a string, you must specify what you want to get. For the length function, you want to get the integer. So let's point out that the output type is an integer type. Set the function again. Check its schema, and now everything is in order. Whew. Now you're ready to write a function that parses the user agent carefully, throwing out everything that is odd. Here is the simplest example of a function that divides string by spaces. You transform it into UDF. What kind of result should it return? It should be already separated line. For this, the output type must be a list of strings, like this. Let's substitute it into our transformation. The result remains the same, but at least you have already used the code that you wrote and can change it. Let's clean our data. Firstly, let's remove all the numbers by regular expression. Numbers, points, slashes, and underlinings, they just cock out strings. We want to see what words you meet. Excellent. Secondly, you have too many punctuation marks. Opening brackets, closing brackets, periods, semicolons. You don't need all of them. You can clean it with another regular expression. It is getting better. The third step, you can translate everything into the lowercase so that the word Mozilla and Mozilla are considered one, not two. Simply write the function lower. And now your result is exactly the same as we wanted. And top of the most popular words look like you want. Now you are able to apply UDF function to the DataFrame API. But what should you do to use Python function in SQL queries? For example, you work in Jupyter, and if your SQL query fails, you say crap, and then write it correctly. To do this, you need to register your UDF function and assign it a text name by session UDF register. You should specify name of a new SQL function, a related Python function, and return type. Well, you already know it, isn't it? You have registered a new function with name Parse user agent. Now you write your query with Parse user agent and get list of words for each user agent. Next, you add explode there to break list into the words. Add group by word to count the word frequencies. Then you apply order by to sort the results. And here is your result. And everything is fine. You probably still ask me, how do we get the browser device and other parameters from the user's agent? How to extract useful information from it? This is an important task. But here I advise you not to reinvent the wheel, but to use ready-made functions. For example, the Python library called userAgent. Before using it, do not forget to ask the admin to install it on all of the cluster machines. It works very simply. Import it into your program, apply it to string with userAgent, and take the fields you need from the result. Based on it, you can create UDF functions to determine the browser, operating system, and device, and apply it to your log. Here is the result. So remember about such tool as user-defined function. Use it if necessary, but don't forget about overhead. These functions work much more slowly than functions written on Scala and Java. Use them wisely, and you will be happy. In this video, we have learned how to write user-defined functions for DataFrame API, for SQL queries, and practiced cleaning the user agent. Next time, I will talk to you about work with time. Hello everyone, my name is Pavel, and now we will talk about the way how you can work with time. Imagine that the boss comes to you and tells you to build a report on how many days each visitor spends at the website. He wants to know who spent 1 day, 2 days, 3 days, and so on. How do you do this? First of all, you need to take the time column and translate it into Spark SQL internal format. Let's look at it. Oh, the task seems difficult. If you parse this date by yourselves, you will spend a lot of time waiting for nothing. Thanks God there is a wonderful Spark SQL where everything is already done for you. And there are functions that allow you to work with time. Therefore, in this video, you will figure out how time is stored in the Spark, how to parse the time columns property, and learn how to work with time to solve our tasks. In fact, computers store time not in days, months, and years format. The time inside a computer is stored as a value, the number of seconds since 1917. This format is called Unix time. The Unix timestamp function not only allows you to get the current time, it also allows you to turn any line with a date into Unix time. But if you apply the Unix timestamp to the current line, you'll get an empty value. You need to explain how this line is arranged. Where is the day, month, and year are. This is done by using the string format. You are writing a neat template for the date, the time, and the time zone. Voila! You have done it. You have received the timestamp. You can turn a timestamp into everything you need. Save the data frame with a new field to a new variable. Let's return to our task and find the time difference between the first and the last page view for each visitor. To begin, you need to find the time when visitors came for the first and the last time. Calculating the minimum and the maximum click time will help you. Let us find the difference in time of the first and the last browsing of the pages. As a result, you get the total time spent on the site. We call it seconds CNT. According to the calculations, someone spent 100,000 seconds on the site, someone 20 seconds, and someone 0, because he opened the page of your site only once. To convert seconds into dates, divide the result by 60, 60, and 24. You also need to add 1, since the person who made 1 click was on the site 1 day, not 0. And this result will bring to the boss, but an attentive manager will ask you a question. Guys, let's say a visitor came to your site last night and this morning. Your calculations say that user spent 1 day on site, but this is not true. He or she was on the site for 2 days, yesterday and today. You have an error in the calculations. Go and fix it. To calculate our value correctly, you can use the Spark SQL time functions. For example, DataDiff will tell you how many days have passed between the first value and the second. This function works with a timestamp and doesn't work with seconds. Let's turn Unix time into a timestamp by a simple time conversion and save it into a new variable. Find the beginning and the end of user's history like you made it before, and then apply the function DataDiff to them. You will get the correct numbers of days between 2 elements. And add one to take into account the first day of the visit. Now your task is finally solved correctly. So, at this lesson you have got acquainted with Unix time, have learned how to parse lines in time, have learned how to manipulate time to solve problems. In the next video, you will learn how to use window function to solve one of the most important log analysis problems. Stay with us. Hello everyone, my name is Pavel, and now we will talk about how to find visitor sessions. This is very important task should be solved when you analyze users' behavior. How do people usually browse the internet? Imagine someone goes to the Facebook. He scrolls the feed, reads the news, writes something, then he gets tired of it, he closes Facebook and goes chatting with people, enjoying the life. And after a couple of hours, he comes back, uploads the new photos and checks their statuses, surfs a bit and leaves again. In fact, most people visit websites in this way, enter them, reading something interesting and leave. Web analysis has even a special term for such visits. They are called sessions. On some sites, the sessions last 2-3 clicks. People read some articles and leave. In online games, there can be thousands of clicks, but only one session. Practically, the concept of session for site owners is more understandable and important than individual clicks. And first of all, they are interested in know how many sessions a person makes on their site. Let's learn how to answer this question. It could seem an easy thing to do. You take all the clicks of the visitor, find the delays between clicks that are greater than 30 minutes. Each of them is treated as a new session. But, frankly speaking, for a long time I have been thinking that a new sessions couldn't be found in SQL. And I'm sure that half of big data engineers doesn't know how this can be done. And early I took Python, loaded all clicks from SQL as a list, processed them in a loop, found the session, and loaded back into SQL. But you can use SQL or our beloved DataFrame API for this now. I will show you how to do this. For this, you need to use window functions. And in this video, you will recall what window functions are and how they work, what types of windows there are and why they are needed. And as a result, you will solve the task of counting sessions gracefully. So, window functions are special kind of aggregation functions. However, when you apply them, the size of the source table doesn't change. A new value is added to it as a new column. A typical window function is defined inside the selects method and looks like this. This transformation also consists of two parts, the same as aggregation. The grouping condition, which is called the window, and the aggregation function. This example counts the number of clicks for each IP address and adds it to the end of the list. You can verify that for the first IP address, the number of clicks is calculated correctly. There are 2 clicks. Window functions are similar to aggregates, but there are differences between them. Let's take a look. Firstly, the window is applied not to the whole table, but to a separate column. Secondly, the number of values doesn't decrease as output, as an aggregation. Thirdly, for window function, the grouping condition is written at the end. And the fourth, which is very important, the values in the window functions can be ordered, and that can be used. Let's talk in the details about how the windows are arranged. In window functions, the grouping of values is specified using the window. As in group by, you can choose the columns you need. Using partition by, you select the lines can be grouped by IP address. It divides events into groups with the same IP. For example, you have a visitor who did 9 clicks, and here is the time of each of them. And in the grouping and in the simplest type of window, the events are not organized. But unlike groupings, you can set order in windows using order by. And since the function is applied to each line, it also has a sequence number of the current line of the list. And this allows you to use completely new types of functions, such as get the first value, get the last value, take the previous value, take the following value, return the number of current line in the window. And the old aggregation functions like the minimum, maximum, sum also continue to work. To make it more clear, let's take a window grouped by users and organized according to timestamps. And for each click based on this window, you will find the sequence number of the event in the window, time of the previous event, time of the next event. In fact, it is very convenient. You can see that for first click, the previous value is null. In pandas, it's designated as not a number. The same applies to the next value of the last click in the group. Function lead that I used here will help us to find sessions. As I said before, to find the session, you need to compare the time to the current and the next click. You have thrown out all the unnecessary columns from the query. By subtracting the Unix time column from lead, you have found the time between clicks. When the time is none, this means that it was the most recent withdraw click. You are interested in finding two types of events: when the time difference was greater than half an hour, or when a person made his last click and the time difference is null. You count number of sessions for each person, grouping them by IP. You did it. I wonder who had the most sessions. Let's see. For this, you sort the results by number of events and take the top. In our little piece of the log, there are 3 people with 6 sessions. Wow! Now, let's check the accuracy of our calculation. It is always important to check your result before presenting it. Let's take some IP address and check the number of sessions in it. For example, you choose the IP with 3 sessions and visualize them. To do this, filter all the events from access log for this IP address and store them as a pandas data frame. The time will be on the x-axis. For this, you need to make the timestamp index of the data frame. On the y-axis, you will set some random values so that will separate close points on the chart. Everything is ready to visualize our time series, and you can be sure that there were 3 sessions. You found that right. So, at this lesson, you revised window functions, talked about the types of windows, and solved a counting sessions problem by them. In the next video, we will talk about two-dimensional aggregation using pivot tables. Do you know what is it? So, hello everyone. My name is Pavel, and now I will tell you how to build two-dimensional distributions using Spark data frame. Such thing doesn't exist in Hive. It can be made in Spark by SQL query. It's available only in DataFrame API. I can honestly say that I found out about it only when I began to prepare these lectures. But I think this tool definitely comes in handy for my work, and I hope it will be useful for you as well. So, you have already calculated how visitors are divided by countries for our director of business development. But it could be not enough for him. Typically, he wants to see more details about visitor URLs and ask us to calculate the share of Russians, German, British, and French on every page. It will allow him to decide which page to translate first. Or, for example, our data scientist comes to us and says, "You have user ID and URLs in the log. Could you make me a table of users and mark how many times they visited each URL there?" For all URLs? Of course not. Only for 1,000 most popular. It's very important for a data scientist to know how to make such tables. They will be used in the predictions. You will learn details in the next course. Of course, you can count how many times each person clicked any URL, but only for one URL, not for 1,000. You can join the results for one URL and for other, but 1,000 jobs will calculate for years. Well, don't worry. In the DataFrame API, there are special tools that can help us with this. It is called a pivot table. At this lesson, you will learn what type pivot table is and how you can construct two-dimensional distribution using the pivot table. Now you are going to solve the task of the data scientist because it is a common problem. To start, you need to find the most frequent URLs. You will use them in filtering. This is not difficult to do. You group the access log on URLs and count them. Then you sort the results by number of found URLs. Then you take 1000 of the most frequent URLs and save them to pandas. You convert the URL column into a list of values, so your top is ready. Now you build the distribution of URL for each visitor. Firstly, calculate how many pages each IP address has visited. You have already done it many times. And now you add the function pivot. On the input, it takes two parameters, a column for the second dimension and a list of predefined values for new columns. The second parameter is optional. Without it, all the distinct values will turn into new columns. You have 40,000 different URLs. Spark will fail trying to build tables with 40,000 columns. Therefore, the second parameter is important for us. The pivot method is called in between group by and count. You will make the second dimension from the URL column. The values will be the most frequent URLs that you have recently found. And now you get our two-dimensional table. What do we have here? Most values are equal to none. How will the data scientist use it? He needs zeros, not the missing values. Don't worry, the fillNA function will help you. FillNA sets the default value for all the missing values. Hooray! You have done it! And you have learned how to build pivot tables, create features from the visited URLs for each visitor, and fill the missing values in. Now you know enough to use the data frame in your ongoing work. My mission is fulfilled, and I say goodbye to you. Good luck on the way of your learning.
Hello. As we are bound to spend some time together, I believe that getting to know each other might be a good idea right now. My name is Natasha, and within 2 weeks, I'm gonna bring you through the hardships of framework GraphFrames. So, buckle up, let's get going. In this video, I'll give you some examples of graphs. We see graphs in everyday life even without realizing it. For example, a map of a public transport service, such as a metro map or a street map on a car GPS navigating system. In these two examples, the graphs represent some geographical places, bus or metro stops, villages, areas, etc., and connections between them, bus routes or just roads. There are many other examples of graphs. When you are sneaking up into Facebook, Twitter, Instagram, yeah, I know, we all are walking this way. So, when you are entering Facebook, Twitter, Instagram, or any of your favorite social network, you are dealing with graphs again. Social graphs this time. Your social graph is all people with whom you have different kinds of communication, to whom you're writing messages, whose photos you're viewing, and whose posts you read, as well as chat messaging. And what about good old phone calls? Yep, we make calls and we receive them, and the records form graphs as well. And one last but not least example, bank transactions. People send and receive money, and these transactions can be shown as a graph as well. So, now you know that a lot of data in real life can be called a graph, and it's useful to know how to work with such data. But what is the strict definition of a graph? In mathematics, a graph is a structure relating to a set of objects in which some pairs of the objects are in some sense related. The objects correspond to mathematical abstractions called vertices, and the lines between each of the related pair of vertices are called edges. Typically, a graph is depicted in diagrammatic form as a set of dots for the vertices joined by lines or curves for the edges. In this picture, we see a drawing of a labeled graph of 7 vertices and 9 edges. The edges may be directed or undirected. For example, if the vertices represent people at a party and there is an edge between 2 people if they shake hands, then this graph is undirected because person A shakes hands with the person B only if B also shakes hands with A. In contrast, if any edge from person A to person B corresponds to A is admiring B, then this graph is directed, because admiration is not necessarily reciprocated, unfortunately. The former type of graph is called an undirected graph. The edges are called undirected edges, while the later type of the graph is called a directed graph, and the edges are called directed edges. Summing up, a graph is a structure relating to a set of objects in which some pairs of the objects are in some sense related. And in our everyday life, we're surrounded by data which can be analyzed in a graph form. So, it's worth knowing how to work with them. Hello! Time flies, and at my second lesson you will be dealing with different ways to represent graphs. Each has its own advantages and disadvantages. It's common to identify vertices not by names, such as Natasha or Moscow, but instead by a number. Knowing just 2 things about me, like Natasha and Moscow, you will still need my number. So, let it go. That is, if you have a graph with v vertices, then you typically number them from 1 to v. Here is a graph with its 7 vertices identified by numbers rather than names. The first way to represent a graph is an edge list, which is an array of E edges. To represent an edge, you just use a pair of vertex numbers. If the edges have weights, you can add the third element to the array, giving the edges weight. For example, here is how you represent an edge list in Python for our graph. Edge lists are simple, but if you want to find whether the graph contains a particular edge, you have to search through the edge list. If the edges appear in edge list in no particular order, that's a linear search through E edges. Another way to represent the graph is adjacency matrices. For a graph with V vertices, an adjacency matrix is a V times V matrix of zeros and ones, where the entry in row E and column G is 1 if and only if the edge from vertex E to vertex G is in the graph. If you want to indicate an edge weight, put it in the row E column G entry and reverse a special value, perhaps null, to indicate an absent edge. Here is the adjacency matrix for our graph. With an adjacency matrix, you can find out whether an edge is present in constant time by just looking up in the corresponding entry in the matrix. For example, you can query whether edge from vertex 3 to vertex 6 is in the graph by looking at the element in the third row and in the sixth column. So, if there is a disadvantage of an adjacency matrix? Yep, more than that, there are 2. First, it uses a V by V matrix, even if graph is sparse and has relatively few edges. In other words, for a sparse graph, the adjacency matrix is mostly zeros, and you use lots of space to represent only a few edges. So this is inefficient. Second, if you want to find out which vertices are adjacent to a given vertex, for example, vertex E, you have to look at all V entries in row E, even if only a small number of vertices are adjacent to vertex E, which is also inefficient. For an undirected graph, the adjacency matrix is symmetric. The row E, column G entry is 1 if and only if the row G and column E entry is 1. For a directed graph, the adjacency matrix need not be symmetric. The final way to represent graphs is adjacency lists. Representing a graph with adjacency lists combines adjacency matrices with edge lists. For each vertex E, you store an array of vertices adjacent to it. You typically have an array of V adjacency lists, one adjacency list per vertex. Here is an adjacency list representation of our graph. Vertex numbers is an adjacency list are not required to appear in any particular order, though it's often convenient to list them in increasing order, as in this example. You can get to each vertex adjacency list just by its index in an array. To find out whether an edge from vertex E to vertex G is present in the graph, you go to the E's adjacency list and then look for G. How long does that take in the worst case scenario? Any ideas? Don't be shy, nobody going to be mad. The answer is the number of vertices connected to vertex E, because that's how long E's adjacency list is. This number is the number of connections and could be as high as V minus 1 if E is adjacent to all other V minus 1 vertices, or as low as 0 if E is isolated with no edges. In an undirected graph, vertex G is in vertex E's adjacency list if and only if E is in G's adjacency list. How much space do adjacency lists take? This much? You have V lists, and although each list could have as many as V minus 1 vertices, in total the adjacency lists for an undirected graph contain 2 times E elements. Why 2 times E? Each edge from vertex E to vertex G appears exactly twice in the adjacency lists, once in E's list and once in G's list. And the second reason is there are E edges. That's why adjacency lists have 2 times E elements in total. For a directed graph, the adjacency lists contain a total of E elements, 1 element per directed edge. To sum up, now you know there are different ways to represent graphs: an edge list, an adjacency matrix, and adjacency lists. Also, you know their advantages and disadvantages connected to each of them. Hello, it's high time to speak about life. We've known each other already for 2 lessons. Let's turn up the heat and speak about real life. Users and connections between them are the most precious thing all social networks have. So, to make users more involved, social networks are making huge efforts helping users to broaden their social graph. For example, they try to guess whom you know in real life but still aren't friends in terms of social networks, and show you the people you may know in special blog offering. For good recommendations of people you may know, it would be useful for each pair of users to count them mutual friends. This task was presented as a part of Social Network Analysis Hackathon, which was organized by the Social Network Одноклассники in April of 2016. Одноклассники has about 40 million users per day. The first step is to choose the most suitable way to represent a graph in memory. If you choose an adjacency matrix as the way to represent our graph, then it will be 40 million times 40 million matrix. Let's estimate the amount of friends of an ordinary user as 500. You think it's too much? I bet you have more. Also, let's decide that you can be friends with somebody only in symmetrical way, which means that if you are a friend of Joe, then Joe is a friend of you as well. In this case, the amount of non-zero elements in the matrix will be equal to 40 million times 500 times 2. But the amount of all elements in the matrix will be equal to 40 million times 40 million. Thus, divide 40 million times 500 times 2 by 40 million times 40 million equals to 1/40,000th. So ones will occupy only 1/40,000th of all memory. This doesn't look like the most effective way to store your data, to put it mildly. Believe me, you don't want me to put it crudely, as far as you are here not to learn Russian swearings. But you have two more ways to represent graphs in memory, an edge list and adjacency lists. Let's try them one by one, started with an edge list. Let's take a mini social graph as an example. Its edge list will look like a tuple you can see in the slide right now. Explanation is as follows. User 1 has edges 1, 2, 1, 3, and 1, 4, which reflects that user 1 has 3 friends, 2, 3, and 4. We know user 2 is friends with 1, 3, and 5. So we should add edges 2, 1, 2, 3, and 2, 5 to our edge list. But in undirected graph, the edge 2, 1 shows us the same as edge 1, 2. So by adding it, we will duplicate the information that user 1 and user 2 are friends. So we don't add edge 2, 1 because edge 1, 2 already exists. User 3 has more friends than users 1 and 2. 1, 2, 5, 4, 6, and 7. Reversed copies of edges 3, 1 and 3, 2 already exist in our edge list, so we don't add them, but we should add edges 3, 4, 3, 5, 3, 6, and 3, 7. User 4 has just 2 friends, 1 and 3 we already have. Reversed copies for both these edges in our list. If we look carefully, we will see that for the rest of users, id 5, 6, and 7, we already have all possible reversed copies for their edges. Id user 5 has 2 friends, 2 and 3, with reversed copies 2, 5, and 3, 5 added already to edge list. User 6 as well as 7 has only one friend, user 3. Reversed copies 3, 6 and 3, 7 are also added. Now, let's count the amount of mutual friends for each pair of users using the edge list. Let's use the Spark DataFrame API to represent our edge list. Each edge will be a separate row of data frame. First element of each pair will go to a column A and second will go to a column B. If you look carefully, you will see that vertices A and B are sorted in ascending order. It's important to remember this. Remember our final goal. For each user, we want to know how many mutual friends he or she has with all other users. We want to know how many mutual friends user 1 has with all other users, user 2 has with all other users, and so on. Thus, for user 1, we will find the following result of computation. With user 2, he has only one mutual friend, user 3. With user 3, he has two mutual friends, users 2 and 4. With user 4, he has only one mutual friend, user 3. With user 5, he has two mutual friends, users 2 and 3. With user 6, he has only one mutual friend, user 3. And with user 7, he has one mutual friend again, user 3. We will see a combinatorial explosion. The amount of people with whom user 1 has at least one mutual friend is much bigger than the amount of people user 1 knows directly. So we need to write our code in an effective way. How can we receive the desirable results from an edge list? For the pairs of vertices, let's call them A and C, we count the amount of intermediate vertices, people who share connections with both A and C. Let's call them B. Data frame with columns A and B, we will name ABDF. Let's duplicate it first. Second, let's rename the column A as column B and column B as column C in the duplicated data frame. Finally, let's give this copied data frame the name BCDF. So now, to find the structural pattern ABC, two vertices A and C connected through a third vertex B, we should inner join ABDF to BCDF using the condition that ABDF's column B is equal to BCDF's column B. It's time to show you the code. Here, we are importing all necessary libraries. Here, we are creating the edge list for our graph. Here, we are creating a schema for our data frame, naming columns A and B. Here, we are creating the ABDF data frame. In these two rows, we are creating a duplicate of ABDF, renaming column A to column B and column B to column C. Here, you can see two newly born data frames, ABDF and BCDF. Aren't they cute? After inner join ABDF to BCDF using the condition that ABDF's column B is equal to BCDF column B, we will receive the ABCDF data frame with columns A, C, and the duplicated B, one from ABDF and second from BCDF. Then we can throw away the friend in the middle, column B, because for each pair of users we need only the amount of their mutual friends, and we don't need the IDs of their mutual friends. Now, let's group our data on columns A and C and count the amount of times we receive each pair of users. Finally, let's filter from the result only the rows where column A is equal to 1. We will get the next result. But wait, why it is that user 1 doesn't have any mutual friends with user 2 and has just one mutual friend with user 3? Maybe he's just too picky to make friends randomly? I don't think so. The answer is, for each pair of vertices, we have just one edge. For example, we have an edge 2, 3, but we don't have a symmetrical edge 3, 2. After joining ABDF to BCDF using the condition that ABDF column B is equal to BCDF column B, we will not receive a row 1, 3, 3, 2. That's why in the final result we don't receive row 1, 2, 1. Will adding a symmetric copy for each edge fix our problem with the missing one mutual friend for the pair of vertices 1, 3? Let's check. For each edge in a BDF data frame, we are adding its reversed copy. Duplicate the new doubled ABDF again. Rename the column AB to BC, give a new copy name BCDF, and perform an inner join again. And let's take a look at this intermediate result. For user 1, we now have this. Looks promising. We have row 1, 2, 2, 3, so after throwing the friend in the middle 2, we will receive the missing result that 1 and 3 have mutual friends. Let's finish the computation. In the new A, B, C, D, F, let's throw away the friend in the middle, both big columns, group our data by columns A and C, count the amount of times we receive each pair of users, and finally, let's filter only the rows where column A is equal to 1. We will get. Hooray! Now we can see that the result is correct, and we have side effect. We know that user 1 has 3 mutual friends with user 1, which is actually true, because user 1 and user 1 is the same person. This side effect can be easily filtered in the last step of our algorithm. In summary, we count the amount of mutual friends in 5 steps. First, for each edge of a BDF, add its reversed copy. Create a copy of a BDF and rename columns BCDF. Join a BDF to BCDF using the condition a BDF column B is equal to BCDF column B. Throw out friend in the middle B. For each pair of vertices, count the number of occurrences. Filter the pairs consisting of identical vertices. What are the bottlenecks of this calculation? First of all, we double the data on our first step. Second, we shuffle our data twice, once on step 2 and once on step 4. That is very expensive in terms of sending data through a network. Could adjacency lists be better choice than an edge list? Yes, for counting mutual friends for each pair of users, they certainly are. What would our mini-social graph look like as the adjacency lists? It will have the following form. Now, let's create a data frame called user_friends_df. It will have 2 columns. Column A will contain the vertex ID. Column friends will contain an array with all friends of A. Nota bene, if 2 users are in the same adjacency list, it's because they have at least 1 mutual friend. Which friend? The user owning the adjacency list, where they actually are. So, if we walk through the adjacency list of the first user, then we can produce pairs. If we do the same for all users, for each row in user_friends_df, we must count the amount of times we receive each pair. So, our algorithm will have 2 steps. First, for each adjacency list, producing all possible pairs. For each pair, count the number of occurrences. Now, we still enlarge the amount of data on step 1, and we have 1 shuffle on step 2 during grouping. Can we avoid the data explosion on step 1? The answer is yes. As far as the graph is symmetrical, then if user 1 has 2 mutual friends with user 3, then user 3 has exactly the same amount of mutual friends with user 1. How can we use this fact? If all vertices in a fixed adjacency list are ranked in ascending order, then instead of producing all pairs, we can produce only pairs where ID of the first element is smaller than the ID of the second element. If we are acting in this way, then the fixed pair user X, user Y, where X is smaller than Y, will be produced from all adjacency lists where it's possible. So the final amount of their mutual friends will be correct. Let's see how this approach will work for user 1 in our mini-social graph. Let's produce the ordered pairs from all the lists containing an element 1. Adjacency lists for second, third, and fourth users you can see now in the slide. After this, we will receive the next pairs. After counting the occurrences for each pair, we receive the correct result. So, our algorithm will be modified in the following way. First, sort all adjacency lists in ascending order. Second, for each adjacency list, produce all possible ordered pairs. For each pair, count the number of occurrences. Now, we won't explode the data on step 2, and we will need only one shuffle on step 3. So, do we see a profit? In last version of counting the number of mutual friends with adjacency list, we finally see the number of mutual friends for the pair of users 1, 2, but not for the pair 2, 1. In the agelist version, we receive both. So, should we admit that adjacency lists have a disadvantage and after the last step we still need to double the data? Not really. The agelist algorithm won't work correctly without doubling the data. However, the adjacency list version gives us the correct result and in a more compact form, and we have the choice to double it or not. Insofar as the graph is undirected, then the amount of mutual friends for, say, 2 users don't depend on the order of these users in pair. For example, 1, 2 or 2, 1 will have the same amount of mutual friends. The decision to produce a reversed copy for each pair or not depends on how you will build your people you may know recommendation system further. So, let's summarize. What have we learned in this lesson? Now you know how to solve the task of counting mutual friends with an age list and adjacency lists. And you know that your choice of graph representation can critically influence the effectiveness of further graph processing. So, before making a choice between adjacency metrics, age lists, and adjacency lists, you should understand how the initial graph representation will be transformed on each further step of your graph algorithm. Hello! In this video, we are bound to get to know each other better, and I'm here to tell you the useful information I have concerning GraphFrames library. GraphFrames is a graph processing library for Apache Spark compatible with versions of Spark starting from 1.4. Still having some old stuff? You'd better get going and upgrade it right now. Wait, not right now, of course. GraphFrames benefits from the scalability and high performance of DataFrames, and it provides a uniform API for graph processing available from Scala, Java, and Python. GraphFrames supports general graph processing algorithms. However, GraphFrames is built on top of Spark DataFrames, resulting in some key advantages. First, GraphFrames allows users to phrase queries in the familiar powerful APIs of Spark SQL and Spark DataFrames. Second, GraphFrames fully supports DataFrame data sources, allowing writing and reading graphs using many formats like Parquet, JSON, and CSV. Users can create GraphFrames from vertex and age dataframes. A vertex dataframe should contain a special column named ID, which specifies unique IDs for each vertex in the graph. Age dataframe should contain 2 special columns, SRC, source vertex ID of age, and DST, destination vertex ID of age. Both data frames can have any other columns apart from special. Those columns can represent vertex and age attributes. One more step and you are almost there. So, let's create the graph frame reflecting our mini social graph from lesson 1. Create the vertices first. So, as you can see, GraphFrame can store data with each vertex in a social network as well as in a real life. Each user might have age, name, and gender. There is no wonder, as all my ideas are made for life, for making your life easier. And then, ages. Each connection might have a relationship type. In our example, all the ages have the same type friend, but a social graph can have connections with such a relationship type as follow, relatives, colleagues, in relationship, etc. If you look carefully, not only at me, but at the slide, you will notice that the ages data frame of our graph contains a reversed copy for each edge. Why? Because by default, each edge in GraphFrames library has a direction from source vertex to destination. So, to represent undirected graph in GraphFrames, we should create a reversed copy of each edge. I bet you all can hardly wait making your own graph frame from these vertices and these edges. Here you are. GraphFrames library supports basic graph and data frame queries. What do I mean by this? Naturally, during your work, you will have a lot of different questions such: how many users in our mini-social network have age over 30? Or, how many users have at least 2 friends? Well, my dear pals, these types of questions can be easily answered using graph queries. Since graph frame vertices and edges are stored as data frames, many queries are just data frame or SQL queries. Let's answer our question one by one. Interested in how many users in our mini-social network have age over 30? Feel free to use the query, the vertices data frame, with this piece of code. Looking for an answer to question how many users have at least 2 friends, simply combine the built-in integrity method with a data frame query by this code. So, first, in integrity method, we'll generate data frame with 2 columns, ID and inDegree, where inDegree will contain number of incoming edges for each vertex. Second, you just filter the IDs of vertices with inDegree equal or greater than 2. So, for those of you who was more concentrated on the content of the video than on my hairstyle, a brief summary. Now you know how to create a graph frame and how to do basic queries on it. As for the rest of you, you might get the rarest chance of reviewing this video again and enjoying my company. Coursera is generous enough to provide you with an unlimited number of watching. Just make sure you're through with it till your subscription is expired. Hi there! Here I am again. I bet you missed me, and this video is fully dedicated to the modifying DSL. Modifying refers to searching for structural patterns in a graph. GraphFrame modifying uses a simple domain-specific language, DSL, for expressing structural queries. For example, the structural query that you can see in the slide right now will search for a pair of vertices A, B connected by edges in both directions. It will return a data frame of all such structures in the graph, with columns for each of the named elements, vertices or edges in the motif. In this case, the returned columns will be A, B, E, and E2. By analyzing our mini-social graph, you are going to understand how this logic works. So, for each vertex in g.vertices of our mini-social graph, you have 5 columns: ID, name, gender, age, and university. But after finding all structural patterns that can be described by this pattern string, the result of modifying algorithm will have just 1 column for each vertex. This comes as no surprise, as modifying is wrapping all columns with attributes of the vertex in 1, so data is transforming in a way you can see on a slide right now. This transformation of g.vertices to one column A is conveniently enough done by the method nest_as_call that receives two parameters, the f, which is a data frame, g.vertices in our case, and call name, A in our case. That is the name of the column into which all the existing columns will be wrapped. So, nest_as_call returns a data frame with only one column named call name. The same miracle works for the edges. What opportunities to express structural patterns does DSL provide you with? The most concerned of you might have already learned that the basic unit of a pattern is an edge. For example, this pattern expresses an edge E from vertex A to vertex B. Be sure to note that vertices are put into parentheses, while edges are denoted by square brackets. A pattern is expressed as a union of edges. Edge patterns can be joined by semicolons. This motif specifies two edges from A to B and from B to C. Do you happen to know that within a pattern, names can be assigned to vertices and edges? For example, this pattern has three named elements, vertices A, B, and H, E. These names serve two purposes. First, the names can identify common elements among edges. For example, this pattern specifies that the same vertex B is the destination of edge E and source of edge E2. The names are used as column names in the result data frame. If a motif contains named vertex A, then the result data frame will contain a column A, which is a struct type with subfields equivalent to the schema columns of GraphFrame.vertices. Similarly, an edge E and a motif will produce a column E in the result data frame with subfields equivalent to the schema columns of GraphFrame.edges. Feel free to omit names for vertices or edges in motifs when not needed. For example, this pattern expresses an edge between vertices AB but doesn't assign a name to the edge. There will be no column for the anonymous edge in the result data frame. Similarly, this pattern indicates an out edge of vertex A but doesn't name the destination vertex. An exclamation mark before an edge means that the edge should not be present in the graph. For instance, this pattern finds edges from A to B for which there is no edge from B to A. More complex queries, such as queries which operate on vertex or edge attributes, can be expressed by applying filters to the result data frame. Let's sum up. In this video, you have learned the syntax of domain-specific language of modifying algorithms. How many friends do you have? In real life, people are quite happy with 1 or 2, 5 friends. Whereas in social networks, there are countless friends. Countless for users maybe, but after watching this video, you will have a trouble-proof device for counting the number of mutual friends for each pair of users. I'm speaking about modifying method of the GraphFrames library. Let's take again our good old mini social graph. Voila! And solve the task from the first lesson for each pair of users A and C, count the amount of their mutual friends, such as B, this time using modifying algorithm of GraphFrames. To use modifying algorithm, you should first create GraphFrame representing your graph. And to create GraphFrame, you should previously create vertices and edges data frames like in this slide. After vertices and edges data frames are created, use them to create GraphFrame. You are quite experienced now. To express the idea, two users have mutual friends of GraphFrames DSL language. Any ideas? Okay, I give you a hint. First of all, three users are participating in our structural pattern. The first user, let's call him or her A. The second user, let's call him or her C. And a friend in the middle, let's call him or her B. Actually, B is the user who is a friend of both users, A and C. So, you will have three vertices in our pattern, A, B, and C. Note that in GraphFrames DSL, names of vertices are enclosed and parentheses. So, let me guess how you want A, B, and C to be connected by edges. Do you want A and B to be friends? So, let's connect them by edge in our pattern. Using this pattern, you will have a separate column named E that will contain edges type, edges source, and edges destination. Do you need this info about edge in our final result? Not really. In this case, all the edges having the same type, friend. Source of the edge will be stored in column named A, and destination of the edge will be stored in column named B. As there is no additional value in having a separate column E for each edge, you can omit the name of the edge in the pattern. Thus, with no separate column E describing edge in the result data frame. The result will still contain only pairs of vertices A, B connected by the edge. So, let's change your final pattern too. If we want B and C to be friends, we use this pattern. Let's omit the name of the edge E2 in our pattern again. The type of all the edges in our graph is still the same, friend. Source of edge will be stored in column B and destination will be stored in column C. Thus, adding another column E2 describing our edge to the resulted data frame won't bring any additional value. So, final pattern will be. Let's try it and look what you will get. We see that Alex and Alex have a mutual friend Emily. What is actually true, cause Alex from the column A and Alex from the column C is the same person. So this fact is correct, but useless for solving tasks about people you may know recommendations. We want to recommend Alex to become friends with people who have a lot of mutual friends with him. But recommending Alex to become a friend with himself is quite strange, don't you think? So, let's filter such patterns. Much better, huh? But still not good enough for the final result, the number of mutual friends for each pair of users. Quite a task, you think. Trust me, I know what I'm doing. First, you don't need attributes for each column in your final data frame. So, just take an ID attribute of vertices in each column A and C and name new data frame AC. Now grouping data in AC by columns A and C and counting the occurrences of each pair. Here you are. See the result? For user 1, it's correct. In the final result, you don't have vertex B, so let's throw it away from our pattern like this. Don't even think about it. Of course, The pattern that you can see right now on the slide will find all the triplets of A, B, and C vertices in our graph, such as A and B connected by an edge, and B and C connected by an edge, while the pattern that is under it will find all the pairs of vertices AC, such as there is an edge from A to any other vertex in the graph, and there is any incoming edge from any vertex of the graph to vertex C. Thus, this video has certainly enriched your bundle of knowledge, and now you are able to: first, formulate tasks on GraphFrame DSL language. Second, make the right choice between anonymous and named vertices when making your patterns. Third, count for each pair of users number of their mutual friends using modifying algorithm of GraphFrames. Hello! In this video, we'll take a look under the hood of modifying method of GraphFrames library. Get ready for some really cool stuff. Relax, with a guide like me, you have nothing to worry about. Solving mutual friend task in lesson 1, you used the edge-list graph representation and joined original ABDF with its copy BCDF, in which column A was renamed as column B and column B was renamed as column C, considering these two data frames had the same value in column B. Modifying algorithm will do similar joins during finding their particular structural pattern. Follow me and I'll show you how modifying algorithm of GraphFrames is working. On the first step, structural pattern string, such as you can see in the slide right now, is splitted on patterns from the following list: named vertex, anonymous vertex, named edge, anonymous edge, and negation. For example, for string that you can see right now, you will get the following collection of patterns: named vertex A, anonymous edge, named vertex A from named vertex A to named vertex B, named vertex B, named vertex B again, anonymous edge from named vertex B to named vertex C, and finally named vertex C itself. On the second step, you will iterate over a collection of patterns produced on the step 1, joining more and more columns. Let's make an agreement right now and right here that the original graph frame will be called G, and the current result of iterations will be stored in the variable current result. How exactly every new pattern will be handled depends on two factors. First, type of pattern, and second, do current result already contain the columns with names mentioned in preceding pattern. Now, arm yourself with patience. We will browse together through all possible cases. I will try to describe each case as briefly as possible in order to maintain an understanding of what is going on. I do want you not just know that method modifying exists, but also to have a solid understanding of what is going on under its hood. And now, let me draw your attention to named vertex pattern. If current result contains a vertex name, then modifying will do nothing. If current result doesn't contain vertex name, then g.vertices data frame will be transformed to one column data frame by the method nestAsCall. This method was discussed in detail before in previous video when we were talking about DSL. Let's call the resulting data frame of method nestAsCall as one column vertices df. Note that the only one column of one column vertices df will be named vertex name and will contain at least one subcolumn with name .id. Further, Cartesian join of current result and one column vertices DF will be done. Having finished with this, we are moving to anonym vertex. Modifying will do nothing and current result will stay untouched in this case. Named age and the source and destination having type anonym vertex is our next pattern to discuss. GraphFrame.age's DataFrame will be transformed to one column DataFrame with name one column ages.df by the method nestAsCall. The only one column of one column age.df will be age name, and subcolumns of column age name will be DST and SRC. Cartesian join of current result and one column ages.df DataFrame will be done. Ready for a new step? Here we go! Named age with source having type anonym vertex and destination having type named vertex. G.ages DataFrame will be transformed to one column DataFrame with the name one column ages.df by the method nestAsCall. It will contain one column with the name age name with subcolumns DST and SRC. If current result already has the column with the name DST vertex name, then the inner join of current result with one column ages.df on condition current result.dst vertex name.id is equal to one column ages.df.agename.dst will be done. If not, then first G.vertices DataFrame will be transformed to one column DataFrame by the method nestAsCall. This DataFrame will have the name one column vertices DF and will contain one column with the name DST vertex name. Second, one column ages.df will be joined with one column vertices DF on condition one column ages.df.agename.dst is equal to one column vertices DF.dst vertex name.id. Let's call the product of this join temp.df. Third, the Cartesian join of current result and temp.df will be done. Yet we are not though. Please meet named age with source having type named vertex and destination having type anonym vertex will be processed in the same way as the previous case. The only thing you should do to transform the previous case to a current one is to replace DST vertex name to SRT vertex name everywhere and DST to SRT in joining conditions. Shall we go further and speak about named age with source and destination having type named vertex? As you've probably already guessed, there are four possibilities in this case. Column named SRT named vertex is in current result, and column named DST named vertex is in current result. Second variant, column named SRT named vertex is not in current result, and column named DST named vertex is not in current result as well. Third, column named SRT named vertex is not in current result, and column named DST named vertex is in current result. And last one, column named SRT named vertex is in current result, and column named DST named vertex is not in current result. Let's consider these four cases one by one, but before, G.ages DataFrame will be transformed to one column DataFrame with the name one column ages.df by the method nestAsCall, because you will need it in all four cases. The one column ages.df will contain one column with the name agename with subcolumns DST and SRT. In the first case, column named SRT named vertex is in current result, and column named DST named vertex is in current result as well. Current result will be joined with one column ages.df on condition one column ages.df.agename.srt is equal to current result.srt_vertex_name.id, and one column ages.df.agename.dst is equal to current result.dst vertex name.id. In the second case, column named src named vertex is not in current result, and column named dst named vertex is not in current result as well. First, g.vertices data frame will be transformed to one column data frame by the method nest_as called 2 times. Let's call the first resultant data frame of the method nest_as call as one column src vertices df. It will contain one column with the name src vertex name. And let's call the second resultant data frame of the method nest_as call as one column dst vertices df. It will contain one column with the name dst vertex name. Second, one column ages df will be joined with one column vertices df on condition one column ages df dot agename.dst is equal to one column dst vertices df dot dst vertex name dot id. Let's call the product of this join temp_df. Third, temp_df will be joined with one column src vertices df on condition temp_df.agename.src is equal to one column src vertices df dot src vertex name dot id. Let's call the product of this join temp_df 2. Finally, Cartesian join of temp_df 2 and current result will be done. That was a hard job, and successfully done. In the third case, column named src named vertex is not in current result, and column named dst named vertex is in current result. First, g.vertices data frame will be transformed to one column data frame by the method nest_as call, as usual. This data frame will have the name one column vertices df and will contain one column named src vertex name. Second, one column ages df will be joined with one column vertices df on condition one column ages df dot agename dot src is equal to one column vertices df dot src vertex name dot id. Let's call the product of this join temp_df. Third, join of current result and temp_df will be done on condition current result dot dst vertex name dot id is equal to temp_agename.dst. Last case, column named src named vertex is in current result and column named dst named vertex is not in current result, is the same as the third one. To transform the third case in last one, you need to change src vertex name to dst vertex name everywhere and src to dst in joining conditions. Last two cases, anonymous age and negation, can be reduced to the previously considered cases. Let's start from the anonymous age. It will be transformed to named age, and with the new age named _temp, it will proceed further as named age, but after the last join, column _temp will be thrown away from current result. Let's proceed by dealing with negation of named age or anonymous age. Negation will be done in 2 steps. On the first step, pattern negation will be transformed to named age or anonymous age, depending on what was inside it. Then, named age or anonymous age pattern will be proceed on current result in a way described before in this video. A new data frame will be received. Let's call it temp_df. Important to mention that temp_df is a subset of rows of origin current result. So, on the second and final step from current result, all the rows that are in both data frames, current result and temp_df, will be deleted. Data frame received as a result of pattern proceeding becomes a new current result, and iterations over collection of patterns from the step 1 continue. Let's sum up. What do we have learned in this video? Now you know in details how modifying algorithm of GraphFrames is working. Hello! After you know how all possible scenarios of modifying method are working, let's count the amount of joins modifying method will do, processing the following structural pattern. This pattern can be used for counting mutual friends of each pair of users in the graph. After the parsing string that you can see on the slide right now, as we have previously discussed, we will receive the following sequence of patterns: named vertex A, anonymous age from named vertex A to named vertex B, named vertex B itself, named vertex B itself again, anonymous age from named vertex B to named vertex C, and named vertex C. So, let's follow the previously described algorithm step by step and count the amount of joins needed to be done. You are starting from current result, which is known. So, when you process the first pattern from our sequence named vertex A, just one column vertices the F, this column A will be returned. So, 0 joins so far. Going further, anonymous age from vertex A to vertex B will be transformed to named age from vertex A to vertex B with the name _temp. First, proceeding named age from A to B with name _temp, as far as you already have the column named A in current result, so you should follow the case current result has the column with the name assertive vertex name and doesn't have the column with the name DST vertex name, and do 2 joins. Named vertex B time. Current result already has the column B, so nothing will be done. Named vertex B again, and nothing will be done again. Anonymous age from B to C will be transformed to a named age from B to C with name _temp first. Proceeding this way of age, as far as current result already has the column named B, so you should follow the case current result has column with name assertive vertex name and doesn't have column with name DST vertex name, and do 2 more joins. So now you have 4 joins. Finally, named vertex C, but it's already in current result, so nothing will be done. So 4 joins altogether during counting mutual friends with the modifying algorithm will be done. Why so many? In lesson 1, when we were counting mutual friends with the edge list, we managed to do the same just in 1. What are 3 additional joins doing? The answer is next. Extra free join will add info about the vertices A, B, and C. When you are not interested in the attributes of vertices A, B, and C in final result, that can seem to be an overkill. But in real life, the attributes of vertices A, B, and C can strongly influence the final recommendations. For example, if user A, user C are not only mutual friends of B, but also have attended the same university as B, then probability of them to know each other is higher. But if you don't have such attributes of users as university, then 3 extra joins can be unnecessary. GraphFrames give us a powerful instrument of modifying that lets us easily search for any structural patterns that can be expressed by a language of modifying DSL. You should understand the way it's working, its pros and cons that will let us in future optimize parts of our program that will become a bottleneck of our product. But Also, you should still remember Donald Knuth's observation: premature optimization is the root of all evil. Hello! While choosing the task for this lesson, I was counting your votes of my previous video and got the idea that counting itself is a very useful task. So, today we will count triangles passing through each vertex. Triangles? What is a triangle in terms of graph? For undirected graph, it's a set of 3 vertices provided there is an edge between any 2 of them. Let's take a look at our mini-social graph and find all triangles in it. You can see that vertices 1, 2 and 3 form a triangle. Vertices 1, 3 and 4 form a triangle, and vertices 2, 3 and 5, what a surprise, form a triangle as well. Okay, now you know what a triangle is in graph, but what means the number of triangles passing through vertex? For vertex A, the number of triangles passing through it is the number of triangles that contains vertex A as an element of 3-element set. Thus, triangles number for vertex 1 will be 2, for vertex 2 will be 2 as well, for vertex 3 will be 3, for vertex 4 will be 1, for vertex 5 will be 1. Vertices 6 and 7 don't have any triangles passing through them. If there is any sense in counting triangles apart from having fun with me on Coursera? Actually, the answer is yes. Social networks face such problem as spam. One of the strategies to spare the unwanted content is to register a fake user or even a bunch of them and then start to do activity from their names, sending messages, post stories, like posts of other fake users, etc. Still wonder what triangles have to do with it? One of the strong symptoms that user is fake is low amount of triangles passing through him or her, comparing to the amount of his or her friends. But this is only one possible use of triangles. Another one is clustering coefficient of the graph. Let's learn how to count triangles number using GraphFrames library. Let's assume that you are working again with our mini-social graph. So, to count number of triangles, you should just call the method triangle. The return data frame contains all the original vertex information and one more additional column, count, of long type, having the count of triangles. So, you have learned how to count number of triangles passing through each vertex in graph using GraphFrames library. And more to that, you now have the real usage of that method. Hi, I'm happy to say that at this lesson we will, yes, right you are, we will continue counting the triangles as if we haven't counted all of them, you may think. No, my dear students, we haven't. So, take your quizzy roads, let's get the show on the road. Let's see how triangle counting task can be solved with edge list. Let's assume that you already have the edge list for the undirected graph in a standard form, meaning that for each pair of vertices connected by edge, you will have just one edge in the edge list. And this one edge, such as the first vertex of the edge is smaller than the second. Remember the first lesson when you used the Spark DataFrame API? It's hard, but I believe in you. Do you remember? Right. Now you need it again to represent your edge list. Each edge will be a separate row of data frame. The first element of each pair will go to column A, and the second will go to the column B. So, vertex A will always be smaller than vertex B. Quite naturally, the original data frame with columns A and B will be called AB. And now you should duplicate it twice. Why? Trust me, I know what I'm doing. sometimes. In this first copy, rename the column A as column B and column B as column C1 and give this copy a name BC1. In the second copy, rename only column B to column C2 and give this copy a name AC2. Python code for this will be: now join AB and BC1 on condition AB.B is equal to BC1.B. So, in our newborn data frame ABC1, each row will represent 3 vertices, A, B, and C1, connected by 2 edges, from A to B and from B to C1. So, to understand whether these 3 vertices form a triangle or not, we should check whether the edge AC1 exists. To do this, let's join data frame ABC1 with data frame AC2 on condition ABC1.A equals AC2.A. So, what info does data frame ABC1C2 provide you with? The info that edges AB, BC1 and AC2 exist. So, if you find now all the rows where C1 and C2 are equal, then you will find all the triplets A, B, C which form an edge by any 2 of them. Hooray! Looking at our precious mini social graph, you will be surprised to see the correct result. Told, I knew what I was doing. To count the number of triangles for each vertex, you can do the same procedure as in the previous video. Come on, wreck your memory. You need to explode triangles and count the occurrences of each vertex. If you count the amount of shuffles to be done, there will be 2. When you were joining AB and BC1 and when you were joining ABC1 and AC2. Can you do triangle counting in less than 3 joins? Wanna bet? Actually, answer is yes, if there is enough memory on each worker to store an edge list. Because in this case, you can broadcast the edge list, and for each row of data frame ABC1, you can check whether the edge AC1 is in the edge list or not. Please take a look at this code implementing it. First of all, you're creating a set out of your edge list and then broadcasting this edge set. Second, you're creating UDAF function that later, for each pair of vertices A, B, will tell you if there is an edge between A and B or not. Third, for each row in ABC1, you are checking if there is an edge between A and C1. And if there is one, then A, B, and C form a triangle. So, to receive triangle's data frame, you should filter the row where is triangle is true. So, now you know how to find all the triangles with only one shuffle, joining AB and BC. Perfect! Congrats! Hooray! But now you should broadcast the edge list. Whether it's possible or not depends on size of the edge list and the amount of memory on each worker. My empirical experience shows that if it's possible to broadcast the edge list, then this will work faster. Otherwise, you'll have to use implementation with 3 joins, which is scalable and which will work even with huge edge list. To sum up, now you know how to count number of triangles using edge list. Hello, this lesson will be dedicated to details. Teeny tiny details can make your life happy or miserable. So, watch and learn. In this video, we examine how triangle count method of GraphFrames works. Remember that triangle count method computes the number of triangles passing through each vertex. First of all, this algorithm ignores edge direction. That is, all the edges are treated as undirected. In case there is an edge from vertex A to vertex B and an edge from vertex B to vertex A, duplicated edges will be counted only once. How can you get it? By flipping edges in a way that source of each edge is less than destination, and dropping all duplicate afterwards. Let's take toy example and see how this strategy works on it. In our toy example, data frame will contain edges 1, 2, 2, 1, 1, 3, 3, 1, 1, 4, and all of a sudden 4, 3. Let's go through it row by row and flip all the edges where condition source is less than destination is not true. The edge 1, 2 is correct, so it won't change. In the edge 2, 1, source is bigger than destination, so source and destination will be flipped, and edge 2, 1 will become an edge 1, 2. The edge 1, 3 is correct. 1 is less than 3. The edge 3, 1 is not correct, because its destination 1 is smaller than source 3. So let's flip them and get a new correct edge 1, 3. The edge 1, 4 is correct. And finally, in the edge 4, 3, source and destination should be flipped, and edge 4, 3 will be transformed to edge 3, 4. So the new data frame with all edges flipped will be 1, 2, 1, 2, 1, 3, 1, 3 again, 1, 4, 3, 4. Let's drop the duplicates and voila! 1, 2, 1, 3, 1, 4, 3, 4. Let's create a graph frame named G using this deduplicated edges data frame. As source is less than destination for each edge, then in the new data frame there will be only one variant of each triangle, where the first vertex ID is smaller than the second and the second is smaller than the third. Why? Let's call the first vertex A, the second vertex B, and here comes the surprise, the third vertex C. If A, B, and C form a triangle, then there should be edges between A to B, B to C, and C to A. If there is an edge from A to B, that means that A is less than B. If there is an edge from B to C, then B is less than C. And then, consequently, A is less than C, which means that if there is an edge between A and C, then it can go only from A to C. Let's formulate this in DSL language of structural patterns. So, now using triangles count method of GraphFrames, you will find all triangles using modified method which was described in detail in the previous lesson. Note that each triangle will be found just once. After you have found all the triangles, you should count the amount of times each vertex was mentioned in all the triangles. You can do it by exploding the triangles data frame, grouping by new call ID, and by counting the amount of occurrences of each ID. Let's call the data frame you received after exploding triangles as vertex triangles. The final step will be to join vertex triangles with the original data frame g.vertices on condition vertex triangles.id is equal g.vertices.id. Triangle count algorithm summing up. First, flip all edges in a way where source is less than destination and delete all duplicates. Second, find all the triangles with a motif using pattern. Third, explode triangles and count occurrences of each vertex. Fourth, Join info about triangles for each vertex with its original info about it. So, let's count the amount of shuffles of data that triangle count method will do with the data from the original GraphFrame G. On the first step, you won't do any of them. On the second, motif finding will do 6 shuffles. We counted them in assessment in lesson 2. On third step, 1 more shuffle will be done during grouping by ID. And finally, 1 more shuffle will be done at the last step, joining vertex triangles with the original G.vertices data frame. To sum up, you have learned how triangle count method of GraphFrames works step by step, and now you know how to estimate the amount of shuffles that will be done during it. Hi! Every time I start my video with some scintillating remarks, it has become a tradition already. If rules are made to be broken, traditions for sure. I'm not in my best mood today, so no jokes for you guys, sorry. Let's just start. In this video, you will learn how to find all the connected components of the graph using GraphFrames API. In graph theory, a connected component of an undirected graph is a subgraph in which any 2 vertices are connected to each other by paths, and which is not connected to any additional vertices in the supergraph. For example, the graph shown in the illustration has 3 connected components. A vertex with no incident edges is itself a connected component. A graph that is connected by itself has exactly 1 connected component consisting of the whole graph. Testing whether a graph is connected is an essential preprocessing step for every graph algorithm. Subtle, difficult to detect bugs often happen when your algorithm is run only on 1 component of the disconnected graph. As far as the connected components of a graph represent, roughly said, the pieces of the graph, finding the number and sizes of connected components allows you to do the descriptive research of the graph data you have. For instance, it helps you to understand what amount of isolated vertices the graph has. Also, computing connected components of a graph lies at the core of many data mining algorithms. For example, consider the problem of identifying clusters in a set of items. You can represent each item by a vertex and add an edge between each pair of items that are deemed similar. The connected component of this graph corresponds to different classes of items. Let's learn how to find the connected components of the particular graph using the GraphFrames API. But before, let's take a look at the graph which connected components you're gonna look for. To create it in the terms of GraphFrames, you need to interpret the following code. And then you just call method connected components like in the slide. Now, for each vertex, you know the ID of connected components it belongs to. Let's go through parameters of connected component method to understand what opportunities you have. First, you can choose which algorithm to use. Supported algorithms are GraphFrames and GraphX. GraphFrames is based on the article Connected Components in MapReduce and Beyond by Raimundas, Kiveris et al. And we will discuss it in detail in next video. I can particularly hear that sigh of relief after these words. Yes, you would definitely see me again, and I don't mean the rewind. Another variant, GraphX, converts the graph to a GraphX format and then uses the connected components implementation from GraphX library. Second parameter you can adjust is checkpoint interval in terms of number of iterations, and default is 2. Checkpointing regularly helps recover from failures, clean shuffle files, shorten the lineage of the computation graph, and reduce the complexity of plan of optimization. As of Spark 2.0, the complexity of plan optimization would grow exponentially without checkpointing. Hence, disabling or setting longer than default checkpoint intervals are not recommended. Checkpoint data is saved under org.apache.spark.sparkcontext.getCheckpointDir with prefix connected components. If the checkpoint directory isn't set, this throws a Java EO exception. Set a non-positive value to disable checkpointing. This parameter is only used when the algorithm is set to GraphFrames. The last parameter you can adjust is in connected components method is broadcast threshold in propagating component assignments. Default is 1 million. If a node degree is greater than this threshold at some iteration, its component assignment will be collected and then broadcasted back to propagate the assignment to its neighbors. Otherwise, the assignment propagation is done by a normal Spark join. This parameter is only used when the algorithm is set to GraphFrames. Oops! The time is up. Let's summarize what do we learn in this video. First, what is the connected component of the graph? And second, how to find all connected components of the graph using GraphFrames API. Hi! Now, as I've promised before, and I always keep my promises, let's talk about the algorithm based on the article Connected Components in MapReduce and Beyond by Raimundus Keveris et al. Computing connected components of a graph lies in the core of many data mining algorithms. This problem is well studied, yet many of the algorithms with good theoretical guarantees perform poorly in practice, especially when faced with graph with hundreds of billions of edges. Raimundus Keveris et al. Designed the improved algorithm based on the traditional MapReduce architecture for large-scale data analysis. In this work, they represent new alternating algorithm which has strong theoretical guarantees, bounded communication cost, and load-balanced computation. Extensive empirical evaluation of this algorithm was performed, and the authors compared to the best-known state-of-the-art approaches. With all the algorithm implemented on the same hardware, the alternated algorithm outperformed the fastest time algorithm reported in the previous work by Rastorgi et al. Finding connected components in MapReduce in logarithmic rounds. The new alternated algorithm computes the connected components by iteratively transforming the input graph over the multiple MapReduce rounds. It was proved that, unlike past approaches, this algorithm transforms the graph in a way that the number of edges never increases. The alternating algorithm is local, with every node in the graph performing some rewriting decision based solely on the structure of its neighborhood. This locality makes for an easy implementation in a distributed setting. Now, we will introduce some notation. Let G be an undirected graph on n nodes and m edges. For a node V, you denote by gamma of V the neighbors of V. You will use gamma plus of V to denote the neighborhood of V and V itself. Furthermore, with every node V, you associate the real number label L sub V. The alternated algorithm makes use of the small star and large star operations. Both operations are given a node U and a subset of its neighborhood N. Let M of U be the neighbor node with the minimal label. The operations replace for every V belonging to N the edge U V U with an edge V M of U. Both the small star and large star operation can easily be implemented in a distributed manner. I'll give the MapReduce version of these two operations in algorithm 1 and 2. Wait, guys, I haven't told you where you will go together yet. Let's go through pseudocode. Map receives a pair of nodes as an input and sort them in descending order by associated L value. It returns the sorted pair of nodes as an output. For example, if it gets pair UV and L sub V is smaller or equal than L sub U, then pair remains the same, UV, and vice versa. If L sub V is greater than L sub U, then the output will be VU. At the shuffle phase, you process the pairs produced by a map. Important to understand, after it, you don't get the full set of neighbors gamma of U associated with each vertex U. Since the shuffle processes sorted pairs, in case L sub U greater than L sub V, shuffle will process only UV pairs and never VU. This is why you will put V to subset of neighbors of U, but never U to subset of neighbors of V. Further, for each node U, you will call a reduce function, which gets as an input node U and subset of its neighbors N from the shuffle phase. Then you calculate M, the node with a minimal value L associated with it within a subset N. Then, for each node V of subset N and for U itself, you will emit a pair of node V or U and node M. Now, in this slide, you can see an illustration of small star at node 8. The minimal neighbor of 8 is 1, so small star connects 1 to all the nodes no larger than 8. Let's iterate over the pseudocode of this small graph together, step by step. On the map phase, we will reverse all the edges in a way that the source is greater than the destination. On the shuffle phase, the source of the edge will serve as a group in K. So, all the destination vertices with the same source vertex will group together. Further, we will consider how a reduce phase works only for the source vertex 8. The vertex with the minimal index among the received subset of neighbors for vertex 8 is 1. So finally pairs 1, 1, 5, 1, 7, 1 and 8, 1 will be emitted. Now, let's browse through the large star operation pseudocode. On the map phase, each edge will be emitted together with its reversed copy. During the shuffle phase, again, for each K source vertex, let's call it U. All destination vertices will be collected in a set named gamma of U. On the reduce phase of large star operation, you will iterate over elements of set gamma of U with the included vertex U. Let's call them V and emit a pair VM in case label of V is greater than label of U. M now is the minimal element among set gamma of U with added vertex U. Now, in this slide, you can see an illustration of large star at node 8. The minimal neighbor of 8 is again 1. At figure B, large star connects 1 to all the nodes with the label strictly larger than 8. For the same small graph as on the small star operation, let's iterate over pseudocode together, step by step. On map phase, we will duplicate all edges. On shuffle phase, source of the edge will serve as a group in K, so all destination vertices with the same source vertex will group together. Further, we will consider how reduce phase works only for source vertex 8. The vertex with minimal index among received set of neighbors for vertex 8 is 1. So finally, only pair 9, 1 will be emitted. Even though it seems from figure A and figure B that the two operations can disconnect the graph, in the article the following lemmas were proved, showing that performing the operations at all nodes in parallel preserve the connectivity of the graph. Lemma 1. Performing the large star operation on all the nodes in parallel preserves the connectivity of the graph. Lemma 2. After one round of large star, the number of edges in the resulting graph is no larger than in the original graph. Lemma 3. The small star operation preserves connectivity and doesn't increase the number of edges. I give a link to the full text of the article in the description of this lesson, so if you're interested in details of the proof, you have opportunity to satisfy your curiosity. As it's visible from the pseudocode in the slide, you can see right now the alternated algorithm combines invocations of large star and small star operations until convergence, what in the current context will mean that a fixed point is reached, at which point the overall graph is reduced to a union of disconnected stars, one for each connected component. It was shown in the article's lemma 8 that the alternating algorithm converges. Let's sum up. In this video was presented the new parallel connected components algorithm that outperforms the current state-of-the-art approaches. Hi! In this video you will examine how GraphFrames is implementing the alternating algorithm from the article Connected Components in MapReduce and beyond. To do this, you will browse through the Python-looking pseudocode that is a copy of the original GraphFrames code. Why are not we looking at the real one, you could probably ask me. Because it's on Scala. So, to make your educational process more smooth and pleasant, I've made a copy for you. Let's enjoy it together. All the logic will be implemented in method run, which receives a graph itself and broadcasts threshold. And right after receiving the graph, method run calls method prepare on it. How does method prepare actually arrange our graph? Method prepare is doing deduplicating vertices and assigning unique long IDs to each. Changing edge directions to have increasing long IDs from source to destination. Deduplicating edges and removing self-loops. In the returned graph frame, the vertex data frame has two columns. Column ID stores a long ID assigned to vertex. Column attr stores the original vertex attributes. The H data frame has two columns. Column src stores the long ID of the source vertex, and column dst stores the long ID of the destination vertex. And you always will have source is less than destination. After the graph is prepared, you can continue. Let's initialize variables, converged, iteration, and pref_sum with values false, 1, and none, respectively, and starting iterations. One iteration of alternated algorithm consists of two phases, a large star step and a small star step. Let's remember what is a large star step in the terms of the article. First, for each edge, you are emitting it in its reversed copy during the map stage. Then, during the shuffle for each vertex, you are grouping all its neighbors. Finally, among the neighbors of the vertex U and vertex U itself, you are searching for the vertex with the minimal index. Let's call it M. For all the neighbor vertices V of vertex U with indices bigger than U, you are emitting pairs VM. If you look now at the pseudocode of GraphFrames, it may be not obvious why it's doing the same. So, let me explain. First, the method MinNeighbors is applied. How does the method MinNeighbors work? For each edge in the edges data frame, it adds its reversed copy. Then, for each edge, finds its minimal neighbor and the amount of neighbors. According to the description of the large star step in the article, for each vertex you should find a vertex with a minimal index among neighbors of vertex U, and vertex U itself. So here you are adding the vertex itself to the set among which you should search for the minimal vertex. Going further, let's join every edge with min neighbor of its source vertex by the method skew-join. How does the method skew-join work? It finds vertices with a degree higher than broadcast threshold and calls the skew-join method of GraphFrames, handling the skew in the join keys by doing a broadcast join for frequent keys and a normal join for the rest. Let's come back to the large star step. After skew join is performed for each edge of the prepared graph, where the source of the edge is smaller than the destination, you have column with name min neighbor containing the vertex with minimal index among the neighbors of vertex SRC and vertex SRC itself. So, in the received triplet, min neighbor is less or equal to SRC and SRC is less or equal to DST. If now you rename the column DST as SRC and min neighbor as DST, then automatically new SRC will be bigger than new DST. This action makes the same effect as emitting only the pairs VM, where L sub V is bigger than L sub U at the last step of large star in the article. Consequently, the above-mentioned pseudocode is doing exactly the same large star routine as described in the article. Let's examine now a small star step. The article offers you to reorder all the vertices in edges in a way that makes SRC bigger than DST. You have already had this in GraphFrames implementation after the large star step. Then, for each fixed vertex, you should find the minimal element among its neighbors, which are smaller. Finally, for each small neighbor of SRC vertex and vertex itself, according to the description of the small star operation from the article, you should emit a pair SRC neighbor or SRC itself min neighbor. During this step, you will receive all the pairs SRC neighbor min neighbor. With this step, you will add pairs SRC min neighbor, rearranging them if needed in a way that SRC is less than DST, because it could happen that vertex is smaller than its smallest neighbor. Finally, let's filter all rows where the vertex happens to be the smallest neighbor of itself, because according to the article, it will be filtered later during the large star. Here, in GraphFrames, the invariant where SRC is less than DST for input data for large star operation is preferable to making this filtering. Finally, when another cycle large star small star is over, you should check whether our algorithm is converged or not. To do this, you are summarizing all IDs of SRC vertices, and if the sum isn't equal to the sum of the previous step, you change the meaning of pref sum variable and continue iterations. If the sum equals, then the algorithm is converged. And now you will do the following. First, join vertices with last version of edges on field DST. Second, if there is no incoming edge to this vertex, that means it's the center of the connected component, and its ID serves as the connected component identificator. Third, select vertex attributes, including its ID and new column component. To sum up, in this video, you have learned how exactly the parameter broadcast threshold impacts the computational process, So now you have a better understanding how to tune it. You browse through the example of algorithm implementation with good theoretical guarantees with GraphFrames and DataFrames API. And third, you understand now in detail how algorithm was implemented, and that gives you opportunity to predict the bottlenecks you can meet in practical application of it. Hello! In this video we'll talk about random walk, and before we start I want to share with you next quote by Shizio Kakutani. A drunk man will find his way home, but a drunk bird may get lost forever. Imagine now a drunk man searching his way home. As we mentioned in the very first video of the third week, a map of routes can be represented as a graph. So our dear smashed man is staying at vertex A of the graph. And as far as he is completely drunk, he is making his choice where to go randomly. But he can choose only from the vertices that are adjacent to the initial vertex A, where he is staying. Let's say he has chosen vertex B, and now he should choose which way to go again. The random sequence of vertices selected this way is a random walk on the graph. Now I need you to strain your memory again. In the very first lesson of the first week, when we were talking about different ways to represent graph in memory, we mentioned adjacency matrix. Remember? Let me refresh your memory. For a graph with V vertices, an adjacency matrix is V times V matrix of ones and zeros, where the entry in the row E and in the column G is 1 if and only if the edge from vertex E to vertex G is in the graph. Here is the adjacency matrix for our good old mini-social graph. If you want to indicate the edge weight, you can put it in the row E column G entry. Let's indicate the weights of all the outgoing edges of the vertex in a way where sum of them is equal to 1. What meaning will these weights have in case of random walk? Probabilities. If the edge from vertex A to vertex B has weight 1/2, that will mean that our precious drunk man will prefer this way to other with 50% chance. A matrix with the property where the sum of values in each row is equal to 1 is called a transition matrix, and a graph where for each vertex sum of weights of all outgoing edges is equal to 1 is called stochastic. Now, let me introduce some notations. Let x sub t of E be a probability that a drunk man is at node E at time t. Then x sub t plus 1 of E will be equal to sum of probabilities of being at node G multiplied by the probability of transition from G to E as G runs over all the vertices in the graph. What is equal to x sub t of G multiplied by p sub EG as G runs over all vertices in the graph. If you write the same equation in a matrix form, you will get the later matrix equation can be written in the following form. Now, it's high time to introduce you a stationary distribution. A stationary distribution is a distribution such as the following equation is correct. And there is a theorem asserting that if a stochastic graph satisfies two following conditions, the first, there is a path from every node to every node, and the second, the greatest common divisor of all the cycle lengths is 1, then there is a unique stationary probability distribution x with asterisk. The stationary distribution at a vertex is related to the amount of time a random walker spends visiting this vertex. Or, in other words, it shows you a probability of getting to a certain vertex after quite a big amount of steps. So far, an approximation of stationary distribution can be calculated by iteratively multiplying transition matrix on the initial probability distribution. Important to mention that stationary distribution doesn't depend on the initial vertex. Let's sum up. Now you know that if a graph is stochastic and it satisfies certain requirements, then a stationary distribution exists and it's unique. This theorem gives us a theoretical basement for this lesson devoted to ranking web pages by search engines like Google, and for last lesson of this week, describing music recommendation algorithms. I can see you can't wait to apply the powerful theoretical skills you received in the previous video to real-life tasks. Let's not waste time and start right now. In this video, you are going to deal with PageRank. PageRank is the first algorithm previously used by Google Search to rank websites in their search engine results. PageRank assigns a weight to each web page in the Internet with the purpose of measuring its relative importance. This weight is called PageRank of E and is denoted by PR of E. How does PageRank algorithm actually work? World Wide Web, also known as Internet, can be represented in the form of graph as well. Web pages will be vertices and links between the pages will represent edges. Now, let's rename our drunk man as an internet surfer who is sitting at his laptop and just browsing over billions of web pages by clicking on links leading from one to another. Maybe one day you were also spending your time like this. Intuitively, it's clear that a big amount of links leading to a certain web page leads to the bigger amount of time users spend on it. So, the more important this page is, and the higher its position should be in Google search results. Wait. At the beginning of the video, I promised that you would have a chance to apply your theoretical skills, and what? Here you are. Our surfer is acting exactly in the same way as drunk man from the previous video. Staying at each vertex, he is doing his choice to what page to go further. You know that if a graph satisfies certain conditions, then after quite a big amount of iterations, you will receive a stationary distribution. The stationary distribution at a vertex is related to the amount of time a random surfer spends visiting this vertex after quite a big amount of steps. And in case of World Wide Web, this can be interpreted as importance of the page. Imagine you have a small universe of 4 web pages, A, B, C, and D. PageRank is initialized to the same value for all pages in a way that the sum of page ranks of all the universe will be equal to 1. And all of them are equal as well. Hence, the initial value for each page in this example will be 1/4. Sounds familiar? The initial page rank of all vertices is nothing but a probability to visit each edge at the time t equal to 0. In the previous video, we denoted this probability by x sub 0 of e. The weight assigned to each edge will be 1. After the initialization is done, we can start iterations of random walk. Let's do one iteration. If the only links in the system were from pages B, C, and D to A, then PageRank of vertex A after one iteration will look like this. Now, suppose that instead of that, page B has a link to pages C and A, page C has a link to page A, and page D has links to all three pages. If there are several outgoing edges from certain works, then PageRank assumes that probability is equal to 1 divided by a number of vertices outgoing edges. So now, at the completion of this iteration, page A will have a PageRank of approximately 0.456. If you denote the number of outbound links as L, then in general case the PageRank value for any value U can be expressed as. That is, the PageRank value for a page U depends on the PageRank values for each page where contained in the set gamma of U, the set containing all the pages linking to page U, divided by a number L of where of links from page V. Okay, now you can see that a PageRank algorithm is just a particular case of a random walk. You know that if a graph is stochastic, then iterations converge to the stationary distribution only in case if each of its vertices is reachable from any other vertex and the greatest common divisor of all the cycle lengths equals 1. But why will the graph of the World Wide Web satisfy these conditions? It won't. So, ladies and gentlemen, let me introduce damping factor. The PageRank theory holds that an inventory surfer who is randomly clicking on links will eventually stop clicking. The probability that the person will continue at any step is a damping factor D. Various studies have tested different damping factors, and nowadays the damping factor is generally assumed to be set around 0.85. After the surfer stops, he continues from any page in the internet. So, for any page probability to be chosen is equal to 1 minus d over n. That is, in the new model, PageRank can be calculated by the formula. So, any page's PageRank is derived mostly from the PageRanks of other pages. The damping factor adjusts the derived value downward. The formula uses a model of a random surfer who gets bored after several clicks and switches to a random page. The PageRank value of a page reflects the chance that the random surfer lands on that page by clicking on a link. Google recalculates PageRank scores each time it crawls the World Wide Web and rebuilds its index. As Google increases the number of documents in its collection, the initial approximation of PageRank decreases for all the documents. So, the equation for PageRank is as follows. Where P sub 1, P sub 2, P sub n are the pages under consideration. Gamma of P sub e is a set of pages that link to P sub e. L of P sub g is the number of outbound links on the page P sub g. And n is the total number of pages. PageRank can be computed iteratively. At t equal to 0, the initial probability distribution is assumed. Usually, it's 1 over n. At each time step, the computation yields the following as detailed above. The computation ends after a fixed number of iterations or when, for some small epsilon, the following equation is true. It ends when convergence is assumed. After the damping factor is introduced, the graph of the World Wide Web satisfies both conditions for existence of the unique stationary distribution. So now you can be sure that computations of PageRank will converge, because stationary distribution at a vertex is the probability of getting to a certain vertex after quite a big amount of steps. In this video, you've got acquainted with PageRank, a first algorithm by Google search to rank websites in their search engine results. Moreover, you have learned how to calculate PageRank iteratively for every vertex in our graph. Hello! In this video, we will check how PageRank algorithm can be implemented using Spark's RDD interface. Why should we use RDD interface instead of DataFrames or datasets? For a change. Just joking. Real reason is that during the next week you will explore different optimizations of Spark jobs. Some of them are possible only for RDD, so the code that you will write during this video will be reused later as a base for RDD-specific optimizations. Let me remind you that the PageRank algorithm aims to assign a measure of importance, a rank, to each document in a set based on how many documents have links to it. It can be used to rank web pages, of course, but also scientific articles or influential users in a social network. PageRank is an iterative algorithm that performs many joins. The algorithm maintains two datasets, one of URL neighbor URL elements containing each neighbor of each page, and second of page ID rank elements containing the current rank for each page. It proceeds as follows. First, loads in the input file. Second, loads all the URLs from the input file and initialize their neighbors. Third, load all the URLs with other URLs linked to from the input file and initialize the ranks of them to 1 divided by a number of URLs. The algorithm starts with the ranks RDD initialized at 1 divided by a number of URLs for each element, and keeps updating the ranks variable on each iteration. The body of PageRank is pretty simple to express in Spark. Here you are. First, it makes a join between the current ranks RDD and the static links 1, in order to obtain the linked list and rank for each page ID together. Then uses this in a flat map to create a contribution values to send to each of the page's neighbors. After that, you add up this alias by page ID and set this page's rank to 0.15 plus 0.85 multiplied on contributions received. Although the code itself is simple, this example makes several things to ensure that the RDDs are partitioned in an efficient way and to minimize communication. Notice that the links RDD is joined against the ranks on each iteration. Since links is a static dataset, you partition it at the start with partition by, so that it doesn't need to be shuffled across the network. In practice, the links RDD is likely to be much larger in terms of bytes rather than ranks, since it contains a list of neighbors for each URL instead of just a double. So this optimization saves considerable network traffic over a simple implementation of PageRank. For the same reason, you call cache on links to keep it in RAM across iterations. When you first create ranks, you use map values instead of map to preserve the partitioning of the parent RDD, so that our first join against is cheap. In the loop body, you follow your reduce by key with map values because the result of reduce by key is already hash partitioned. This will make it more efficient to join the mapped result against the links on the next iteration. To sum up, in this video you have learned how to implement PageRank algorithm using Spark RDD API. And second, we discuss tricks that make HD implementation more efficient. Hello! In this video we will talk about GraphFrames implementation of PageRank algorithm and browse through the parameters available for tuning. First of all, there are two versions of PageRank in GraphFrames library. The first implementation uses the standalone GraphFrame interface and runs PageRank for a fixed number of iterations. Alpha is a random reset probability. Typically, it's equal to 0.15. In neighbors of E is a set of neighbors which link to E, and outDeg of G is the amount of edges outgoing from vertex G. This version of the algorithm can be run by setting parameter maxIter in the method PageRank call. The second implementation uses the org.apache.spark.graphics.pregel interface and runs PageRank until convergence. This version of the algorithm can be run by setting a parameter toll in the method PageRank call. Note that this is not the normalized PageRank. As a consequence, pages that have no in-links will have a PageRank of alpha. In particular, the PageRanks may have some values greater than 1. Let's take our usual mini-social graph and take a look how GraphFrames PageRank implementation will work on it. It's important to understand that PageRank's algorithm takes into account the direction of each edge. First, let's rank PageRank until convergence to tolerance toll. The resulting vertices data frame contains one additional column, PageRank, of double type, the PageRank of this vertex. The resulting edges data frame contains one additional column, weight, the normalized weight of this edge after running PageRank. You see that vertex Natasha has the highest PageRank, which is absolutely natural and highly predictable, not only because of the biggest amount of incoming edges, but also because it's my lesson. So, I'm an influential user in a social network. Let's see what result you will receive running PageRank for a fixed number of iterations. As you can observe, Natasha is still a leader, no doubt about it. But her PageRank is different from the one you received in Until Converges PageRank run. It's also not surprising, because the amount of iterations needed for convergence with tolerance 0.01 could be different from 10. What implementation is more practical? My advice is the following. Convergence to tolerance gives you more control over the process. You understand how close your current PageRank is to stationary one. However, if your graph is incredibly huge, but you still have a need to calculate fresh page ranks every 6 hours, then you could be limited by number of iterations. Let's sum up what do we learn in this video. First of all, what parameters GraphFrames implementation of PageRank has, and second, how to tune them. Hi! All the time spent with me, we've been talking about serious things, like ways to represent graph in memory, counting shuffles, and features of GraphFrames library. So, I think it's time to relax and speak about music. In this video, I'm gonna present you with a set of algorithms used for music recommendations and personalization in a general-purpose social network ok.ru, the second largest social network in the Commonwealth of Independent States, visited by more than 40 million users per day. The success of nearly all internet projects nowadays highly depends on how much value they can provide for the user, requiring as less efforts as possible. Recommender systems are one of the approaches used to increase value for effort rate. By analyzing users' activity in the past, a good recommender selects the items which are most relevant to the user's current needs, increasing users' satisfaction, loyalty, and the revenue of the product. For example, in this slide, right now, you can see my radio tab, where I can choose from 4 radio stations: pop rock, indie rock, Russian pop, and metal, specially created for me basing on the songs I've listened to before. Guess which station is my favorite? Continuing. The core component of the Одноклассники recommender system is a taste graph, containing information about different entities, users, tracks, singers, and music genres, and relations between them. For example, user Natasha likes song Take Me Out with certainty 1/4. Track Love Me Tender, created by Elvis Presley. Group Placebo is similar to Group Green Day with certainty 1/8, and so on. Using the graph, it's possible to select tracks a user would most probably like, to arrange them in a way that they match each other well, to estimate which items from a fixed list are most relevant for the user, and more. Thus, soon you will know one more useful application of the graphs. Taste graph is used in order to combine all the information mined from the system, including the history of users' activity and content information. Then, this graph is analyzed by different algorithms in order to construct recommendations and personalized output. The taste graph is an oriented graph with weights associated to its edges, capturing all the information mined from the system. Formally, taste graph G can be defined as a following tuple, where V is a finite, non-empty set of vertices. T sub V is a finite, non-empty set of vertex types, and tau sub V is a mapping function matching each vertex to its type. For example, the type for vertex Natasha is a user, for vertex Green Day it's a singer, and for vertex Rock the type is genre. Having finished with this, we are moving to theta. Theta belonging to V is a zero-balancing vertex used to compensate impact of the vertices with a small amount of outgoing edges. We will in detail talk about it later. Ready for a new step? Here we go. E is a finite, non-empty set of edges. T sub E is a finite, non-empty set of edge types. And tau sub E is a mapping function matching each edge to its type. For example, from vertex Natasha to vertex Love Me Tender, there is only one step, really. Joking. For each, from vertex Natasha to vertex love me tender, the type is like. For the age from vertex ever you and ever me to vertex placeable, the type is created by. For the age from vertex green day to vertex rock, type is belongs to. Shall we go further and speak about R? R is a function matching each edge to its start vertex and end vertex. Edges leading to theta are zero balancing edges. One of the most important parts of taste graph is omega. Omega is a weight function matching each edge to its weight. A set of outgoing edges of a type T from a vertex V is defined as out of V and T. Taste graph G must satisfy the following condition. For all V belongs to set of vertices and all T belongs to set of edge types, sum of omega of E as E runs over out of V and T is equal to 1. Assuming that a graph has only edges of the same type T, you can define its stochastic. Why it's important? Because the graph being stochastic is a necessary condition for every vertex of a graph to have a fixed probability to get to it after quite a big amount of steps. And this probability doesn't depend on the vertex from which you start. These probabilities of getting finally to every vertex of the graph are called stationary distribution. We already talked about it before in the lesson devoted to page rank. Taste graph is called partly stochastic. In order to get a fully stochastic graph, balancing function beta is used. The balancing function must satisfy the following condition. Given the balancing function beta, it's possible to define a balanced weight function omega sub beta as. It's clear that under the weight function omega sub beta, graph G is a stochastic graph. First of all, the role of introducing non-standard construct should be explained. Split of the vertices and edges to different types and partial stochastic allows different parts of the taste graph to be constructed independently and then combined. For example, belonging of tracks to different genres, edges of type track A is a roll one, is constructed on metadata received from partners, while edges of type track B has weight X are constructed by an aggregate function from the overall track ratings. Furthermore, different parts of the graph can be updated at different frequency depending on the complexity of the update and the natural dynamics of the part. Balancing function beta is used to manage the impact of different factors on the overall result. For example, by increasing the weight of user track links, you increase the impact of collaborative recommendations, while decreasing the impact of content-based recommendations. Zero balancing vertex theta plays an interesting role. In the taste graph, the number of outgoing edges might vary from vertex to vertex. For example, track 21 guns might have 5 similar tracks identified, while tracks clouds and Camarillo only 1. Smaller number of outgoing edges typically indicates the lack of statistics and low certainty of the list, but absolute weights on the edges from clouds to Camarillo would be greater than on the edges from 21 guns, increasing the impact of clouds and Camarillo on the recommendations. In order to compensate this impact, the zero balancing vertex is used. This vertex does not match any of the object and has only a self-outgoing edge, but each time when the amount of outgoing edges of type T for vertex V is below limit, an edge from V to theta is added to drain weights from the existing edges. To sum up, after watching this video, you can answer the question, which parts does the taste graph consist of? Hello! In this video, we will learn how edges in taste graph are constructed. As for now, the taste graph for musical recommendations consists of the following parts. First, we will list them one by one, and then we will talk about each in detail. Users' preferences, encoding the relations between users and the items they like, tracks and singers. Singers' similarity, based on the collaborative correlations between singers in the music catalog. Track similarity, capturing the collaborative and temporal correlations between tracks in the music catalog. Singers' tracks, representing a set of tracks produced by a singer weighted by overall popularity. Users' preferences are most dynamic component of the graph. It's updated each time preferences are requested. Preferences, in turn, are composed from different parts. All the history of user playbacks is recorded into a data warehouse and aggregated at a daily basis. Furthermore, there is a running window of the 1000 last played tracks with timestamps in real-life storage, which is also considered. In addition to the playback's history, there is a real-time storage of users' custom playlists to consider. The singer's similarity is created by an analysis of playback's history. Analysis is done in multiple steps. First of all, from a set of all singers, only representative tracks are selected. Then playbacks for these tracks are aggregated in order to get a user-singer matrix. Using a simple correlation measure, a singer-singer matrix is constructed. Finally, outliers filtration algorithms are applied to the matrix, and for each singer, the top similars are selected. To count the track similarity matrix for each pair of tracks, A and B, we use the amount of playbacks of these tracks together in the scope of a limited time window from all users. Then the results are normalized. Finally, the outliers filtration is applied and the top similars are selected. The singer's works are selected from the music catalog metadata, which keeps mapping from track to its main singer and the overall rating of the tracks in the system. Track ratings are analyzed in dynamics in order to put tracks with higher recent interest above the others, even if they have lower overall rating. Additional boost is applied for fast-growing, recently introduced tracks. To sum up, after watching this video, you can answer the question how edges in taste graph are constructed. Based on the data of the taste graph, you can construct algorithms for solving most of the standard recommended tasks. In this video, we will discuss generating recommendations algorithms. This task can be formulated as follows. Given a user U, select a set of items such that the user U would probably most like. Let's use a random walk with a restart model for this task. The main idea of the algorithm is to model a process of random graph traversing, starting from the user's node with the probability alpha to restart at each step. So, generating recommendations for user Natasha will start from the vertex Natasha, then select one of the edges outgoing from this vertex. The probability of selecting each edge is equal to its weight. For example, on the first step of iteration process, you can choose the edge leading to vertex take me out. Think, it's connected with Natasha? You wish. Then you are coming in vertex take me out and choosing which way to go again. But keep in mind that at every step you can restart and return to the initial vertex Natasha. Reminds you of the PageRank algorithm? Exactly. During the lesson 2, we were talking about damping factor D, the probability at any step that the person will continue surfing. Alpha is opposite to D. It's a probability that the process will stop. But both cases model the random walk process with restart. Let's come back to recommendations. The state of the process is presented by a vector x, with the number dimensions equal to the amount of vertices in the chased graph. X sub e is capturing the probability of being in this vertex for each vertex with index e. Given the current state x, the next state of x is calculated as follows, where u is the initial vertex corresponding to the user. Vector u corresponding to the vertex u is a vector with a single one on the position equal to the vertex u index, and the rest elements in it are equal to 0. Next of u is a vector calculated as follows. After quite a big amount of iterations, the random walk recommender will find the stationary distribution. Items with higher stationary probabilities are most likely to be relevant for the user. Thus, selecting the top n items from the vector should be a good choice of recommendations. Let's now take a toy example and take a look how the one iteration of the above described algorithm will be proceed on it. Imagine that our test graph consists of just 5 vertices. All of them you can see in the slide right now. Important to mention that this graph is partly stochastic. Let's initialize a vector x with equal values. Vector u corresponding to the vertex Natasha will have a single one digit on the first position, because the index of the vertex Natasha in our graph is 1. Let's assume that the probability of a restart is equal to 0.15. To count next of x, you should first count next of each vertex v. Let's do it for all the vertices. To count next of v, you should know the balanced weights of all the outgoing edges. And to do it, you need to define the balancing function beta for each combination of vertex type and edge type presented in the graph. In our case, let's do it in the following way. For example, you have decided to make users' appreciation of a singer more valuable than his feelings to particular tracks. You have also decided to make singer's connection with tracks more powerful than the influence of his connection with the other singers for making recommendations. And finally, as the edges in our example can only go from some tracks to other tracks, then the beta function from the track vertex and the edges track will be just equal to 1. Come back to the counting next of vertex Natasha. Now you defined the balanced function beta and can count balanced weights. To count the balanced weight of edge from Natasha to green J, you should multiply its origin weight 0.4 by beta of the user and the singer. So you will receive 0.24. To count balanced weight of the edge from Natasha to Franz Ferdinand, you should do exactly the same using 0.6 as the original weight of the edge. So this time you will receive 0.36. As It's clear from the picture of the graph that Vertex Natasha connected not only with singers, but with track 21 guns. So let's count the balanced weight for this edge as well. It's gonna be 0.4. After we did it, we can count next on Natasha, and according to formulas I've showed you a little bit before, and which you can see again at the top of this slide, it's gonna be 5-dimensional vector with 0 on its first position, 0.4 on the second, 0.24 on third, 0 on the fourth, and finally 0.36 on the last one. How can we interpret this result? 0 in the first position, meaning that you can't return back to Vertex Natasha without restarting in one step. The same meaning has 0 on the fourth position. With probability equal to 0.4, you can go to the Vertex 21 guns. With probability 0.24 to the Vertex Green Jay, and with probability 0.36 to the Vertex Franz Ferdinand. After you finished with Vertex Natasha, you can count exactly in the same way next of Franz Ferdinand Vertex, next of Green Jay Vertex, next of 21 guns, and next of Take Me Out. I will fastly skip through slides containing this now, but you can pause the video and study these calculations in detail. Now, when you know the next state vector for all the vertices in our graph, you can calculate the next state of random walk process using highlighted formula. So, you see now that if the initial probabilities of being in every vertex of the graph are equal, then after one step of the random walk, you will find yourself with probability 0.15 at first Vertex Natasha, with the smallest probability 0.119 at Vertex 21 guns, with probability 0.3298 at Vertex Green Jay, with probability 0.221 at Vertex Take Me Out, and with probability 0.1802 at Vertex Franz Ferdinand. Now we are taking this vector of probabilities instead of the initial one and continue iterations. As far as the following conditions are satisfied: first, graph is stochastic after applying the function beta. Second, it's possible to get from each vertex to any other vertex. And third, the common greatest divisor of all the cycle lengths is equal to 1. Iteration process will converge to the stationary distribution. Let's sum up. Now you know how to solve the generating music recommendations task using the taste graph.
Hello, I'm Pavel. Welcome to the final week of our course. And this entire week will be dedicated to the topic of the Spark application optimization. During this week, you will dig into the execution model of Apache Spark and learn how it performs a shuffle. You will be able to make a difference between narrow and wide dependencies and co-partition RDDs for better performance. You will learn about the fundamental limitations of PySpark and how it tries to overcome them internally. You will learn about the internals of Spark SQL and how the Scalist optimizer works under the hood. You will understand how to debug the execution plan and correct call list if it seems to be wrong. You will learn about the resource management in a distributed system and how to allocate resources to your Spark job. You will also understand the evolution of memory management in Spark and how to use it for your own profit. At the end of the week, you will have a solid understanding of the Spark internals and learn lots of practical methods to optimize your applications like a professional. Are you ready? Let's start. This video will help you refresh and deepen your knowledge about the Spark execution model. Strong understanding of the execution model is essential to create optimal Spark programs. Let me introduce you the dataset which we will use throughout all the lessons of this week. The dataset consists of two tables. The first one contains 10 million rows of logs, and each row has 3 columns: IP address, message code, and message body. The second table contains 100,000 rows, and each row contains an IP address and a source country. Let's imagine that we need to compute the number of messages that have codes warning and error. These can be computed using a simple Spark program. You just read the log file, filter out rows that contain info substring, and finally, a typical MapReduce pattern to emit 1 for each key and reduce by key. As you already know, there are two kinds of operations in Spark: transformations and actions. And transformations take an RDD as an input and return an RDD as an output. So all the transformations in our code can be represented as a sequence of RDDs. But what is an RDD? In the previous lessons, you have learned that an RDD is a distributed collection of objects. These objects are grouped into partitions, which are stored and processed by executors. Spark represents the computation in the so-called lineage graph. It consists of a sequence of RDDs, which are generated by the transformations, and the dependencies between the RDDs. In this example, the RDD returned by the filter transformation depends on the RDD returned by the text file, and the RDD returned by the reduce by key transformation depends on the map RDD. Dependencies are divided into two types: narrow and wide. Conceptually, narrow transformations are those in which each partition in the child RDD has simple finite dependencies on partitions in the parent RDD. Dependencies are only narrow if they can be determined at their design time, irrespective of the values of the records in the parent partitions, and if each parent has at most one child partition. Specifically, partitions in narrow transformations can either depend on one parent, such as in the map operator, or a unique subset of the parent partitions that is known at design time, like coalesce. Thus, narrow transformations can be executed on an arbitrary subset of the data without any information about other partitions. In contrast, transformations with wide dependencies cannot be executed on arbitrary rows and instead require the data to be partitioned in a particular way, for example, according to the value of their key. While sorting, for example, records have to be partitioned so that keys in the same range are on the same partition. Transformations with wide dependencies include sort, reduce by key, group by key, join, and anything that calls the repartition function. The division into narrow and wide dependencies creates stages of execution. This means that a subsequence of a lineage graph, which has only narrow dependencies, can be computed without any data transfer in a nice pipelined fashion. Wide dependencies, which cause data shuffling, create new stages. It is always useful to look at the lineage graph of your Spark job. You can do it in a visual way using the Spark UI. As in this picture, there is the job which has two stages. The first one contains text file, filter, and map as narrow dependencies, and the second one is reduced by key. As a side note, this DAG was generated by the same program that we use, but written in Scala. This is done for clarity, because PySpark does some optimizations which result in DAGs that are hard to understand. We will talk about them later this week. Here is the table of narrow and wide transformation in Spark. You can use a simple rule to remember it. Almost all narrow transformations contain words map and filter. It is worth to note that join may be a narrow transformation if the partitions of the RDD are co-partitioned. We will talk about this situation later. Let's sum up what you've learned. An RDD is a distributed collection of objects. These objects are grouped into partitions, and a partition is an atomic unit of parallelism in Spark. An RDD may have dependencies on other RDDs, and these dependencies can be narrow or wide. Narrow dependencies don't cause data transfer and can be pipelined. Wide dependencies cause data transfers, which are called shuffles. Shuffles are expensive, so they should be avoided, or the volume of the transfer data should be reduced. This video will teach you partitioning in Spark and its effective usage to reduce shuffles. In the previous video, you've learned that wide dependencies create shuffles. Shuffles are data transfers between different executors of a Spark cluster. And in general, shuffles are expensive. If you open the Spark UI of your application and navigate to the page containing the statistics of the tasks that have been executed, you will notice a column called Shuffle Right Size. This is your instrumentation mechanism to spot the shuffle and to measure how much data it has transferred. So, what does Spark do to perform a shuffle? To perform a shuffle, Spark has to answer two questions: what executors to send data to, and how to do it. Let's consider a simple example of a group by key transformation, assuming you have two executors. The first executor has keys A and B. The second executor has keys A, B, and C. To perform the group by key, Spark has to move all the values of the same key to the exactly one executor. So how does Spark know which record to send to which executor? This is done using a partitioner. A partitioner defines how records will be distributed and thus which records will be completed by each task. From the programming perspective, a partitioner is just an interface with two methods, nonpartitions and getPartition. The nonpartitions defines the number of partition in an RDD after partitioning. The getPartition defines mapping from a key to the index of the partition. Returning to our example of the group by key. The definition of the group by key method in the Spark API reference is as follows. Now we know that group by key uses a hash partitioner. It is a default partitioner in Spark, which just hashes keys and sends the keys with the same hash value to the same executor. Another example of a partitioner in Spark is the range partitioner. Range partitioning assigns records whose keys are in the same region to the given partition. Range partitioning is required for sorting, thus ensuring that by sorting records within a given partition, the entire RDD will be sorted. As you see in this example, many transformations do not assign a partitioner to the RDD. In this situation, the default partitioner is created when Spark has to perform a shuffle. But you may also explicitly assign a partitioner to your RDD. This partitioner is called the non-partitioner. This definition becomes useful when you start to optimize shuffles. The first optimization is to co-partition your RDDs. RDDs are co-partitioned if they are partitioned by the same known partitioner. Like in this example, you have two different RDDs which are partitioned by the hash partitioner with 10 partitions. By using co-partitioned RDDs, you can reduce the volume of the shuffle. This means that to make a partition in the final RDD, Spark has to merge only one partition of the parents at a time. The best possible option is to have co-located RDDs. Partitions of the RDDs are said to be co-located if they are both loaded into memory on the same executor. And this could be achieved if you co-partition your RDDs and then persist them in memory. Well, okay. But what should you do if you assign a known partitioner to your RDD but continue to apply new transformations? To optimize your job, you should definitely think about preserving the partitioner. Many transformations have a preserves partitioning argument, which is set to false by default. It becomes obvious for the map method, for example, because map may spill not only new values, but new keys. But if you are 100% sure that your keys don't modify, you can set preserves partitioning to true or use map values, which preserves a partitioner. Summing up, you have learned that a partitioner defines how records will be distributed between the executors. and a partitioner is just an interface which has two methods, nonPartitions and getPartition. The default implementation of the getPartition method is to use hashes computed on the keys of an RDD. You also learned about several partitioner-based optimizations, like co-partitioned RDDs, which have the same non-partitioner that allows to reduce the volume of the shuffle, or co-located RDDs, which entirely avoid it. If you assign the non-partitioner to the RDD, you should definitely think about preserving it if your keys are static and don't change. In the previous video, we answered the first question of shuffle, where to send data to. In this video, we will answer the second question, how to send data. Let's recall that an executor in Spark is just a JVM, holding a bunch of objects in its memory. So, what Spark has to do performing a shuffle is having an object 1 in executor 1 transfer it through the network to the JVM of the second executor. Well, how does Spark do it? Spark uses serialization. Serialization is the process of translating data structures or object state into a format that can be stored and reconstructed later in the same or another computer environment. Basically, it's just a mechanism of representing an object as a stream of bytes, transferring it through the network, and then reconstructing the same object and its state on another computer. Spark provides two serialization libraries, Java Serializer, which is a bit slow but robust, and Cryo, which is fast but has some corner cases. That's why it couldn't be used as a default implementation. Considering Cryo, it is not that useful when you work with RDDs in Python because Python objects already come into JVM as byte arrays, but in some workloads it could still be useful to test Cryo, especially when you can set it as a default serializer, switching one option of the SparkConf object. PySpark is a great API considering the speed of application development, but as it is built on top of Scala codebase, it has some limitations and performance considerations. As you can see on this diagram, PySpark context is a Python interpreter which communicates with the JVM using a socket and Py4j library. Py4j provides mechanism of calling Java methods and wrapping objects. On Spark workers, Python is just a process which starts side by side with the JVM and communicates through Unix pipes. PySpark adds another layer of serialization to computations. At first, Spark has to serialize Python objects and pass them to JVM, where they should be serialized again for Spark's execution model to work. This introduces additional complexity and overhead to your Spark application. PySpark developers realized that this process is quite an issue, so they tried to reduce serialization overhead by pipelining operations inside the Python interpreter. This is great because it allows to speed up programs written in Python, but it also introduces some plug-sum side effects, which you will see next. Let's get back to our example log crunching program. It is a clear and simple example of using map, filter, and reduce by key to count number of log messages of different severity levels. If we look at the DAG, which is generated by the identical Scala program, it is straightforward and easy to follow. As soon as PySpark tries to pipeline operations inside the Python interpreter, and map and filter are always pipelined, you get some weird and uninterpretable DAGs like this. And this is a real downside of using PySpark with RDDs, because it is hard to debug what is happening. Summing up, as Spark is a distributed framework, it uses serialization to transfer data and code. Spark Core uses two serializers. The default is Java Serializer. It is robust because it can serialize pretty every kind of object, but is a bit slow. The other option is Cryo, which is fast, but can't handle several special cases. PySpark is built on top of the core Spark and introduces double serialization. This causes performance issues. PySpark tries to minimize this overhead by pipelining operations inside the Python interpreter, but it produces DAGs that are hard to understand and debug. In the previous video, you have learned that Python API introduces a tangible performance overhead to your Spark app, and how PySpark tries to reduce this overhead by pipelining operations. In this video, we will learn how to reduce this overhead more by optimizing functions used in transformations. While programming with RDDs, you understand that most of the business logic is captured inside lambdas and functions which you pass to different transformations like map or filter. And these functions, being serialized, are really opaque to the core Spark framework. It is your job to implement these functions as optimal as possible to reduce their network payload, startup time, and the number of function calls. We will see what can possibly go wrong with a simple example of a program which just maps some user-defined function to an RDD of objects. We'll make our program a bit tricky by using an object with a really slow initialization and a large memory fingerprint. For example, we can use our function to perform some kind of morphology analysis on text strings using an LTK library. When you initialize an LTK object, it has to read different resources like stop words, different dictionaries, text corpora, and so on. So it becomes a really big, bulky object with lots of dependencies. The worst thing you can do is to encapsulate this object initialization into a function call. This way, your program will do initializations of the object on every function call, and you will also have to provide all the resources needed for the object creation on all the executors. Alright, that was a stupid approach to this problem. Why don't we move object creation outside of the function definition? That is a good point, because object initialization will be done only once on a driver. You won't have to pass resources on executors. Function call will speed up. But Spark will still need to serialize bulky function closure on each executor. Okay, we can use another feature of Spark called broadcast variables. In simple words, broadcast variables are just objects which are distributed by Spark to all the computers in a cluster, and each executor can use these variables during computations. So, you broadcast your bulky object, and then Spark serializes a small function which just uses a tiny proxy object to your broadcast variable. That seems to be an optimal solution, but there is still a problem. Our code uses map transformation, which applies provided function to every row of an RDD. That can be a problem, because we don't save function calls. A much more performant solution can be to iterate over a batch of objects with one function call. Spark provides you with such a mechanism. It is called map partitions. All you have to do is to modify your function to accept iterable as an argument. Your function should also follow the generator interface and yield result instead of returning it. Let's sum up. In this video, you have learned how to implement the optimal solution to a simple task of mapping a function. You have saved on long-running initialization with broadcast variables, saved on serializations by using tiny proxy object inside your function, and also saved on function calls by using map partitions. Alright, let's now use everything you have learned in this lesson to optimize a real-world Spark application. And this will be the PageRank algorithm. You already managed to figure out how PageRank works and also created a solid implementation of this algorithm in Spark. This implementation already uses some smart performance tricks. For example, you know that the links RDD is static and will be used iteratively, so you persisted it in memory. Or you know that reducing the volume of the shuffle is great, so you use the reduce by key transformation to sum up all the contributing page ranks. But, as always, you can do better. We will start with a simple example of a graph with only 5 nodes and 9 edges. This makes things simple, fast, and manageable. As usual, our test environment has 10 executors, each having 2 cores and 4 GB of memory. The input file contains just 9 lines, and we will do 30 iterations. The test run has been finished in 24 seconds. It has generated 63 stages, but more than 2,000 tasks. And it looks a bit strange that just 9 lines of the input produced 2,000 tasks. It becomes pretty obvious why this happens when you look at the DAG, which was generated by the job. It has these repetitive redundant stages marked in red rectangles. And what you want to do is to get rid of these unnecessary shuffles. The cause of these shuffles is the join of the links with the ranks. Why this join generates a shuffle? Simple. Joins just generate shuffles due to their nature. But you know something about this specific problem. You know that links and ranks have the same keys and they don't change. So it may be possible to use this knowledge and optimize things a bit. You know that Spark uses a partitioner to perform a shuffle. In this implementation of the page rank, the links RDD has 2 partitions and a non-partitioner. But the ranks RDD, though having 2 partitions as well, does not have a partitioner. This is not good, because ranks were created by the transformation of the values, not the keys. And that means that the links RDD and the ranks RDD should be co-partitioned. But they are in fact not. Their partitioners are not equal. To make things explicit, we will use the partition by method on the links RDD to introduce a partitioner. We will use 2 partitions as the dataset is small, but we will increase this number later. Okay, you have specified the partitioner, but nothing has really changed. What should you do next? To make your RDDs co-partitioned, you should use the same partitioner for the ranks. It can be achieved by preserving the partitioner in the map transformation. As you see, both RDDs now have a non-partitioner, and they are equal. Are we done? Not quite. The ranks RDD is modified in the for loop using the page ranks of the contributing links. And this modification is done by the reduce by key transformation, which also needs to do a shuffle. But if you ensure that the reduce by key generates the same number of partitions in the rank RDD as before, everything will be okay. One final note. The damping factor is applied via the map values transformation, which preserves the partitioner. If this was done with the map transformation, you would have to explicitly preserve the partitioner. Great! The final implementation is here. It is mostly the same as before, with only 3 minor modifications. Let's test it. As you see, the execution time has halved, as well as the number of stages, and the number of tasks has decreased 31 times. Now, Spark UI tells you that there are no redundant stages, and everything that is happening is the same stage recomputing the ranks on each iteration. Let's now test your modified solution on a realistic problem. We'll use the Berkeley-Stanford web graph, which contains about 700,000 nodes and more than 7 million edges. The algorithm will iterate 5 times. The first implementation, which did not use all the partitioning optimizations, has been finished in 4.1 minutes. And the optimized solution took 3.5 minutes to finish, which gives an increase in performance by about 20%. And that is pretty great because the algorithm used just 5 iterations, which is too small for a web graph of this size. So, summing up, the most important thing you should care about in your Spark applications is reducing shuffles. You may achieve this if the partitioners of RDDs are known, and it is better to explicitly assign a partitioner. If your transformations do not change the keys, you should preserve the partitioner. And if your job has to shuffle, make sure that you decrease the volume of the shuffle by using the appropriate transformation, like reduce by key. In this lesson, we will talk about Spark SQL. We will try to answer the following questions. Why was Spark SQL implemented? Why is it promoted as a default API to develop applications? How does Catalyst optimize your applications? And what are other tricks to boost performance of Spark SQL programs? So, to start, I'd like to talk about motivation of integrating SQL into Spark framework. And to be more specific, let's recall our log crunching program. As a quick reminder, you have two files. One contains 10 million lines of log messages and has 3 columns: IP address, message code, and message body. The second file contains a table of 100,000 rows with 2 columns: IP address and the source country. What you want to achieve is to collect the distribution of warnings and errors across countries. And we'll start with the version using plain SQL. As you know from the previous lessons, SQL is in declarative paradigm, which means that you don't exactly perform computation that should be done to get a result. Rather, you just specify constraints on the result and the structure which should be applied to the result. You can achieve this goal by this simple query, which joins 2 tables on the IP column, filters out info messages, and finally takes just 2 columns: country and code. So, this is pretty straightforward, and I think that every person who works with data knows SQL more or less to understand this particular query. Next, we will recall the RDD API and see how to implement this same task using it. You have already guessed that the RDD API is an imperative one, so you have to specify each step of the computation to perform to achieve the result needed. This is a piece of code which is equivalent to your SQL query using the RDD API. You start by reading both text files, then apply some kind of schema, as you know that these files are TSV files with the particular columns. Then you perform the Cartesian product, which is the simplest form of doing joins using Spark. Then you filter out the records, which don't have the same IPs, and filter out info messages. And finally, you do a projection of the requested columns. As our lesson is about performance of Spark apps, let's see how these 2 implementations perform. The test environment is as follows. The first table has 10 million rows of logs, which take up around 500 megabytes on disk, stored in 20 partitions. The second table has 100,000 rows of IP addresses, which take up 2 megabytes on disk, stored in 2 partitions. Our Spark application has 10 executors, each of which has 2 cores and 4 GB of memory. Let's start with the imperative implementation. As you see, I could not wait for this job to be finished. 2 hours passed, but only 8 tasks of 40 have been executed. This is the price you pay for using a Cartesian product. Now we get to the SQL implementation. Using the Spark SQL API, you register temporary views and then just execute the SQL query we talked about in the beginning. And this computation has been completed in just about 6.6 seconds. Just to compare, more than 2 hours using the imperative computation and just about 7 seconds using the declarative one. That's a pretty cool result, and that means that something is going under the hood which can optimize this computation well enough to get about 100x performance boost. So, what is actually happening? Why is Spark SQL able to do its job so well? To start with, RDD is a low-level API, as you already got from the first lesson. And that means that you have to specify each step of the computation yourself, and you have to think about the performance optimizations beforehand. To not generate unnecessary data, to not make redundant operations, and so on. And the main downside is that you have to do it over and over again, even for the simplest cases which are easy to automatically optimize. For example, if you look at our first straightforward implementation, you know that the Cartesian is a bad choice because it generates tons of unnecessary rows. Thus, you can redefine your computation to use the inner join, which automatically skips rows with the unmatched keys, reducing the volume of data to be processed. And if you look at the performance of this implementation, you will see that it took only 13 seconds to compute. The previous, straightforward version used more than 2 hours to compute, and this version, which was slightly optimized by an obvious transformation, performs much better. But it is still not as performant as the Spark SQL implementation, which took just 7 seconds. And why is it so performant? Because it restricts you to use only the expressions and operators which it knows, and because it knows the structure of your data. Let's understand it step by step. When using RDD, Spark knows nothing about your data. If you consider the SQL query in the context of a database management system, the DBMS knows what columns your tables have and what are their types. And it knows from the query that it only needs to use 3 columns: IP, country, and code, thus reducing unnecessary reads and redundant computations. And if you implement your solution using the RDD API, what Spark sees is just a bunch of unstructured text files. So the best it can do is to just read these files line by line and feed it to your functions. And it is your functions which apply schema to the data. Like in this example, a map transformation projects data onto the subset of the necessary columns. The second point here is that using the RDD API, Spark knows nothing about your computations as well. So in this query, you see that there are just predefined operators like select or join, and expressions that are implemented in SQL itself. And all these computations are available to the query optimizer, which can use this information to provide the fastest execution plan. And if you look at the same thing in the RDD program and recall what you learned in the previous lesson, the computations are opaque. And what really happens using PySpark is that Spark gets your lambdas as serialized byte arrays, and the best it can do is just apply it to each row or partition of the data. So, to wrap up, what is the motivation of implementing Spark SQL as far as I consider it? The first point is RDD is imperative and low level. This means that you must specify each step of your computation, and there is no way to optimize these steps by reordering or substitution. And if you don't think about the performance, no one will do it. But thinking about the performance all the time is really tiring, especially in obvious and simple cases. And the second point is opaque computations and data. So Spark can't even prune the unnecessary columns because it is your computations that define the shape of the data. And basically, the only job of Spark here is to transfer your lambdas back and forth, applying them to black box data rows. But Spark SQL, which restricts you to using operators and expressions provided by the API, and which enforces you to specify the schema of your data, has all the knowledge to generate the best possible execution plan. In this video, we will talk about the core component of Spark SQL, the Catalyst Optimizer. We will start our discussion by introducing a slightly modified version of the query from the previous video. This query uses the group by operator and computes a simple aggregate. To debug the performance of Spark SQL application, it is useful to look at different execution plans, which can be done using the explain method, providing true as the value of its single argument. If you do that, you'll get a bunch of different plans generated by Catalyst. Let's figure out what those plans are and what is going under the hood. This is a graph of the optimizer's pipeline. Catalyst starts with a SQL query or a computation written using the DataFrame API, which is then parsed into unresolved logical plan. This plan is unresolved because at this stage the framework knows nothing about tables and attributes in a query. To get this information, Catalyst uses a catalog, which could be an HDFS metastore or a DBMS. The plan is resolved and Catalyst starts to optimize this plan. When a logical plan is optimized, Catalyst generates a bunch of physical plans, which are then evaluated using a cost model, if appropriate. And finally, the most performant physical plan is used to generate the actual executable code. This pipeline looks pretty complicated and involved, so we will simplify it to understand how plans are transformed. To make optimizations, Catalyst uses a neat abstraction of users' programs using trees. And all the optimizations are done as, in most cases, simple transformations of one tree to another. So basically, Catalyst consists of three components: a general library for representing trees and manipulating them. Then it contains libraries specific to relational query processing. And there are also different sets of rules or transformations that handle different phases of a query execution. Let's look at a simple example. As you already know, tree is the main building block of Catalyst. We will imagine a tree which may consist of nodes of three types: literal, which is just an integer constant; adder, which represents an identifier; and add, which arithmetically adds left and right subtrees. You have an expression x plus 1 plus 2. This can be represented as the following evaluation tree. We already mentioned that Catalyst performs optimizations by transforming trees using rules. One of these rules is called constant folding and evaluates constants at optimization time to reduce computations. As Spark is written in Scala, a probable piece of code could look like this, which applied to a tree folds the right subtree of a root node into a single constant, producing a new simplified tree. And Catalyst implements a whole load of these transformations. Some of them are grouped into sequences and may be applied to trees using different strategies, for example, exactly once or recursive. Let's get back to our log crunching query. As you remember, the explain method returned 4 different plans: parse logical plan, analyze logical plan, optimize logical plan, and physical plan. Let's follow Catalyst's pipeline with this example. First 2 logical plans can be represented by this tree. You need to scan 2 tables, join them, filter out unmatched keys and info messages, project needed columns, and finally aggregate. Let's now introduce the second real rule of Catalyst, called filter pushdown. Looking at our query, it is obvious that you should not read all the records from the table with logs, because most of them are info messages. And Catalyst rules are smart enough to get these, and if storage layer allows, Catalyst pushes filter as close as possible to the bare metal. Filter pushdown, when applied to the unoptimized plan of our query, produces the tree on the right. And if you look at the actual output of the optimizer for this query, you will notice this transformation in the optimized logical plan section. One final stage before the code generation is to produce a physical plan, or if possible, several physical plans, and evaluate them according to the cost model. We will talk about this later this week, but for now, the optimized logical plan of our query may be transformed into the following physical plan. Scans are now file scans with the CSV option. Join is performed using the broadcast hash join. This has happened because the second table, containing the mapping of IP addresses and countries, is really small. And group by is implemented using the familiar hash partitioner. Summing up, you learned that Catalyst is the Spark SQL query optimizer. Its pipeline consists of 4 major steps which produce execution plans. Execution plan is represented as a tree, and basically, Catalyst is a library for working with trees which implements transformations on them. You also saw 2 examples of the real transformations: constant folding and filter pushdown. In the previous video, you have learned about the theoretical aspects of how Catalyst Optimizer works. In this video, you will see how it works in practice on a real example. Let's slightly modify our well-known log crunching program. What we want to do now is to count the number of log messages each country has generated. So we will perform the usual join, filter out info messages, group by countries, and then count the aggregate. Let's recall the Catalyst pipeline. It consists of several steps: an unresolved logical plan, a resolved logical plan, which uses an external catalog to get the information about the tables. Then Catalyst performs transformations to produce an optimized logical plan and generates several physical plans. Finally, physical plans are evaluated using the cost model, and the best physical plan is used to generate the code. If you represent the query as an abstract syntax tree, you will get something like this: 2 scan operations at the bottom, then join, filter, projection, and finally count in the aggregate. To get the execution plan in Spark, you should use the explain method of the data frame. If you call it with the argument set to true, it will output 4 blocks that match 4 execution plans in Catalyst. Let's look at the plans of your query. At first, the unresolved logical plan. It is called parsed logical plan in the output. As you can see, it is your abstract syntax tree. 2 scans at the bottom, then join, filter, and count in the aggregate. But as you see here, there are unresolved relations, table 1 and table 2. At this point, Spark does not know what are those tables, where they are located, and how to read them. The other thing you should notice here is that the join is performed before the filter. This is not the optimal solution, and you will see if Catalyst could resolve this issue later. The second step of the optimizer is producing a logical plan. It is called analyzed logical plan in the output, and what you see here is the unresolved tables from the previous steps are now resolved. Spark now knows that they are located in Parquet files and have schemas shown in square brackets. The third step is the optimized logical plan, and at this step you will see the examples of the different optimizations which are performed on the query. The first one, and probably the most important one, is the filter pushdown. If you recall the previous video, filter pushdown is the transformation of one tree into the other. On the left side, join is performed before the filter operation, but you know that you should filter the unnecessary data before joining to reduce the volume of the shuffle performed. So, if you look at the optimized logical plan, you will notice that the join operation is now performed after the filter, and the filters are pushed down to the bottom. You should also notice the predicates which are used to filter the data. There are the predicates on IP columns because join is performed on them. And also, there is the predicate on the code column to filter out info messages. The last major step of the Catalyst pipeline is producing the optimal physical plan. The chosen physical plan is shown as the 4th block of the explain output. It is called physical plan. Here you see that there are 2 scan operations from the Parquet files, and those filters were pushed down to the bare metal. Actually, these filters are pushed down to the layer which reads from the file, and this is the most optimal thing you can do. What you should also notice when looking at the physical plan is what join algorithm is chosen. You will learn more about joins in the next videos, but for now, you see that Catalyst has chosen the broadcast hash join, which is the fastest algorithm to perform because it does not do any shuffle. Another important thing you should take care of is column pruning. As you know, the table with the logs contains 3 columns: IP, code, and message. But our query does not use the message column at all, so Catalyst eliminated the message column from the file scan, thus reducing the volume of the data to be processed. To sum up, when you use Spark SQL, you should always look at the execution plan produced by the explain method. What should you check in the first place? You should definitely check whether filters were pushed down, because it may dramatically reduce the volume of data to process. If, for some reasons, Catalyst did not push the filters, you should check if Spark SQL Parquet filter pushed down, or Spark SQL ORC filter pushdown configuration option is enabled. The second thing you should check when looking at the execution plan is the join algorithm. And the third thing to check is whether the unnecessary columns were pruned. Let's start the discussion of joins in Spark by understanding how joins could be implemented in general. This new knowledge will help you to understand different physical join plans in Spark SQL. Let's state the problem. You have two tables and a join predicate on the columns on these tables. Your algorithm should return a new table which contains rows from both tables, and the join predicate for these rows evaluates to true. What are the possible solutions for this problem? Basically, there are three of them: nested loop join, hash join, and sort merge join. Let's now look at them closer. The first algorithm which probably comes to your mind is nested loop join. It is really simple. You have an outer loop to iterate through the rows of the first table and an inner loop to iterate through the rows of the second table. And if both rows match the join conditions, you yield a new row. Nested loop join is a really universal algorithm. It does not use any extra memory. It supports any kind of join conditions, but having a quadratic complexity, it is really slow. The second algorithm is the hash join. The hash join is an obvious optimization of the nested loop algorithm, because when you try to optimize some quadratic algorithm, you come with the idea of using a data structure with a constant complexity. And in many cases, it is a hash map. The hash join takes the smaller table in a join and creates a hash map of it, and then loops through the rows of the larger table, trying to find rows in a hash map. The problem with the hash join, though it is a fast algorithm, is that it needs to create a hash table. And if both of your tables are huge, it is a bad decision. The other problem with the hash join is that it supports only equijoin, which is a predicate which tests values for equality. The third algorithm is the sort merge join. It consists of two steps. The first one sorts values of the columns used in the join predicate, and the second one loops through both tables simultaneously, merging the appropriate rows. The sort merge join is a little bit slower than the hash join, but it does not need to use an extra data structure. The other benefit of the sort merge join is that it supports not only equijoins, but other types of join predicates. But, as the name implies, sort merge join can work with keys of sortable types only. Summing up, there are three main implementations of join algorithm. The nested loop join is a universal but slow algorithm. The hash join is fast but needs to create a hash map for one of the tables and can't be used for huge tables. Also, it supports only equijoins. The sort merge join is slower than the hash join but can be used for huge tables because it does not use any extra memory. It also supports different join conditions. Now, after you have learned about the algorithm to perform a join and their advantages and disadvantages, we will continue with joins in Spark and learn the ways to optimize their performance. There are four physical plans of joining in Spark: the broadcast join, the shuffle hash join, the sort merge join, and the broadcast nested loop join. Let's start with the sort merge join. As you already know, the sort merge join is a pretty fast algorithm which can be used to join huge tables. That's why it is the default joining algorithm in Spark. It is turned on by the configuration option Spark SQL join prefers sort merge join, which is true by default. But as you already know, keys for this type of join must be sortable. Let's recall our log crunching program and join data frame of logs with the data frame of IP addresses. If you call the explain method on this query and look at the physical plan, you will see that Catalyst used the sort merge algorithm. The second type of a join physical plan is the shuffle hash join. The shuffle hash join is used when the join key is not sortable or the sort merge join is disabled. One side of the plan should also be much smaller than the other, and Spark should also be able to build a local hash map. So, what does it all mean? These are the actual functions implemented in Spark. Though they are in Scala, their implementation is simple to understand. Can build local hash map returns true if the estimated size of the one side of the plan is smaller than the product of the number of partitions used to perform the join and the threshold for the automatic broadcast. The second function is called much_smaller, which returns true if the estimated size of the one side of the join is 3 times smaller than the other side. This means that if you're absolutely sure that using the shuffle hash join is good for the performance of your app, but Catalyst thinks differently, you can trick Catalyst by changing the values of the Spark SQL auto-broadcast join threshold, which is 10 megabytes by default, or by changing the default number of partitions for joins. And finally, there is the broadcast join. It is the best possible option for a join in Spark, because it does not perform any shuffle at all. To use the broadcast join, Spark has to figure out if it can broadcast one side of a join at all. If it can, then the broadcasting happens and map side join is performed. So, how does Spark answer the question if it can broadcast? It simply looks at the value of the configuration option Spark SQL auto broadcast join threshold. So, if Catalyst tells you that it won't use broadcast join, but you are sure that broadcasting one of the data frames and performing broadcast join will be faster, you can either change the value of this option or hint Catalyst with the function broadcast, which is in the PySpark SQL functions module. So, what happens if we use the broadcast hint for our log crunching join? Well, as you see, the execution plan has changed, and it now uses the broadcast join instead of the sort-merge algorithm. When you use joins in Spark SQL, you should definitely keep in mind the level of parallelism, which is 200 partitions by default. You can increase the level of parallelism by tuning the option Spark SQL Shuffle Partitions. But this, however, does not help you with the skewed data. If your keys are not distributed evenly, then you may get stragglers. We will talk about stragglers in the third lesson. For now, you may fix the problem of uneven data distribution and increasing the level of parallelism by using the repartition method. Let's sum up what you have just learned. The default physical plan of a join in Spark SQL is the sort-merge join, but it has a disadvantage that keys must be sortable. The other option is the shuffle hash join, which is used when one side is much smaller than the other, but you can force Catalyst to use the shuffle hash join if you are absolutely sure that it will boost the performance. And the third option is the broadcast join. It does not perform any shuffle because it is a map side join, but one of your data frames should be really small to be broadcasted. Anyway, you can hint Catalyst to use it to speed up your app. And the last thing you should keep in mind is the level of parallelism of your joins, especially if they are large. You may increase the default number of partitions via the configuration option or use repartition if your data is skewed. In this video, you will learn about user-defined functions and how to optimize them. As you already know, Spark SQL is a restricted API, and by being a restricted API, it can be fast. But there are some situations when the provided API is not enough, so you need to somehow extend the API to make it do what you want it to do. We will talk about UDFs using a simple example. In our log crunching program, we join two tables using the IP column, and in these tables, IPs are stored in the .decimal format. Now, let's perform a simple inner join on these tables using the IP column and see how much time it takes to compute. The configuration of the Spark app is the same as before, except the tables are now stored in the Parquet files compressed with Snappy. This simple join on the IP column took just 2 seconds to compute. But let's imagine that you have to join the data frames not on the dot decimal representation of IPs, but on their numeric representation. To achieve this, you have to implement a function which converts the dot decimal value to the numeric value. This can be done with the user-defined function. PySpark SQL Functions module contains the function called UDF, which is used to convert your arbitrary function into the appropriate UDF. You call it with your function as the required argument and can also specify the return type. As a return value, you get the column expression, which can be used in the DataFrame API. The piece of code at the top implements the function that converts IP addresses. Then you create a UDF with the return type of integer and add a new column, IP to int, to both data frames. If you join the data frames on the value of this new column, it takes around 10 seconds for the job to be finished. This is 5 times slower than the first join. So, why does this happen? As you already know, Spark SQL avoids almost all communications with Python. Being a restricted API, Spark SQL can do all the computations inside the JVM, and there are no expensive round trips to the Python interpreter. But when you use a UDF implemented in Python, you force serialization because Spark needs to apply your UDF to a column of a data frame. Well, what are the options you can use to speed up your UDFs? The general answer to this question is to not use Python at all. And this leads to the following solutions. The first one is to use functions which are available in the PySpark SQL Functions module. These functions are just wrappers to the functions implemented in Scala, so they are fast. The second solution is to use UDFs and UDAFs that are available in Hive. There are plenty of them, and you can learn more in the Hive documentation. And finally, if you haven't found the function which does what you want, you can implement it in Java or Scala and use in PySpark. Let's see how it is done. I have implemented the conversion of IP addresses in a Java function called IP to int. You can find its source code in the supplementary materials. What you have to do is to add the jar file with the compiled function to the Spark context and then register a temporary function. There is a problem though. You can't use a UDF implemented in such a way in the DataFrame API. The only option available is to use it in a SQL query. Okay, no problem. Let's register our data frames as temporary views and write a query which joins these tables using the column IP to int created by our UDF. And if you execute this query, it will be finished in about 4 seconds, which is 2 times slower than the original vanilla join, but around 2.5 times faster than the UDF implemented in Python. Let's sum up. Spark SQL can be extended via user-defined functions or user-defined aggregate functions. But if you implement your UDF in Python, it forces serialization, which slows down your application. The solution to this problem is to use non-Python UDFs. You can use functions which are available in the PySpark SQL Functions module or functions implemented in Hive. If you can't find the appropriate function there, you can implement the function in Scala or Java and use it in your Python code. In this video, we will talk about persistence and checkpointing, and look at them as the ways to improve the performance of several kinds of workloads. As you know from the previous lessons, all Spark computations are represented as lineage graphs. Different parts of job computations are connected by dependencies, and computations are lazy. To trigger a computation, you have to call an action on RDD or data frame, for example, count. This makes Spark start from the beginning of the graph and compute result step by step, partition by partition. The point here is that if you have the same lineage but call another action, for example, collect, Spark will recompute the whole graph even though nothing has changed. And this thing can be really bad for several types of computations. For example, if you have an iterative algorithm which loops through stable pre-computed data like machine learning algorithm. That's why Spark provides you with a method to actually store intermediate result of a computation, and this is called persist. RDDs and DataFrames have a persist method which does the following. At first, it computes the whole lineage graph and then stores partitions of an RDD or data frame in some place. And actually, when you call an action on a persisted data, nothing happens except computing this only action. For example, if you call a count method on a persisted data frame, everything Spark has to do is count rows in stored partitions. And if you call collect, Spark doesn't have to recompute the whole thing. It just transfers data to your driver program. Interesting thing here is that persisting is not a reliable method to store results, but it is robust. So, if you have a data frame consisting of several partitions on different executors, if one or more executors fail and are restarted by the resource manager, Spark will recompute lost partitions, but will not recompute those which are in order. When you persist, you have to choose where to persist the data. There are three kinds of storage levels available in PySpark. The preferable one is memory only. Your executor has some reserved memory for persisting, and when you choose memory only, Spark tries to save partitions in this part of memory if there is enough space. There is also a memory only 2 option, which provides a bit of redundancy by storing 2 replicas on different cluster nodes. The second level is memory and disk. Basically, Spark tries to store as much of data as possible in memory, and if there is not enough space, it will spew records to disk. This, however, introduces performance considerations because disk's I/O is pretty slow. And the third level is disk only. In this mode, Spark writes data to disk and doesn't store it in memory. So, what do you have to keep in mind when using persistence? Spark is an in-memory framework, and you have to keep it so for the best performance. That's why store your partitions in memory if they fit. And even if it does not fit, you should probably think about increasing the memory of your executors. The second thing to consider is that recomputing results may be as fast as reading from disks. So, in several scenarios, you may not need to persist at all and let Spark recompute things. And this will not affect the performance of your job. And finally, if you use some kind of iterative algorithm, like machine learning algorithm in case of all specialization, you should definitely think of persisting the results of intermediate computations, like training dataset. Okay, as I have already mentioned, when you persist, intermediate results are stored in the memory of an executor or on disk of an executor. So, actually, if an executor fails, Spark has to recompute partitions of the particular executor from scratch. But your cluster can be really crowded by different jobs and users, and the resource manager will not allocate new containers for this recomputation. This situation may dramatically increase the running time of your job. That's why Spark provides you with the mechanism of a reliable persistence called checkpointing. When you checkpoint, Spark writes partitions of an RDD or a data frame to a reliable storage. And this storage is HDFS. And another interesting thing with checkpointing is that it also truncates the whole lineage graph which produced this intermediate result. To make a checkpoint, you need to specify a directory in HDFS where to store the data, and then call checkpoint method of an RDD. And the caveat here is that you can't checkpoint a data frame. For a data frame, you have to checkpoint the underlying RDD. So, when to make a checkpoint? You should definitely think about checkpointing in a noisy cluster. Cluster is called noisy if there are lots of jobs and users which compete for resources, and there are not enough resources to run all the jobs simultaneously. You may think about checkpointing if your computations are really expensive and take long time to finish. because it could be faster to write an RDD to HDFS and read it back in parallel than recompute from scratch. And as a slight inconvenience, there is no way to checkpoint a data frame, so you have to checkpoint the underlying RDD. So, to sum up, in this video, you learned that Spark provides ways to store intermediate results by persisting or checkpointing. It helps to speed up several kinds of workloads, like iterative algorithms in general, and machine learning algorithms in particular. You have learned that persisting is unreliable. If an executor fails, Spark has to recompute its partitions. And checkpointing is reliable because it stores data in a reliable HDFS. Now you also know that checkpointing is slow because you have to write data to HDFS. And persisting may be slow if you use not only the memory but the disks for persisting as well. In the previous video, you learned that Spark uses an executor's memory to store persisted partitions. And now you will dig deeper into Spark's memory management and know how it is done under the hood. There are two kinds of memory in Spark: the execution memory, which is used to store temporary data of shuffles, sorts, and aggregations, and there are also the storage memory, which is used to cache RDDs and data frames. How does it look? Your executor has some amount of total memory, which is divided into two parts: the execution block and the storage block. This is governed by two configuration options. The first one is Spark executor memory, and it is the total amount of memory which is available to your executors. It is 1 GB by default. And the second one is Spark memory fraction, which is a fraction of the total memory available for execution and storage. In early version of Spark, these two kinds of memory were fixed, and if your job was to fill all the execution space, Spark had to spill data to disk, reducing performance of the app. On the other hand, if your app relied heavily on caching and your job filled all the storage space, Spark had to evict cached data, and this is done using least recently used strategy. This strategy frees blocks with the earliest access time. This approach had a natural fallacy. If your app does not use caching a lot, an executor has some free memory available, but as the execution part is fixed, you reduce performance of the job anyway. And starting with version 1.6, Spark introduced unified memory management. That means that execution and storage are not fixed, allowing to use as much memory as available to an executor. Two premises of the unified memory management are as follows: evict storage, not execution. This is pretty obvious because if you evict the execution data, you will definitely read it back soon. And if you evict the cache data, you probably won't use it anyway. The second premise is that unified memory management allows the user to specify the minimum unevictable amount of data for applications which relies heavily on caching. The minimum unevictable amount of data is defined using Spark memory storage fraction configuration options, which is 1/2 of the total memory by default. Let's sum up what you've learned. There are two kinds of memory in Spark: the execution memory and the storage memory. In older versions of Spark, these two blocks were fixed, which led to performance issues. If execution memory was full, Spark had to write data to disk, which is expensive. On the other hand, if your app cached a lot, Spark had to evict least recently used blocks of data. Evicting execution memory is less desirable because Spark has to read it back anyway. That's why, in Spark 1.6, unified memory management was introduced. This management strategy does not fix the size of execution and storage memory, but allows you to specify the minimum unevictable storage, which allows to fine-tune several kinds of workloads. In this video, we will talk about how to allocate resources for your Spark app. When you try to run your application on a Spark cluster, you need to make several decisions. How many executors should you allocate? How many cores should each executor have? And how much memory should each executor use? In this video, we will try to answer these questions and to provide you with some tips on provisioning Spark resources. For simplicity, we will consider a small cluster of 4 nodes, each containing 16 cores and 64 gigs of memory. By saying gig, I mean gigabyte, of course. To start with, you may try the most granular approach. In this case, each executor gets only 1 core, and one node has 16 cores. That means that you start your app with 64 executors, each having 1 CPU core and 4 gigs of memory. And it turns out that this is not a right solution. Because if you recall a simplified architecture of Spark, you have a driver program which contains Spark context and schedules tasks. You have a cluster manager, which is a program allocating containers to your executors, for example, Yarn. Then there are a bunch of worker nodes, each starting 1 or more executors. And finally, each executor is a JVM which can process several tasks. Multiple tasks are processed as separate JVM threads. This allows to reduce an overhead on starting and initializing an executor. So, if you allocate only 1 core to each executor, you can't use these benefits. Well, okay, the most granular approach is not good. So, why won't you use the least granular approach? You will start only 4 executors, and each executor will get all cores and memory of a node, making a JVM as parallel as possible. In practice, this is not the right answer again. To learn why this answer is not right, you should remember about Resource Manager. There are a bunch of resource managers available for Spark. You can start Spark as a standalone cluster and it will manage its resources itself. You can use Mesos, or you can use Yarn, which is a resource manager implemented in Hadoop starting from version 2. In this video, we will concentrate on Yarn because it is the most widely used resource manager. So, if you look at the architecture of an app developed for Yarn, you see that there is a master node which contains the resource manager itself and a scheduler. There are also slave nodes, and each node contains the so-called node manager. Node manager is a Hadoop process which communicates with the resource manager and allocates containers on this particular node. So, basically, you need to leave resources for this node manager daemon and other auxiliary Hadoop daemons. Now, getting back to the least granular approach, you will leave 1 core and 1 gig of memory on each node for these daemons, and get the following solution: 4 executors, 15 cores each, and 63 gigs memory for each executor. But this is also not quite right. Because if you look at Yarn app architecture, there is also an application master. The application master is a container which communicates with your driver and sends resource allocation requests to the resource manager. So, you already got it. If the application master is a container, you have to leave resources to start it. The other consideration you should keep in mind is HDFS throughput. If you really allocate 15 cores per executor, this can dramatically decrease the performance of your job if it reads from HDFS or writes to it. And the rule of thumb is to use 5 cores per executor. There is also a third consideration. Spark executor is a JVM. JVM has a heap memory and an off-heap memory. In case of Spark, an off-heap memory is used for direct buffers. So, when the application master sends resource requests to the resource manager, it gets total memory, which you specified with Spark executor memory, and adds space for off-heap storage. This space is configured with Spark Yarn executor memory overhead option and is about 10% of total memory by default. Now, you know all the needed information to provision your Spark job as a master. One node has 16 cores and 64 gigs of memory. You subtract 1 core and 1 gig for the node manager and auxiliary daemons. You fix your executor to 5 cores for the best HDFS throughput, and that means that if you divide 60 cores available by 5 cores per executor, you will get 12 executors. You leave 1 container for the application master. 63 gigs of memory per node divided by 3 executors per node results in 21 gigs per executor. But, counting all the off-heap storage, this results in 19 gigs. And the final answer could be that you start your app with 11 executors, 5 cores each, and 19 gigs of memory. You may read more details about fine-tuning of your Spark jobs following the link below. Let's sum up. How do you allocate resources for your Spark app? The least granular approach is not good, because it does not use JVM's parallelism. The most granular approach should be tried with care, because you need to leave resources for the operating system and Yarn daemons. You need to leave one container for the application master. For the best HDFS throughput, you should allocate no more than 5 cores per executor. And also, you have to leave space for the off-heap storage of your JVM. In this video, we will talk about dynamic allocation. In the previous video, you tried to answer the following question: how much resources should you allocate for your app? And it turned out that you actually had to answer 3 questions. How many executors should you start? How many cores and memory should each executor have? That's quite a few decisions to make to start a job. It happens that Spark allows you to skip one of these decisions with the mechanism called dynamic allocation. So, how does this work? For simplicity, suppose you have a cluster which can run 12 executors of a fixed size. At the beginning of the day, your colleague starts a Jupyter notebook which allocates 9 executors to compute an expensive analytical query. But then he remembers that he has forgotten to grab his morning coffee and goes to the kitchen to pour some. His Jupyter session is still there on a cluster holding 9 executors which do nothing. Then you come to the workplace and want to start a simple job with just 4 executors, but you fail because only 3 executors are available, although the cluster does nothing. Dynamic allocation handles this situation by deallocating idle executors and starting new executors if your job needs them. So, if dynamic allocation is turned on, Spark will kill several idle containers of your colleague and your job will successfully start. So, why does Spark need dynamic allocation of resources? Classical MapReduce frameworks use short-lived containers for their tasks. But Spark architecture assumes long-running containers to speed up computations. And this may not be the optimal approach in shared and noisy clusters. So, how do you configure dynamic allocation in Spark? The main option is Spark Dynamic Allocation Enabled, which is false by default. Then, you should also specify what is the idle timeout of your executor, meaning how much time should pass for executor being idle before Spark removes it. It is 60 seconds by default. There is also another important option which is forgotten all the time. You now know that you can speed up your job by caching data. And if this executor has cached data, Spark can't remove it because cached executor idle timeout is set to infinity by default. So you really have to tune this option for dynamic allocation to work at all. 2 other options are min executors and max executors. Minimum number of executors which are allocated to your job are 0 by default. This means that you may come up with a situation when your app is running only the driver and no executors at all. This behavior may not be desirable. Maximum number of executors is not bounded, so you may or may not want to tune this option. Another important thing to keep in mind with the dynamic allocation is that executors have a piece of memory for execution. We talked about this in one of the previous videos. This means that the results of the shuffles, aggregations, and joins are stored in this memory. And if Spark removes an executor, your job will definitely lose this data. To prevent this, when your cluster runs on Yarn, you have to enable an external shuffle service in Spark, and also point Yarn to this external shuffle service. So, What are the use cases for dynamic allocation? The first one are long-running ETL jobs. These jobs start on a regular basis and process batches of new raw data. As soon as data generation is some probabilistic process, each start of the job will deal with different volumes. The second one, and the most useful for our course, are interactive jobs like Jupyter notebooks. Due to the nature of analytical work with data, it is best to use dynamic allocation here. And the last one are jobs with large shuffles. So, let's sum up. Spark architecture assumes using long-running containers for speed. This may cause underutilization of the cluster resources. And that's why dynamic allocation can help. Dynamic allocation starts new executors when they are needed and remove executors when they are idle. But dynamic allocation requires fine-tuning of your job, and you need to pay attention for different configuration options. Finally, due to the dynamic nature of this strategy of resource allocation, temporary shuffle results should be stored in an external service. More information on dynamic allocation is available in these talks. In this video, we will talk about speculative execution in Spark. MapReduce was designed to run distributed applications on clusters of commodity hardware. And this may cause a phenomenon called straggler. A straggler is a task which runs significantly slower than all the other tasks. And so, as the performance of the distributed application is upper bounded by the performance of its slowest task, stragglers cause your app to underperform. What are some common reasons for stragglers? The first option, and the best one, so to say, is equal workload but unequal resources. For example, if you have a workload of partitions with roughly the same size, but your cluster consists of unequal nodes. Some are computational powerful with top-notch CPUs and SSDs, but some are outdated and slow. The second option is when you have a cluster of the same nodes and equal resources, but your workload is not uniform, having several partitions which are significantly larger than the others. And the third reason is everything else. Your program may have bugs, stragglers may appear by chance, and so on. We will not consider this option. Let's look at what a straggler is, starting with the good situation of an equal workload but unequal cluster. You have a cluster of 4 nodes, 2 of which are twice as computationally powerful as the other 2. You may have a situation when a job uses all the resources of the smaller nodes and have the resources of the larger nodes. This is a common situation and everything is okay. But you might also have a workload which uses all the computational power of the larger nodes, and in this case, tasks which are executed on the smaller nodes will require at least twice as much time to complete. In Spark, you can enable a speculative execution. So, what does it do? It checks for slow tasks within the given interval of time governed by the Spark speculation interval option. Then Spark computes the median execution time of the tasks which have been finished. This part is defined by the Spark speculation quantile option. And finally, all the tasks which are slower than the median multiplied by the Spark speculation multiplier are rescheduled. Let's see an example. You have a job consisting of 100 tasks, and the speculation options are provided below. The median execution time of the 75 tasks which have been finished is 2 minutes. So, Spark will consider a task a straggler if it executes for more than 3 minutes and will reschedule it. The second case of stragglers, which is not a good case, is uneven data distribution. For example, if you have a cluster which consists of 4 equal nodes and your data is distributed uniformly, then it is okay. Each executor will process roughly the same amount of data. But if your distribution is long-tailed, then some of the partitions will be much larger than the others. This causes some executors to do more computations and results in the so-called false stragglers. As you have already learned from the other lessons of our specialization, there are different approaches to resolve the problem of skewed data. There are sorting or repartitioning, which uniformly shuffles data, and you may also try to use a custom partitioner if you know your dataset well. Let's sum up. Spark, like other frameworks created on top of Hadoop, was built to run on a cluster of unreliable commodity hardware. Distributed computations may cause a problem called stragglers. The good case are stragglers caused by equal load and unequal resources. In this case, you can enable speculative execution to reschedule slow tasks on other nodes. But there are also false stragglers, which are caused by the skewed data. To solve this case, you should consider using sorting, repartitioning, or even implement a custom partitioner.